Micro and nanoplastics in soil and crop systems. 1. Microplastics in soil, inventories, effect, and environmental risks. Abstract. The omnipresence of microplastics, MPs, in the environment has garnered immense scientific and public interest. Recent studies indicate that these contaminants are not restricted to the aquatic environment, but probably are more prevalent in terrestrial systems, including agricultural soils. Soils are vulnerable to MP contamination through multiple pathways, including the disintegration of plastic mulches, sewage sludge for soil amendment, irrigation with, and atmospheric deposition. We present a comprehensive synthesis of the current literature on microplastics in soil systems, focusing on their occurrence, impacts on soil properties, including microbial assemblages, and potential to affect biogeochemical cycling. A systematic literature search was conducted using major scientific databases, and over 150 articles published between 2010 and 2024, including review papers from leading and Springer journals, were evaluated. The findings reveal that microplastics can alter soil physical and chemical properties and affect the rhizosphere's nutrient cycling and microbiota. It also shows the lack of among the methodologies and often lack quality control in reported data. The current research provides insights into microplastic-soil interaction, but significant gaps remain regarding the long-term implications of microplastic accumulation in soils. Future studies should address standardized detection methods, elucidate crop uptake mechanisms, and assess the impact on food safety and human health. The chapter underscores the urgent need for harmonizing methodologies and undertaking simulation modeling to understand the long-term effects of microplastics in soil and to design policies to mitigate MP contamination in soil systems. Keywords. 1.1 Introduction. The proliferation of plastic production over the past several decades has led to widespread environmental contamination by plastic debris, with microplastics, plastic particles 0.001 and 5 min size, emerging as ubiquitous contaminants in various ecosystems. 2015, 2011, 2017. Al. 2022, Bay, 2023. While early research predominantly focused on marine systems, an increasing number of studies now document MPs, occurrence and potential impacts in terrestrial environments. Al. 2022 and 2020. Al. 2020 a 2022 C. 2024. Al. 2021. Al. 2023 and 2024. Al. 2021 Soil is particularly vulnerable due to the application of plastic mulches. Al. 2016 Serrano Al. 2021 Al. 2020 Al. 2015 Irrigation with containing MPs. Al. 2020 a 2022 C. Al. 2021 Atmospheric deposition. Al. 2022 and sewage sludge application for soil amendment and 2024. 111 Background and scope. With an increasing global population, food security has emerged as a significant issue in recent times. The United Nations has included it in the Sustainable Development Goals, SDGs, i.e. SDG 2, Zero Hunger, which primarily focuses on ending hunger, achieving food security, improving nutrition, and promoting sustainable agriculture. Most countries have intensified agriculture to meet the increasing food demand. 2016. Al. 2010. Intensive agriculture has doubled crop production. Al. 2002. Ray Al. 2012 by introducing new resilient high-yielding varieties, extensive irrigation, synthetic nitrogen, phosphorus, pesticides, herbicides, and soil amendments. Al. 2001. Consequent to these pressures of increasing productivity, large-scale soil degradation is reported by the United Nations Convention to Combat Desertification, UNCCD, 2023. The UNCCD stated that over 100 million hectares of healthy and productive land are lost yearly based on the reporting figures from 126 countries across regions, underscoring the need to address the issue of soil degradation on priority. One of the most prevalent ways is the addition of sludge to the soil to improve its nutrient content, organic matter, and water retention capacity, and 2024. However, with the addition of sludge comes other pollutants like heavy metals, persistent organic pollutants, and microplastics, al. 2024. Another fact to consider is that agricultural land is one of the largest terrestrial biomes on the planet, 2016. The intensification of agriculture has exerted massive pressure on the planet's water resources, and almost 70% of the water from underground aquifers and surface water bodies is used in agriculture, FAO 2021, al. 2017. To overcome the issue of water scarcity, both treated and untreated has been in agriculture, introducing gigantic quantities of microplastics, al. 2020 b 2022 c. al. 2021 and pharmaceuticals, al. 2022 into the soils. Agricultural practices have evolved rapidly over recent decades, with the adoption of greenhouses for climate-smart agriculture, plastic mulches to decrease water losses via evaporation and increase the temperature of soil, al. 2019 Li al. 2022 and drip irrigation for optimizing irrigation water use to overcome climatic stressors, al. 2024. However, introducing plastics into the environment eventually degrades, resulting in gigantic microplastics and even nanoplastics quantities in different environmental matrices, including soil, al. 2022 2023, al. 2023, al. 1989, Li al. 2024. The issue was exacerbated further when biodegradable bags and plastic were introduced, since most of them were not fully biodegradable. Instead, they broke into tiny particles, creating a more serious environmental issue in the long term. The reports and claims of microplastics altering soil properties include an exhaustive list of chemical properties from changes in soil texture, structure, aggregate stability, porosity, permeability, infiltration rate, bulk density, saturated hydraulic conductivity, water holding capacity, electrical conductivity, change in soil pH, nutrient cycling, reduction in soil fertility, to name a few. Besides, the MP also act as a vector transporting hydrophobic contaminants, and at the same time, can also leach loosely bounded contaminants due to degradation. There is emerging evidence of microplastic translocation into the plants and its effect on the microbiota in the rhizosphere. 1.2 Materials and Methods. 121 Literature Search Strategy. A systematic literature search using the keywords microplastics in soil, plastic mulching, and microplastics in agricultural soils was performed in Web of Science, Scopus, PubMed, and Google Scholar. The literature search was restricted to peer-reviewed articles published in English between 2010 and 2024. A total of 158 articles were screened. The review articles with similar data were excluded for redundancy. 122 Inclusion and exclusion criteria. Were published in peer-reviewed journals. Were published in peer-reviewed journals. Focused on microplastics in terrestrial settings. Focused on microplastics in terrestrial settings. Addressed microplastic occurrence, transport, or effects in soil systems. Addressed microplastic occurrence, transport, or effects in soil systems. Provided experimental, observational, or modeling data. Provided experimental, observational, or modeling data. Included sufficient detail regarding MP detection and quantification. Included sufficient detail regarding MP detection and quantification. Concentrated solely on aquatic environments or waste, sludge, without discussion of terrestrial transfer. Concentrated solely on aquatic environments or waste, sludge, without discussion of terrestrial transfer. Lacked sufficient or statistical. Lacked sufficient or statistical. Units are not reported clearly. Units are not reported clearly. Data quality objectives are not met. Data quality objectives are not met. 123 Data extraction and synthesis. Study location and soil characteristics. Study location and soil characteristics. MP characteristics. size range, polymer types and concentrations. MP characteristics, size range, polymer types and concentrations. Main findings, inventories and effects on soil properties. Main findings, inventories and effects on soil properties. Microplastic presence in soils. Country region. Matrix. Inventory. Size of MPs. Polymer types. Findings. References. Australia. 2,800 to 19,000 tons of MP year, 2.3 and 15.8 tons MP Ha over the lifetime in the top 75 100 of soil. Al. 2016 Al. 2016 B. China. Agriculture. 0.56 million tons. Mulch covering some 20 million hectares of farmland. 2006 Al. 2014. Nanjing and Jiangsu, China. Fish pond bank soil. 207,340 MP. Li Al. 2019. Bamboo forest soil. 200 MP. Greenhouse soil. 400 MP. Vegetable farm soil. 427,573 MP. Tea garden soil. 407,740 MP. Shanghai, China. Urban soil. 78,129 MP. L. 2018. Southern China. 1971 m above sea level. 410,610 MP. 801,080 MP. 95,61,1170 MP. 97,80,11,130 MP. 50,70 MP. 410,520 MP. 501,060 MP. Each site was 30 m x 5 m from where 6 random samples were collected. And 2018. Xinjiang, China. Agricultural soils. 0 to 52 Ha mean 121.5 Ha. Mulch reside. L. 2016. United States of America. Municipal soil waste. 0.506%, having size less than 2,000 WW for 20-25,000. PET, polyester, polystyrene and foam. MPs constitute 5% WW of the MSW. Southern China. 1908 m above sea level. 691,110 MP. 2042 770 MP. 22,322 5960 MP. 2300026940 MP. 5060 MP. 641,290 MP. 1361,570 MP. And 2018. Southern China. 1894 m above sea level. 475,30 MP. 1490 MP. 1090013430 MP. 122101468 MP. 10 MP. 46550 MP. 17230 MP. Southern China. 1890 m above sea level. 1561,630 MP. 4064,080 MP. 20,292,0530 MP. 2485,024920 MP. 1020 MP. 57650 MP. 48650 MP. Buffer Zone, Chai River Valley, Southern China. Forest 1890 m above sea level. 1010-1280 MP. 2583-370 MP. 9231-1230 MP. 1166013990 MP. 1050 MP. 671-110 MP. 457-80 MP. Hungary. Arable land greenhouse. 225-61-69 MP. Payai PVC and PP. Tomato plantation. And 2022. Shenyang Agricultural University, China. Arable land. 2899 and 8885 MP. PIPP and PET. Mulching experiment since 1987 as source and maize. Li L. 2022 Bay. China. Upland mulched soil. 754 477 MP. PI PET Ps. L. 2021 B. Changsha, China. Topsoil 20 of agricultural land. Pot experiment showing effect of HPDE and polyethylene in Chinese cabbage. Yisheng Al. 2021 China. Arable land. 1,629.68 tons year. MPs resulting from the disintegration of plastic gauze. This info is based on remote sensing observation and models. Mo Al. 2021. Prefecture, Japan. Paddy land. 2 to 123 microcapsules, mean SD40 826 pieces, 6369. 25 min size. Pai. 19 sites were surveyed for microcapsules coated. Al. 2021. Taiwan. Tainan City Agriculture Farms. 12117 MP M2. Range of sizes from 1-5 min form of pellets, foam, fragments, films, microbeads, and others are reported. PI, LPDI, PP, and PS. About 3 times higher MPs in farms adjacent to roads compared to farms away from road. L. 2021. Tamil, India. Arable land. Not reported in terms of numbers. Only information was given as ratio to depths. 010 was 37.97%, 1120 was 35.07%, and 2130 was 36.99%. Plastic mulch in fields growing tomato. And 2021. City, Korea. 05 topsoil. Average 700 MP. Roadside soils 1108 MP, upland soil 3440 MP, agriculture soil 664 MP. PEPP, black styrene butadiene rubber SBR. L. 2021. Switzerland. 29 floodplain soils in Swiss Natural Reserve. 90% of Swiss floodplain soils contain MPs. 0.05075. Dominance of particles in 500 source. PP, PA, HPDI, PVC, PUR, PET, PS, ABS, PA, PC. And 2018. Switzerland. 11 agricultural sites in the Swiss, with high use of mulch foil, mulch tunnels, and other plastic items. MPL in irrigation water. PA is the most abundant polymer in the 100-150 size range, and PE is most abundant in the size range of 150-300. Polyamide PA and PE are the most common polymers. L. 2022. Germany. Test agricultural fields in sludge 97.7 mpg sludge, applied soil 14.6 mpg, control soil 6.4 mpg PE, PA. Only 1.4% of load was observed in deep soil where sludge was applied. L. 2022. Greece. Agricultural soil 030, Ilia County. 301 140 MP in fields planted with watermelons, 6938 MP in fields with tomato plantation. 2500 1668 MP for watermelon planted soils, and 3322 MP for tomato planted soils. 0.55 m. The abundance was 286 138 MP for watermelon planted soil and 3623 MP for tomato planted soil. PIE and black mulch film. Watermelon is planted twice, so input is twice. That might explain the higher MP load in watermelon planted soils. L. 2021. Spain. Murcia loamy soil. 010 depth 23,02937 MP, 1030 depth 21791069 MP. 32 LPDA. Plastic mulch application for 12 years of different types, including 8 LDPE plus 6 pack plus 1 biodegradable. Van Al. 2021. Netherlands. Agricultural soils. 888 500 MP. 32. PI Pipe. 10 tones Ha compost applied for 7 years. Van Al. 2021. Switzerland. Arable land. 22.433 tons year. Organic compost. Al. 2021. Tanzania. Irrigated land. 0.21150 mpg PET, HDLE LDA PS. Al. 2022. Mauritius. Arable land. 321 0024440 MP. Pipe and PA. Al. 2021. Tunisia. Irrigated soil with treated. 13.21089 to 852.24124 MP. Polivier Pi Pibilati PP. Al. 2021. Chile. Agricultural fields. 180,266 to 306,360 MP. PI Pipe PS. Sewage sludge application. Al. 2019. Ontario. Canada. Arable land. Fields 1, 2, and 3 prior to the application of biosolids 18, 187 and 541 MP, respectively, and post-application of biosolids in fields 12 and 3 were 25, 130 and 298 MP. PAPPPS, PMMA, PA, polyester, nylon paint, EVA, EPDM. Field 1, 10.24 Ha. Field 2, 26.1 Ha, and Field 3, 34.4 Ha were treated with biosolids. Al. 2020. Mexico. Arable land. 402,000 MP. LPDA. Mulch. Al. 2021. Shanxi Province, China. Agricultural soils. 1433,410 MP. 0049 were the predominant type. Were the most dominant shape. PS PA PP HD PA PVC PET. Ding Al. 2020 Northeast part of the Tibetan Plateau, China. Soil. 20 to 110 MP. Films were the dominant shape. 88.34% of MPs were 500. Pipe B PA. L. 2020. Schleswig-Holstein, Northern Germany. Farmland 15 locations. 379 MP were identified in of dry soil. Particle abundances in the sampling units ranged from 0 to 217.8 MP soil, with a mean abundance of 3.7119 MP per site. PIPP nylon. About 34% of sites contained MPs. Harms L. 2021 U. Xinjiang Autonomous Region, China. Agricultural soils. 80.3493 MP in filed where mulching was used for 5 years. 308.1381 MP in fields mulched for 15 years. 1075.63468 MP soil in fields where mulching was for 24 years. Films. Payai mulch films. 394 sampling sites in 19 provinces where plastic mulches are used. 040 depth were samples in 1M2 sires. L. 2020. Middle Franconia, Southeast Germany. In agricultural farmland, 0.5 Ha. 16 MPs of 1,5 m. In the soil, 0,125 MP, with a mean abundance of 0.34, 0.36 MP. No plastics in 5 out of 14 samples. The total weight MPs found was 0.005 grams. Fragments and films were the most common shapes, 2 were. 62.5% MPs were white. Others were transparent, blue or green. No particles below 2 m in length. 10 pa, 4 pp and 2 ps particles. No plastic mulch was used, and the farmland was regularly at 20 to 30 depth. L. 2018. Shandong Province and Suzhou, Jiangsu Province, China. Greenhouse soil. MP content in was 380.1093 MP in the control site. 1,003,786 MP in the cultivated soil. In Suzhou, 391,000 MP is in the control site, and 1,303,400 MP is in the cultivated soil. Dominant size range 2,100 pa. A total of 34 surface soil samples, 0-10. Li L. 2021, Jiangxi Province, Southeast China. Experimental plots filled with quaternary red clay. Control plot 16.427 MP. Plots amended with pig manure for 22 years 43.8162 MP. Yisheng Al. 2021 B. Murcia region, southeast Spain. Vegetable fields 0-10, where plastic mulch was used for at least 10 years. Average concentration 2116-1024 MP of dry soil. 32000. L. 2021. In province, Midwestern Korea. Agricultural farms where soil mulching, greenhouses, and rice cultivation paddies. 107,630 MP. PIPP and PET. L. 2021. Town City, Xinjiang, China. Agricultural soils. 40.35. 421,290 MP. 902,000. However, the most abundant were 300,800 in soil mulched for 30 years, i.e. small MP as the mulching period increased. PIA. Mulch films used for over 30 years. Li L. 2020. Village and China. Agriculture farms intensity. 0,800 MP in 010, 0,200 MP in 1020, 0,2200 MP in 2030. MPs in field that has had intermittent mulching for 30 years was 2,200 MP, in was 900. MP. LPDA. Farms with continuous and intermittent mulching, small and large size farms and low and high intensity tillage. L. 2020. City, Shandong Province, Northern China. Agriculture soils. 310,568 MP, average, 1444,986 MP. Dominant size was 0.5 min 010 and 0.5 min the 1025 layer of facility agricultural soils. The dominant shape was films and fragments. Polypropylene, ethylene propylene copolymer, and polyethylene. Smaller MPs tend to migrate as they were more in number in deeper layer. L. 2021. Hangzhou Bay floodplain bordering Shanghai, Hangzhou, and China. Floodplain agricultural soil. Average non-mulched 263 MP. Mulched soil average was 571 MP. Films and were dominant 1,300 in size. Polyethylene, polypropylene, polyester, rayon, acrylic, and polyamide. Joe Al. 2020. Spain. Agricultural soil. Average 937.40 MP light density, 1105.70 MP heavy density in soils without application of sewage sludge. Average 213950 MP light density, 3061680 MP heavy density in soils with application of sewage sludge. 51000 in size. Fragments and films. PVC. Microplastics were found in 97% of the analyzed samples. Van den Berg al. 2020. Heilongjiang Province, China. Agricultural soil. 08400 MP. Average at sites vary between 5087 to 40692 MP. 5100 and 100. Pi Al. 2020 Province, China. Agricultural soil amended with sewage sludge. 545.9 MP after amendment with 30 tons ha yearly, 87.6 MP in soils after annual amendment with 15 T ha annually, 5 MP with no compost application. Al. 2020 B. PS polystyrene, PE polyethylene, PP polypropylene, HDPE high-density polyethylene, PVC polyvinyl chloride, PET polyethylene terephthalate. B strings, C films, D fragments. 5-1 m size fraction. 1025 m size fraction. 025005 m size fraction. Microplastics effects on soil chemical properties. Location. Soil type. Microplastic type. Effect. References. Hunan. HN, China. Red soil. Pai. No significant difference in soil pH where soil was, however there was a considerable pH reduction in soil. Li Al. 2021 B. Zhejiang ZJ, China. Paddy soil. Pai. Higher pH in soil and not in soil. Shandong SD, China. Soil. Pai. No effect on pH, China. Sandy loam soil in pot experiments growing 6 varieties of maize, maize L. PLA, PE 100-154 size. The soil pH increased in presence of PLA and decreased in pots with PA. L. 2020. Netherlands. Sandy agricultural soil. Netherlands. LPDA and biodegradable mulch films. An increase in pH and a decrease in electrical conductivity was observed. Chi Al. 2020. China. Sandy loam agricultural soils with maize plant. HDPA and PLA particles of 100-154 size. Soil pH increased. Yang Al. 2021 C. China. Sandy loam agricultural soil. Polyethylene PE, polystyrene PS, polyamide PA, acid PLA, polybutylene succinate PBS, and butyrate PHB. At a concentration of 0.2% MP, the soil pH was not much affected. However, at 2% MP, the soil pH decreased in the presence of PE and PS, and increased in experimental soils with PLA and PHB. Dissolved organic carbon content increased by low doses of PLA, PE, PS, PA, and PBS. The highest DOC was with 2% PLA. NH4 plus N content was not affected by the high-dose MPs, but decreased by the low-dose MPs, especially PLA and PHB. L. 2022. Hangzhou, China. Cultivated lessial soils from county in climate-controlled chambers. PP particles 180. The addition of a low level of microplastic had a minimal effect on the OC, inorganic N, total P, humic, and acid in the DOM solution. L. 2017. Nanjing, Jiangsu Province, China. Surface soil 020 from an abandoned rice paddy field. PLA powder 2050. The presence of PLA did not affect the soil microbial community. PLA could trade off the priming effect of carbon source. L. 2020. Xinjiang Province, China. Farmland soil. Plastic film. Soil organic matter and inorganic nitrogen were decreased. The microbes actinomycetes decreased and increased. Over 10 years, exposure of residual plastic film in farmland decreased the soil fertility and changed the microbial community structure. L. 2018. Brandenburg, Germany. Grassland dry sandy loam soil. Polyester length of 1.28003 and a diameter of 0.030008. 0.4 g for 100 g soil. Microplastics increase nutrient retention by 70%, soil aggregation by 18%, and soil pH by 4%. MP impacted soil enzymes, respiration, and ecosystem. L. 2021. Qingdao, North China. Cropped sandy loam soils 0-20. PE and size 8.68500. Increased soil seed availability. L. 2021. 1.3 results. The literature search revealed several thematic areas where microplastics interact with soil. The findings can be broadly into 1. Occurrence and distribution, 2. Impacts on soil properties, and 3. Impact on microbial population in soil. 131. Occurrence and distribution of microplastics in soil. Recent studies have documented the presence of microplastics in agricultural soils across diverse regions, including Europe, Asia, and North America, and 2024. Al. 2024. Al. 2016. A. B. Hurley and 2018. Al. 2018. Hanif Al. 2024. Al. 2018. Al. 2020. The main contributors of microplastics in agricultural soils are degraded plastic mulches, treated and sewage sludge for soil amendments, besides airborne MPs, micro-rubber from tires, Al. 2025, degraded drip lines, plastic bags, and others. Microplastic concentrations in agricultural soils vary significantly from a few particles per kilogram to over 105 particles per kilogram, with higher concentrations observed in intensively managed systems. Al. 2018. An enormous quantity of microplastics, 5 and possibly nanoplastics, 1 are generated from plastic mulching in agricultural farms due to environmental degradation from UV radiation, thermal degradation, photooxidation, mechanical breakdown, erosion, and biological activity, e.g. earthworm ingestion, 5 min size, Al. 2016, Al. 2017, Al. 2018 is a conspicuous source of microplastic input into soils. The soil irrigated with has higher MP concentrations, i.e. 5190 MP compared to non-irrigated soil, where an average of 20-30 particles 1 Al. 2016b. Some of the thermoplastics can persist in soil for a long time undergoing fragmentation and may even become nanoplastics, Al. 2018. Studies have shown that using compost can contribute significantly to microplastic soils. An estimate based on experimental results indicated an average abundance of 2,400-358 MP1 dry weight in the compost product GUI Al. 2021. This study stipulated that during composting, a single large expanded polystyrene EPS, PE, and polypropylene PP could release 463 MPs GUI Al. 2021. Others have also highlighted significant input of microplastics from compost and reprocessed waste GUI Al. 2021. Several studies have underscored the ecological impacts of microplastic addition on soil, but over 120 studies have microplastics in soils, in 2023. Another significant issue is the discrepancies in data quality, which underscore the need for a standardized monitoring and assessment protocol. The soil microplastic data is summarized in Table 1.1. Meanwhile, the meta-analysis of studies, see Table 1.1, confirms a significant presence of microplastics in soils globally. The data highlights significant variability in MP concentrations, polymer types, and particle sizes. The heterogeneity in methodologies used, however, renders comparison infructuous. The variation in the kind and inventories of soil microplastics has steady links to the sources, i.e., in regions where the sewage sludge is used for soil amendment or the use of compost or biochar regions, depending on regional practices and environmental conditions. The annual MP input from degraded mulches and the use of for irrigation in Australia resulted in a reported accumulation of 2.358 tons Ha1 of microplastics in the top 10 of soil. The total annual microplastic input is reported to vary between 2,800 and 19,000 tons. Several studies from China highlighted a significant microplastic concentration originating from plastic mulches in farmlands. In province alone, over 20 million hectares of agricultural farms use plastic mulches. The enormous concentration of 97-80-1130 MP1 in 5250 size fractions, whereas in other studies for different types of soils, including forest, greenhouse soil, and vegetable farms, the concentrations were 205-73 MP1. At the bank of a fish pond, the soil has a concentration of 207-340 MP1. In tea garden soil, the microplastics were 407-740 particles per kilogram, whereas in urban soils in Shanghai, microplastics are believed to result from atmospheric deposition and urban runoff. The MP in urban soils were 78-12-9 MP1. The presence of microplastics in agricultural soils in Germany that are treated with biosolids sludge has a higher microplastic concentration of 14.6 mpg, one of soil compared to agricultural soil, where the sludge was not applied 6.4 mpg1. The dominant polymers in these soils were PA, PA, and PS. Microplastics were also reported from greenhouses in Hungary that were planted with tomatoes. A concentration of 225-61-69 MP1 of soil was reported. The main polymers were PE, polyvinyl chloride PVC, and polypropylene PP, which are essentially derived from greenhouse materials and biosolids. The floodplain soils in Switzerland were also contaminated with microplastics. About 90% of the samples had microplastics ranging between 0.05 and 0.751 of soil. The main polymers detected were PA and PA, which are linked to irrigation water. Microplastics in Spanish agricultural soils are omnipresent, especially due to the excessive usage of sewage sludge and plastic mulch for agricultural applications. In Murcia, Spain, a top 10 of soil where plastic mulch was used for 12 years showed a microplastic load of 23,029-37 MP1 of soil. The United States Environmental Protection Agency, US EPA, has authorized the use of biosolids on agricultural lands, forests, rangelands, and degraded lands that are to be reclaimed. The reports that the biosolids have 0.506% MP in a size range of 422-5000 raise the concern of likely chemical changes in soil properties due to the presence of PET, polyester, and polystyrene foams that are commonly reported. Biosolids are also applied in agricultural soils in Canada. A report from Ontario reported 18,541 MP1 of soil before biosolids application, which changed to 25,298 MP1 post-application. This reduction in number can be due to the downward movement of MPs in the soil profile or uptake by the microbial communities and within the plant's root systems. In Tamil, India, the surface soil layer up to 30 depth has a high concentration of plastic mulch residues, with the highest concentration amounting to 37.97% in the top 10. In developed nations like Japan, microcapsules are used to add, and reports of microcapsules from paddy soils in the region are quite striking. An average of 48.26 microcapsules per kilogram of soil have been reported. Microplastic particles of PET and PS have also been reported from irrigated soils in Tanzania, where the concentrations are as high as 0.21150 mpg1. The data availability on microplastics in soil demonstrates the wide range of concentrations that vary across several orders of magnitude within similar applications of sludge or biosolids within the soil, use of treated for irrigation, and use of plastic mulches. The reasons for this deviation can be the different methodologies and protocols used. There is little information on data quality objectives, with a few exceptions. Most studies have not reported on positive controls and blanks. Several studies have reported numbers of MPs in a unit mass of soil, while others report microplastic weight in micrograms and even percentage of soil mass. 132 Effects on soil properties. An increasing microplastic load in soil has been demonstrated to influence its physical and chemical properties, and 2025. Microplastics are reported to have the potential to alter soil structure, soil aggregate stability, water holding capacities, and nutrient dynamics. Al. 2018, Al. 2019, Al. 2022. The microplastics are known to have the potential to act as vectors for contaminants and can desorb these contaminants along the way in the soil profile. Besides, microplastics themselves are chemically complex and can leach these chemicals into the soil as they degrade. Laboratory and field experiments have also indicated changes in soil porosity affecting the water dynamics. Al. 2018. Degraded PE microplastics reduce the soil nitrogen and phosphorus levels in bulk soils. Al. 2022. The changes are not limited to the soil's physical attributes, i.e., blockage of root pores, altered water availability, and chemical change, levels of organic and metal contamination. Al. 2020, Al. 2021, Al. 2024, but also affect the rhizosphere's microbial community, which can be crucial for nutrient cycling, plant growth, and health. Al. 2022. Studies have reported reduced seed germination rates and lower crop yields in microplastic contaminated soils. Al. 2024. 1321 Soil structure and porosity. Microplastics are reported to obliterate the soil structure, a vital element defining soil fertility and productivity. Microplastics in soils influence the movement of water, gas exchange, and root penetration. Microplastic incorporation in the soil matrix perturbs the natural aggregation process since they occur in varied shapes, fragments, granules, films, and sizes 15000, altering the spatial arrangement of soil particles, changing the bulk density, porosity, and permeability. In 2025. A study reported that irregularly shaped microplastics can interfere with the formation of stable soil aggregates. 1322 Water retention and infiltration. Microplastics in soil may significantly alter the water-holding capacity and infiltration rates. They have been observed to increase the number of, which can decrease water and nutrient retention capacities, and 2018. Microplastics with hydrophobic surfaces can also induce water repellency, further affecting infiltration and potentially increasing surface runoff. These hydrological alterations in soil characteristics can affect the retention of nutrients and contaminants within the soil profile. 1323 Bulk density and soil aggregation. Microplastics affect soil bulk density, which is also a measure of compaction. Since most microplastics are lower in density than mineral grains, their incorporation can decrease the overall soil density and potentially alter root penetration. And 2020. As many agricultural fields receive a continuous input of sludge or biosolids, where the microplastic abundance is high over time, soil aggregate structures can change to less stable forms. This warrants a need for long-term studies to understand how the physical integrity of soils evolves with sustained microplastic contamination. 1324 Changes in pH and nutrient dynamics. Microplastics may affect the chemical equilibrium of soils by influencing pH and nutrient availability. There is a report of an increase in soil pH due to high-density polyethylene HDPE and acid PLA at 1 in 10% concentration, Al. 2022. The pH also impacted soil microplastic sorption. The sorption capacity decreased as pH increased, Al. 2018. Polystyrene microplastics have shown changes in surface sorption, and electrostatic interactions, Luo al. 2020. Some research indicates that certain plastic additives, such as phthalates and a BPA, can leach into the soil matrix, altering its chemical characteristics, al. 2018. Leaching these compounds may lead to changes in pH, affecting nutrient solubility and bioavailability. For example, pH shifts can alter the speciation of essential nutrients such as phosphorus and nitrogen, impacting plant uptake and microbial metabolism, and 2018. Additionally, the presence of microplastics can interfere with the cation exchange capacity of soils, potentially modifying the retention and mobility of both nutrients and pollutants. 133 Sorption of contaminants and pollutants. Although plastics are considered stable materials, they undergo physical and chemical degradation. Once plastic enters the environment, it degrades and disintegrates into smaller sizes, and as the microplastics age, they are more likely to absorb pollutants, Ding al. 2020 A. Microplastics in soil are not chemically inert. Their surfaces can absorb various contaminants, including heavy metals, pesticides, and organic pollutants. The capacity of microplastics is primarily determined by their polymer composition, surface area, and degree of weathering, al. 2022. Studies suggest that microplastics can act as a vector for pollutants that bind and concentrate pollutants, potentially enhancing their bioavailability to soil biota. For instance, plastic particles with high surface area to volume ratios have been found to absorb hydrophobic organic compounds, which may desorb and enter the soil solution under certain environmental conditions. This dual role as both a sink and a source of contaminants complicates the assessment of risks associated with microplastic pollution. The studies conducted on microplastics inducing chemical changes in soil are summarized in Table 1.2. Some studies show that microplastics in soil perturb the soil's organic matter, which is critical for soil fertility. Microplastics also influence nutrient cycling, water retention, and the microbial community in the rhizosphere. The presence of microplastics may alter the decomposition and processes of organic matter. The studies in Table 1.2 highlight that microplastics can hinder the absorption of organic compounds onto soil particles, altering carbon sequestration dynamics. The change often leads to less diverse microbial communities in the root zone, potentially obliterating the rate of organic matter disintegration and nutrient and metal uptakes. The microplastics perturb methane CH4 emissions, PE, microplastics with enhanced methane emission and suppressed NO2 Han al. 2022 While terephthalate PET, microplastics with biochar reduce CH4 emission by altering redox conditions Han al. 2022 Bay 134 Effects on soil microbial communities and ecosystem functions. The change in soil's chemical characteristics perturbs the soil microbiome. Microplastics in the soil change the porosity and permeability, significantly affecting water absorption and retention capacities. Microplastics also affect nutrient and trace metal availability, indirectly affecting microbial community structure. The presence of and polystyrene microplastics in soil decrease the abundance of, and which are crucial for nutrient cycling and maintaining soil fertility, al. 2024. Microplastics create a conducive environment for microbes capable of metabolizing synthetic polymers, like stress-tolerant fungi affecting nitrogen cycling, al. 2020. At a concentration of 1%, microplastics have been seen to enhance nitrogen, N-fixing and phosphorus P bacteria, and increasing bioavailable N and P but inhibiting like ammonia-oxidizing bacteria AOB, reducing nitrification rates, al. 2020, al. 2022. This disruption in microbial activity elevates nitrous oxide N2O emissions due to incomplete denitrification, al. 2012. Microplastics stimulate microbial respiration by increasing dissolved organic carbon and soil porosity, leading to higher CO2 emissions, al. 2021, al. 2022. Microplastics with co-contaminants, including heavy metals and antibiotics, exacerbate soil antimicrobial resistance and disrupt nutrient. Al. 2022, Al. 2023. Microplastics act as vectors for organic contaminants and leach additives like phthalates and A into the soil, inducing toxicity on microbial species and resulting in lower microbial biomass and diversity. Al. 2018, and having a cascading effect on overall soil fertility. 1.4 Mechanistic insights and interactions. Complex interaction occurs between microplastics and the soil matrix, bringing about chemical changes. However, understanding the mechanisms underlying the chemical effects of microplastics in soil requires a multidisciplinary approach. The current understanding is underpinned by results from laboratory experiments, field studies, and simulation modeling demonstrating the impact of polymer types, shape, and size on soil bulk density, porosity, permeability, efficacy, as a vector of pollutants and their toxicity. Studies have also demonstrated that plastic degradation by mechanical abrasion or UV weathering enhances its ability to absorb contaminants. Several field studies, especially in areas that use plastic mulches or sewage sludge for soil amendment, exhibit altered chemical properties compared to control uncontaminated areas. The field experiments and also highlight the variation in response to microplastic presence depending on the concentration of MPs, polymer type, soil type, microbial assemblages, plantation crops, and land use history. Environmental ecological modeling provides an edge and is beginning to integrate diverse environmental parameters to predict the long-term impacts of microplastics on soil ecosystems. Some of the modeled results suggest that even low microplastic concentrations can profoundly affect the microbes in the rhizosphere and the soil structure when exposed for a long time, decades. Evidence has emanated on several indirect effects of microplastics in soil, such as the copresence of microplastics and trace metals modifying the microbial community, which alters the bioavailability of metals or enhances the toxic effect on biota. There is a need to pursue research to understand the interactive and cumulative impact of multi-stressors on soil health. 1.5 Future perspectives and research gaps. Limited efforts have been put into studying microplastics in the terrestrial environment, although most of the microplastics originate from land and land-based sources. The limited information on microplastic inventories in soil, quantities, types of polymers, and sizes of microplastics has made it challenging to comprehensively elucidate the effects of microplastics on soil chemical properties. Without a harmonized methodology for microplastics in soil, different sampling strategies, microplastic extraction, quantification, and limit comparison across studies, emphasizing the need to develop a standardized protocol. Most of the reported studies have examined the short-term effects of microplastics in soil employing and pod experiments. However, long-term field studies and a multi-stressor approach are essential to understand the cumulative impact of contaminants that coexist with soil microplastics and how they affect soil health. Understanding microplastic interactions with contaminants and their mechanistic, ecological response and bioavailability is not fully understood. This understanding is vital for assessing toxicity, risk assessment, and designing remediation strategies. The information on how soil moisture, temperature, and pH influence the carbon content and greenhouse emissions in the presence of different polymers is limited, and more research is needed. Additionally, emerging research on microplastics, biological and abiotic degradation pathways in soil offers promising avenues for understanding their persistence and transformation in soil. Studies focusing on the role of soil microbes in the biodegradation of microplastics could provide insights into natural attenuation processes and inform the development of bioremediation strategies. Finally, looking at the complexity and interdisciplinary nature of microplastics in soil, it is essential to bring together experts in soil science, polymer chemistry, microbiology, and environmental toxicology to unravel the multifaceted impacts of microplastics in soil and support the development of comprehensive management strategies aimed at mitigating their environmental and ecological risks. 1.6 Conclusion. Microplastics are a marker horizon of the Anthropocene, with gigantic quantities added to the terrestrial environment due to the degradation of plastic mulch films. the use of sludge for soil amendment, composts, and for irrigation. Consequently, microplastics are regarded as emerging contaminants with profound implications on the chemical properties of soil, besides the impact on the microbiota in the rhizosphere that is critical for maintaining healthy soil. Microplastics are seen to influence the soil structure, hydrodynamics, nutrient cycling, and contaminant, posing significant challenges to the integrity and functionality of soil systems. Research conducted between 2010 and 2025 has provided valuable insights into these mechanisms, yet many uncertainties persist regarding microplastics' long-term and synergistic impacts in diverse soil environments. The role of microplastics as physical disruptors, chemical vectors, and substrates for microbiota plastosphere highlights the complexity of their interactions with soil components. The growing volume of literature underpins the evidence indicating microplastics can disrupt soil aggregation, alter porosity and permeability, water holding capacities, and modify the chemical of soils by leaching additives like phthalates, BPA, etc., and adsorbing metals and organic contaminants. Their presence in soil provides a unique substrate for microbes. Some eukaryotic forms prefer to these polymers, affecting the soil microbial communities and key ecosystem functions, potentially affecting agricultural productivity and soil health. The potential of microplastics in creating imbalances in biogeochemical response and amplifying greenhouse gas fluxes, especially of CO2, CH4, and N2O, further underscores the need for mitigation strategies to address greenhouse gas emissions and their contribution to global warming. This synthesis presents the current knowledge on microplastics, occurrence, uptake, and impacts in soil systems. Integrating findings from diverse studies highlights the complexities and emerging trends in this field. Given the rapid expansion of plastic production and use, future research and policy efforts must the mitigation of microplastic contamination in soil systems. By advancing our understanding of the mechanisms governing microplastic interactions with soil microbes, plants, stakeholders, from researchers to policymakers, can work together to develop sustainable agricultural practices that safeguard ecosystem health and food security. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: Al 2012, Denitrification Potential of the Northern Arabian Gulf, an Experimental Study. Environ Assess 18412710312, org 10100 7S106610112483Y. Al 2017, Waterlogging in Arid Agriculture Areas Due to Improper Groundwater Management, an example from Kuwait. Sustainability 9-11-2-131. Al 2011, Microplastics in the Marine Environment. Mar Bull 6281596160, 5 PubMed. Al 2017, The Plastic in Microplastics, a Review. Mar Bull 119-11222, PubMed. VK Al 2024, Effects of Microplastics on Soil Microorganisms and Microbial Functions in Nutrients and Carbon Cycling, a Review. Total Environ 924-17143, 5 PubMed. Al 2021, Low-Density Microplastics Detected in Sheep and Soil, a case study from the intensive vegetable farming in southeast Spain. Total Environ 755-142-653, PubMed. Al 2022, Microplastics in Agricultural Drainage Water, a link between terrestrial and aquatic microplastic pollution. Total Environ 806-150-709, PubMed. Al 2021, assessing the presence of microplastic particles in Tunisian agriculture soils and their potential toxicity effects using as bioindicator. Total Environ 796, 148959 PubMed. M. al. 2015, Biodegradable Plastic Agricultural Mulches and Key Features of Microbial Degradation. 993103911056 PubMed. N. al. 2024, Unveiling the Impacts of Microplastic Pollution on Soil Health, a Comprehensive Review. Total Environ 951, 175643 PubMed. H. al. 2020, Mixing Effect of Acid Microplastic and Straw Residue on Soil Property and Ecological Function. Chemosphere 243 125271 PubMed. L. al. 2024, Meta-analysis of impacts of microplastics on plant heavy metal accumulation. Environ 348 123787 PubMed. Y. al. 2021, Plastic Contamination of Forest, Urban and Agricultural Soils, a Case Study of City in the Republic of Korea. J. Soils Sediments, 21112. F. al. 2019, Evidence of Microplastic Accumulation in Agricultural Soils from Sewage Sludge Disposal. Total Environ 671, 411 420 PubMed. J. al. 2020, Transfer and Transport of Microplastics from Biosolids to Agricultural Soils and the Wider Environment. Total Environ 724, 138334 PubMed. A. al. 2018, Microplastics as an Emerging Threat to Terrestrial Ecosystems. Glob 24140-51416 PubMed Central. Ding L. al. 2020, The Occurrence and Distribution Characteristics of Microplastics in the Agricultural Soils of Shanxi Province, in northwestern China. Total Environ 721 37525 PubMed. Ding L. al. 2020b, High Temperature Depended on the Aging Mechanism of Microplastics under Different Environmental Conditions and its Effect on the Distribution of Organic Pollutants. Water Rays 174 115634 PubMed. E. 2006, P. Films for Agricultural Applications. J. Film Sheet 2285102. H. al. 2021, Quantification and Analysis of Microplastics in Farmland Soils, Characterization, Sources, and Pathways. Agriculture 11-330. FAO 2021, The State of the World's Land and Water Resources for Food and Agriculture, Systems at Breaking Point. Synthesis Report 2021, Rome. Org 1040607654E. S. al. 2020, Analysis of Microplastics in a Remote Region of the Tibetan Plateau, Implications for Natural Environmental Response to Human Activities. Total Environ 739 140087 PubMed. X. al. 2022, Microplastics Change Soil Properties, Heavy Metal Availability and Bacterial Community in a Contaminated Soil. J. Hazard Mater 424 127364 PubMed. B. al. 2021, Microplastic Addition Alters the Microbial Community Structure and Stimulates Soil Carbon Dioxide Emissions in Vegetable-Growing Soil. Environ Toxicol 42 352 365 PubMed. J. al. 2018, Microplastics in Air, Are We Breathing It In? Environ Health 115. B. al. 2022, Antibiotics in, Baseline of the Influent and Effluent Streams in Kuwait. Toxics 10-4174, PubMed Central. HCJ al. 2010, Food Security, The Challenge of Feeding 9 Billion People. Science 327, 5967812, 818 PubMed. T. 2016, Soil Degradation, Land Scarcity and Food Security, Reviewing a Complex Challenge. Sustainability 83281. Gui J. al. 2021, Microplastics in Composting of Rural Domestic Waste, Abundance, Characteristics, and Release from the Surface of. Environ 274, 116553 PubMed. N. al. 2022, Microplastics in the Atmosphere, a Review. J. Environ Expo Assess 116. DOI 10.20517202107. Han et al. 2022, a co-occurrence of microplastics and stimulated the methane emission, but suppressed nitrous oxide emission from a rice paddy soil. J. Clean Prod 337130504. Han et al. 2022, B. Influence of polyethylene terephthalate microplastic and biochar coexistence on paddy soil bacterial community structure and greenhouse gas emission. Environ 292, 118386 PubMed. Hanif MN al. 2024, Impact of Microplastics on Soil Physical and Chemical Properties, Soil Biological Properties, Soil Biota, and Response of Plants to It, a Review. J. Environ Technol 2116, 10277103118. Harmsike al. 2021, Amount, Distribution and Composition of Large Microplastics in Typical Agricultural Soils in Northern Germany. Total Environ 758 1436 15 PubMed. MN 2025, Adverse Impacts of Microplastics on Soil Physicochemical Properties and Crop Health in Agricultural Systems. J. Hazard Mater Ad 17 100528. E. al. 2021, Abundance of Above-Ground Invertebrates in Agricultural Systems under Glyphosate and Microplastics in Southeastern Mexico. Environments 811-130. AA al. 2017, Microplastics in and Terrestrial Environments, Evaluating the Current Understanding to Identify the Knowledge Gaps and Future Research Priorities. Total Environ 586, 127, 141 PubMed. Y. al. 2020, Agricultural Plastic Mulching as a Source of Microplastics in the Terrestrial Environment. Environ 261, 14096 PubMed. T 2018, Sorption of Organic Compounds by Aged Polystyrene Microplastic Particles. Environ 236 218 25 PubMed. Hurley L. 2018, Fate and Occurrence of Micro-Nanoplastics in Soils, Knowledge Gaps and Possible Risks. Environ Health 16116. EA al. 2021, Microplastics in Agricultural Soils, a Case Study in Cultivation of Watermelons and Canning Tomatoes. Water 1316-2168. JR al. 2015, Plastic Waste Inputs from Land into the Ocean. Science 340 76223, 768 771 PubMed. BKKK S. Fowler SW 2023, Microplastics MPs in Marine Food Chains, Is it a Food Safety Issue? In F. Lead, Advances in Food and Nutrition Research. Academic Press 101-140. DOI 10.10162022070005. MA al. 2019, Mulching as Water-Saving Technique in Agriculture, Review Article. Bull Recent 43-1147. N. al. 2021, Accumulation of Microcapsules Derived from Coated Fertilizer in Paddy Fields. Chemosphere 267, 129185 PubMed. DLB 2021, Material Flow Analysis of Plastic and Organic Waste in Switzerland. Soil Use 3722, 77288. N. al. 2021, Interactions and Effects of Microplastics with Heavy Metals in Aquatic and Terrestrial Environments. Environ 290-11810-4 PubMed. SK al. 2021, Abundance and Characteristics of Microplastics in Soils with Different Agricultural Practices, Importance of Sources with Internal Origin and Environmental Fate. J. Hazard Mater 403-12399-7 PubMed. MV/AM 2021, Effect of Plastic Film Mulching on the Distribution of Plastic Residues in Agricultural Fields. Chemosphere 273, 128590. M. al. 2020, Microplastics as Pollutants in Agricultural Soils. Environ 265-1149-80 PubMed. MNHC G 2022, Analysis of macro and microplastics in riverine riverbanks and irrigated farms in Tanzania. Arch Environ Toxicol 82-1142, 157 PubMed. Lee J.Y. Al 2024, A Comprehensive Review of Urban Microplastic Pollution Sources, Environment and Human Health Impacts and Regulatory Efforts. Total Environ 946, 174297 PubMed. Lee Q. Al 2019, Separation and Identification of Microplastics from Soil and Sewage Sludge. Environ 254, 113076 PubMed. Lee W. Al 2020, Microplastics in Agricultural Soils, Extraction and Characterization After Different Periods of Polythene Film Mulching in an Arid Region. Total Environ 749, 14142, 0 PubMed. Lee Q. Al 2021, Are microplastics correlated to phthalates in facility agriculture soil? J. Hazard Mater 412, 125164 PubMed. Lee H. C. Al 2021 B. Long-term fertilization history, alters effects of microplastics on soil properties, microbial communities and functions in diverse farmland ecosystem. Environ Technol 55846584668 PubMed. Lee F. Al 2022, A Straw Mulching for Enhanced Water Use Efficiency and Economic Returns from Soybean Fields in the Les Plateaux, China. Rep 12117111 PubMed Central. Lee S. Al 2022 B. Macro and Microplastic Accumulation in Soil After 32 Years of Plastic Film Mulching. Environ 301 18945 PubMed. Y. Al 2022, Effects of Polyethylene and Acid Microplastics on Plant Growth and Bacterial Community in the Soil. J. Hazard Mater 435 1290 57 PubMed. EK HWQ, CR 2014, White Revolution to White Pollution Agricultural Plastic Film Mulch in China. Environ Race 99091001. H. Al 2017, Response of Soil-Dissolved Organic Matter to Microplastic Addition in Chinese Less Soil. Chemosphere 185-9, 7917 PubMed. M. Al 2018, Microplastic and Mesoplastic Pollution in Farmland Soils in Suburbs of Shanghai, China. Environ 242, 855-862 PubMed. YM Al 2021, Effects of Microplastics and Drought on Soil Ecosystem Functions. J. 5859-88996. Luo Y. Al 2020, Distribution Characteristics and Mechanism of Microplastics Mediated by Soil Physicochemical Properties. Total Environ 726 1383-89 PubMed. F. Al 2020, Effects of Plastic Mulching on the Accumulation and Distribution of Macro and Microplastics in Soils of Two Farming Systems in Northwest China. Peer J8, E10375 PubMed Central. Mo X. Al 2021, Estimation of Soil Microplastic Input Derived from Plastic Gauze Using a Model. Total Environ 793, 148577 PubMed. L. Al 1989, The Air Pollutant 2 as Initiator and Promoter in a Liver Model for Chemical Carcinogenesis. Carcinogenesis 1034-35440 PubMed. A. Al 2021, Microplastics in Outlets of Bandar Abbas City, Iran, a potential point source of microplastics into the Persian Gulf. Chemosphere 262, 128039 PubMed. E. L. Al 2018, An Overview of Microplastic and Nanoplastic Pollution in Total Environ 627, 13771388 PubMed. L. S. Futter M. 2016, A Pollution, Do Microplastics Spill Onto Farm Soils? Nature 530 7762, 1488 488 PubMed. L. Futter M. S. 2016b, Are Agricultural Soils Dumps for Microplastics of Urban Origin? Environ Technol 5021, 0777107779 PubMed. S. Al 2018, Identification and Quantification of Macro and Microplastics on an Agricultural Farmland. Rep 81179550, PubMed Central. Chi al. 2020, Effects of Plastic Mulch Film Residues on Wheat Rhizosphere and Soil Properties. J. Hazard Mater 387, 121711, PubMed. H. al. 2018, Effects of Soil Residual Plastic Film on Soil Microbial Community Structure and Fertility. Water Air Soil 229, 111. DEGD 2021, Microplastics in Agricultural Soils, Effluents and Sewage Sludge in Mauritius. Total Environ 798, 149326, PubMed. Ray DK al. 2012, Recent Patterns of Crop Yield Growth and Stagnation. 311293, PubMed. MCA 2020, Microplastic in Terrestrial Ecosystems. Science 368 649, 81430, 1431, PubMed Central. MC al. 2019, Microplastic Effects on Plants. New 223.3, 10661070, PubMed. IA 2022, Greenhouse Farming as a Source of and Microplastics Contamination in Agricultural Soils, a Case Study from Southeast Hungary. 71 14357. IA 2023, Plastic Contamination in Agricultural Soils, a Review. Environ 35 113. M. al. 2022, Microplastics in the Soil Environment, a Critical Review. Environ Technol 27 102 408. A. al. 2022, Dietary Microplastics, Occurrence, Exposure and Health Implications. Environ Race 212 113150, PubMed. M. 2018, Microplastics in Swiss Floodplain Soils. Environ Technol 52 6359 1359, 8, PubMed. ME al. 2020, Microplastics Affect Sedimentary Microbial Communities and Nitrogen Cycling. 11-12372, PubMed Central. Serrano H. Martin L. A.M. 2021, Biodegradable Plastic Mulches, Impact on the Agricultural Biotic Environment. Total Environ 751 4122, 8, PubMed. K. al. 2025, Pavement Ware Generates Microplastics in Stormwater Runoff. J. Hazard Mater 480 113649, 5, PubMed. Z. al. 2016, Plastic Mulching in Agriculture. Trading Short-Term Agronomic Benefits for Long-Term Soil Degradation. Total Environ 55697, 5, PubMed. AS al. 2022, Agricultural Application of Microplastic-Rich Sewage Sludge Leads to Further Uncontrolled Contamination. Total Environ 806, 150611, PubMed. D. al. 2001, Forecasting Agriculturally Driven Global Environmental Change. Science 292, 55152 81284, PubMed. D. al. 2002, Agricultural Sustainability and Intensive Production Practices. Nature 418, 6898 671, 677, PubMed. S. Fowler S.W., M. 2020, An Assessment of Microplastic Inputs into the Aquatic Environment from Streams. Mar Bull 161 11538, 8, PubMed. S. Fowler S.W., T. 2020b, Microplastic Particles in the Persian-Arabian Gulf, a Review on Sampling and Identification. Mar Bull 154 111100, PubMed. S. al. 2022, A Micronanoplastic in the Aquatic Environment, Problems and Challenges. Animals 123297, PubMed Central. S. al. 2022, B. A Preliminary Assessment of Size-Fractionated Microplastics in Indoor Aerosol Kuwait's Baseline. Toxics 10271, PubMed Central. S. al. 2022, C. Microplastics in Kuwait's Streams. Sustainability 1423 15817. AS Fowler SW 2023, Environmental Microplastics, a Significant Pollutant of the Anthropocene. In Kane C. AM, Microplastic Sources, Fate and Solution. Springer Nature Singapore, Singapore, 89105. DOI 10.10079789801990696565. S. Al. 2024 Sewage Sludge as Soil Amendment in Arid Soils, a Trace Metal, Nutrient and Trace Organics Perspective. Emerge 1111000420. UNCCD 2023, at least 100 million hectares of healthy land now lost each year. United Nations Convention to Combat Desertification. Sites default files 202.310, data %20 dashboard %20 press %20 release %20n. Van den Berg P. al. 2020, Sewage Sludge Application as a Vehicle for Microplastics in Eastern Spanish Agricultural Soils. Environ 261, 11419, 8 PubMed. Van B. al. 2021, Sources of Light-Density Microplastic Related to Two Agricultural Practices, the Use of Compost and Plastic Mulch. Environments 8436. XX al. 2020, Mycorrhizal Impacts on Root Trait Plasticity of 6 maize varieties along a phosphorus supply gradient. Plant Soil 448, 7186. FX Song-N 2021, Polyethylene microplastics increase cadmium uptake in lettuce, sativa L, by altering the soil microenvironment. Total Environ 784, 147133, PubMed. Y. al. 2022, Investigation of Microplastic Pollution on Paddy Fields in City, Southern China. Environ Raise 2954 81300, 81307. B. al. 2023, Combined Effects of Microplastics and Cadmium on the Soil Plant System, Seed Accumulation and Microbial Activity. Environ 333 121960, PubMed. C. al. 2024, A Review of the Application and Impact of Drip Irrigation under Plastic Mulch in Agricultural Ecosystems. Agronomy 14, 81752. Yang M. al. 2021, Influences of Different Source Microplastics with Different Particle Sizes and Application Rates on Soil Properties and Growth of Chinese Cabbage, Brassica L. Environ 222, 112480, PubMed. Yang J. al. 2021, B. Abundance and Morphology of Microplastics in an Agricultural Soil Following Long-Term Repeated Application of Pig Manure. Environ 272, 11602, 8, PubMed. Yang W. al. 2021 C. Effects of Microplastics on Plant Growth and Mycorrhizal Fungal Communities in a Soil Spiked with O Nanoparticles. Soil 155 10 8179. L. al. 2021, Distribution Characteristics of Microplastics in Agricultural Soils from the Largest Vegetable Production Base in China. Total Environ 756, 143860, PubMed. MS 2024, Sewage Sludge Usage in Agriculture, Are We Introducing Microplastics in Food Chain? Soils International Atomic Energy Agency 10278. A. al. 2022, Effects of Polyester Microfibers PMFs and Cadmium on Lettuce, Sativa, and the Microbial Communities, a study involving biochemical properties and profiles. J. Hazard Mater 424 12740, 5 PubMed. GY 2018, The Distribution of Microplastics in Soil Aggregate Fractions in Southwestern China. Total Environ 642, 1220, PubMed. D. al. 2016, The Status and Distribution Characteristics of Residual Mulching Film in Xinjiang, China. J. Agric 15, 1126392646. S. al. 2020, A Distribution of Low-Density Microplastics in the Mollisol Farmlands of Northeast China. Total Environ 708 135091, PubMed. L. al. 2020b, An Overlooked Entry Pathway of Microplastics into Agricultural Soils from Application of Sludge-Based Fertilizers. Environ Technol 54, 7424842555, PubMed. X. al. 2021, A Systematical Review of Interactions between Microplastics and Microorganisms in the Soil Environment. J. Hazard Mater 418-126288 PubMed. Q. Al 2021b. Effect of polystyrene microplastics on rice seed germination and antioxidant enzyme activity. Toxics 9-8179 PubMed Central. Y. Al 2022. Effects of microplastics on soil carbon dioxide emissions and the microbial functional genes involved in organic carbon decomposition in agricultural soil. Total Environ 806-150714 PubMed. Joe B. Al 2020, Microplastics in Agricultural Soils on the Coastal Plain of Hangzhou Bay, East China, Multiple Sources Other Than Plastic Mulching Film. J. Hazard Mater 388-121-814 PubMed. F. Al 2022, Microplastics Altered Soil Microbiome and Nitrogen Cycling, the Role of Phthalate Plasticizer. J. Hazard Mater 427-127944 PubMed. 2. Microplastics in crop systems. Abstract. The pervasive presence of microplastics MPs 5 and nanoplastics NPs 100 in agricultural systems poses significant risks to crop productivity, food security, and human-animal health. The terrestrial environments where plastic contamination is substantially higher remain understudied, particularly in the context of crop systems. This chapter synthesizes current knowledge on the uptake, translocation, and phytotoxic effects of micronanoplastics MNPs in crops, emphasizing the interplay of particle characteristics, size, polymer type, surface charge, and dose, crop species, developmental stages, and environmental exposure pathways. Smaller MPs, IG, exhibit greater bioavailability, infiltrating roots via transport, endocytosis, or crack entry modes, while foliar uptake occurs through stomata and trichomes. Analytical challenges, such as organic matrix interference during digestion, limitations in spectroscopic resolution, e.g. Fourier transform infrared spectroscopy, FTIR, Raman, and difficulties in distinguishing smaller MPs and NPs from natural particles, hinder accurate quantification. Advanced techniques including pyrolysis gas chromatography mass spectrometry, GCMS, inductively coupled plasma mass spectrometry, ICP-MS, and synchrotron-based imaging show promise but require standardization, and the information obtained is incomparable to existing data where mostly numbers are reported instead of mass. The toxicity is size-dependent, and these techniques lack the capability to provide any size information. Mechanistic studies reveal species-specific responses, dicots e.g. lettuce, carrot, and certain legumes, i.g. cowpea accumulate NPs more readily than monocots, e.g. wheat maize with polymer-dependent toxicity observed for polyvinyl chloride, PVC, PE, and polystyrene, PS. Critical gaps persist in understanding real-world NP interactions with aged weathered plastics, multi-contaminant effects, and long-term ecological impacts. The absence of harmonized protocols and field-validated risk assessments limits regulatory frameworks. This chapter underscores the urgency of interdisciplinary efforts to refine detection methodologies, elucidate translocation mechanisms, and evaluate food chain contamination risks, thereby informing strategies to mitigate plastic pollution in. Graphical Abstract. Keywords. 2.1 Introduction. Over the recent decade, research on microplastics MPs and nanoplastics NPs has grown dramatically. Nonetheless, marine organisms and the environment have been the focus of most of the research. Consequently, more marine animal species than our terrestrial species have been examined for the presence of MPs 5 and NPs 100, al. 2017, al. 2018, al. 2019. Although the annual release of MPs is 4 to 23 times higher in terrestrial environments compared to the aquatic environment, al. 2017, higher plants and crops have been very explored to monitor MP and assessments, al. 2024 and 2024, al. 2023. Plants form the primary source of human food. The Food and Agriculture Organization, FAO, lists 350,000 plant species, of which about 8.6%, 30,000, are edible for humans, with at least 7,000 species in cultivation, al. 2022, in yet another report of FAO, a handful of staple crops N255, including cereals N26, roots and tubers N17, pulses N26, vegetables N44, fruits N69, nuts N14, oils N28, herbs and spices N24, and sugars N3 and stimulant crops N4 provide the bulk of global food supply and pilling 2019. Evidence reports that these small groups of globalized crops have increased dietary homogeneity. However, a decline in their genotypic and phenotypic diversity has been recorded in the farmer's field over the past century. Al. 2014-2022 Bay. Further reports indicate a reduction in crop production when exposed to emerging contaminants like MPs and NPs. Al. 2022. Microplastics were confirmed as a risk to edible crops, and their movement and within the food chain are now known. Su Al. 2022. It is essential to comprehend the movement of micro-nanoplastics, MNPs, in plants since this information sheds light on their fate and pathways within the plant system. The presence of plastics affects the ecosystem as a whole, and its movement within plants acts as a vector for other hydrophobic contaminants, facilitating their extensive dispersion. From 2015 onwards, the majority of research is on the of microplastics to plants. Gong Al. 2021. Assessment of MP uptake is still nascent. In this chapter, we have summarized the key findings of these studies, the parameters affecting MP uptake, analytical methods to track the uptake, and the major mechanism of MNP absorption, as well as translocation within the crops. Major gaps have also been discussed. 2.2 factors affecting microplastic uptake by crops. Several studies have reported the adherence and absorption of MPs in crops. It has been believed that MPs cannot be directly internalized into plant tissue because they are too big to fit past the physical boundaries of intact plant tissue. Al. 2024, Al. 2021, Al. 2023. However, smaller MPs and NPs can be absorbed by plants in the same way as micronutrient particles are absorbed. Chemical and physiological barriers are among the obstacles that MPs must overcome to enter plants. MNPs form aggregates surrounding the plant tissues and can be adsorbed onto plants through various routes. An experimental study observed 54800 sized MNP aggregates on the seeds of during germination. Bosker al. 2019. These MNPs have adhered to the root hairs of seeds that pass the germination stage. In yet another study, polystyrene nanoplastics, PSNPs, predominantly adhered to the root surface, and no signs of uptake and translocation were recorded in root stocks of citrus plants grown. Al. 2025, except for alterations in the external root cell layers. The adherence created root barriers that inhibited nutrient uptake. The structure and composition of communities were altered due to PSNP adsorption on tomato leaves. Al. 2023. The presence of trichomes facilitated the accumulation of smaller-size PSMNPs on leaf surfaces of maize and soybean plants. Al. 2023. The deposition altered the wax layer from crystalline to amorphous form. Very few studies have demonstrated the uptake of NPs by plant tissue. MP or NP uptake in plants depends on plant size, species, particle charge, particle concentration, and exposure duration. 2-1 size. The particle size plays an important role in the absorption of the MNPs by the plant cells. Few studies have proven that smaller MPs and NPs are more readily absorbed by the pores between the cell walls and internalized through the vascular bundles. Al. 2024. A study revealed that smaller-sized PSNPs 50 and 100 readily penetrated the root epidermis of taro, whereas PSNPs 200 and 500 were not detected in the tissues. Su Al. 2025. Hence, it suggests that a smaller-sized plastic particle is easily. It also minimizes the water uptake as it blocks the pores, thus decreasing the germination rate. Studies on cucumber plants treated with NPs of 100, 300, 500, and 700 size revealed that 100 particles were readily engrossed by the roots and transferred to the shoots. The reason behind the easy translocation of smaller particles was a smooth passage between the cellulosic cell walls and the condensed pectin network, al. 2021. The uptake of MNPs in maize seedling roots exposed to polystyrene beads of 0.2, 0.5, and 1 NPs, and 2 and 5 MPs was investigated in a microcosm, al. 2023. The findings demonstrated that under particle sizes in root and shoot biomass stayed constant. Compared to MPs, the NPs significantly boosted their distribution and accumulation in roots. When treated with 5 PSMPs, none were found in any root tissues, and the PSMPs of 2 size were mostly found in the xylem vessels, al. 2023. Similar to this report, it was further demonstrated that 100 PSNPs accumulated in the root tissue of beans and reportedly blocked the cellular pores, potentially obstructing nutrient transport, al. 2019. Particles 5 in size were not observed in the root tissue. In yet another investigation, carrot roots were studied for PSNP absorption and translocation, dong al. 2021. The group revealed that 1 MNPs entered the roots and accumulated in the intercellular layer. However, these could not enter the cells. Those sized 0.2 migrated up to the leaves, while the particles 1 entered the roots only in the presence of arsenic. This suggests the possible role of other environmental contaminants, along with size in the absorption and uptake of MNPs. The study further reported arsenic increased the negatively charged area of PS and also distorted the cell walls, allowing the smooth uptake of PS particles 200. Yet in another study, strawberry seedlings were exposed to 100 and 200 PSNPs, where both sized particles were detected in the vascular bundles of the petioles after 7 days of exposure. On the 14th day, 100 NPs passed the petioles, whereas 200 could not be directly observed in the strawberry seedlings, strongly suggesting that MP absorption and translocation also depend on the size of vascular bundles, al. 2023. It was also reported that different sizes of MPs not only influence their internalization, but also the physiological responses and molecular mechanisms in plant species. PSNPs of 100 and 500 size, when exposed to lettuce roots, were absorbed and translocated to stems and leaves with a stronger movement ability of smaller NPs. The physiological, biochemical, and genetic parameters were affected to a greater extent by larger NPs, al. 2024. A general observation from the above studies is that while NPs can enter plant cells directly, larger MPs find it difficult to get through the tissues of vascular plants due to the plant's cellular structure. Also, the thickness of the cell wall and epidermis varies according to crop type, environmental parameters, contaminants, growth stage, etc., which define the translocation of NPs and MPs across these barriers. Consequently, the size of MNPs that will be absorbed by the plants will be different under different experimental conditions. 222 species. Prior studies have indicated that distinct plant species may employ distinct coping mechanisms to manage various environmental stressors, Gong al. 2021. The uptake of nutrients and defensive action against the emerging contaminants are diverse for diverse species. The responses of several plant species to identical MNP exposure are not well understood. Therefore, to make intelligible conclusions on the impact of MNPs on plants, a thorough analysis of the reactions of different plant species under the same experimental conditions is essential. An investigation on seeds of 4 plants, Italian lettuce, radish, wheat, and corn, exposed to PSNP and PSMP suspension, reported that the tolerance and sensitivity towards the MPs differed according to the crop type, Gong al. 2021. The Italian lettuce plant showed maximum sensitivity towards polystyrene exposure. The root-shoot ratio, dry weight, and length of Italian lettuce and corn were dramatically reduced, whereas the radish and wheat plants remained unaffected. This can be attributed to the difference in root exudates produced by the monocots, wheat and corn, and the dicots, Italian lettuce and radish. Similar responses were recorded by Al. 2023, in which lettuce and carrot plants were significantly affected, whereas barley and wheat remained unaffected. Al. 2023. A significant delay in seed germination of lettuce was recorded, whereas the biomass of carrots was decreased. The absorption and transportation of MNPs encounter numerous physical and chemical obstacles in plants that vary according to crop species and growth stages. The structure and obstacles vary according to the internal structure of plants. A comparison between wheat and maize revealed the latter absorbs more MNPs than the former. Al. 2023. The deposition was in different tissue types as well. In maize, larger PP particles were recorded in the stem, whereas smaller PPs were absorbed by wheat roots. In another study, it was observed that the MNPs can be absorbed during the seed germination stage. However, the early development of monocot species was not affected by PSMP exposure. Al. 2023. Rice and peanuts absorbed PSNPs at the seed setting stage and accumulated them at the grain maturation stage. Al. 2022. The MPs entered pea plants during the root development stage, while Casparian strips were forming. Al. 2022. However, contrary to the above, irrespective of the species, large MPs were found associated with leaf surfaces and trichomes both in maize and in soybean plants. Al. 2023. In addition to this, below-ground crops such as tubers, bulbs, and leguminous crops such as peanuts are more vulnerable to MNPs present in the soil. Peanuts absorbed PSNPs through their roots and reached the grains at the maturation stage. PSNPs at a concentration of 251 reduced the average seed weight of peanuts and also reduced the overall nutritional quality, minerals, amino acids, and unsaturated fatty acid content of the seeds. Al. 2022. Different polymers are absorbed differentially by plant species. A total of 11 different plastics, including polystyrene PS, PE, polypropylene PP, methacrylate PMMA, polyvinyl chloride PVC, polyethylene terephthalate, PET, polycarbonate PC, polyamide 6PA6, PA66, acid PLA, and polyco-terephthalate PBAT were exposed to cowpea, flowering cabbage, rutabagas, and qua. PVC, PET, PA, and PA66 could be found in all crop samples. The predominant components in the samples of all 4 crop species were PVC and PE, although cowpea samples had significant concentrations of PET. Additionally, the accumulation levels of different edible crop parts varied significantly. For example, in blooming cabbage samples, stems accumulated more NPs than leaves, while in cowpea samples, peas were higher in NP content than pods. Al. 2024. It becomes quite evident that MNP uptake and translocation are species-dependent. The crop itself grows in a complex environment, and each species is unique in structure and function. Experiments with multiple species and an array of polymers in field-realistic conditions would shed more light on the transmission of MNPs in terrestrial ecosystems. 223 particle dose. The effects of MNPs on plant systems are intricate and modulated by several factors, including exposure dose. Al. 2024. A meta-analysis of 37 studies on MP uptake concluded that higher doses of smaller MPs exert more pronounced inhibitory effects on root activity and biomass. Al. 2024. The effect of low 103, medium 105, and high 107 particles per was investigated on 4 crop types. Al. 2023. The highest concentration delayed the germination rates of lettuce, wheat, and carrot. The root length, shoot length, and biomass of germinated wheat seedlings were also reduced. Similarly, shoot length and bud biomass of carrot seedlings also decreased at the highest concentration of PSNPs. Further growth of the crops was monitored, and a reduction in the wet weight of wheat was observed. Al. 2023. Inhibition of root growth was recorded in onion seedlings exposed to 0.1 and 1 gl, 1 of PSNPs, as compared to a 0.01 gl1 concentration. Al. 2020. Rice and peanut grains absorbed PSNPs at a concentration of 251. Al. 2022. Overall seed setting rate and seed weight were significantly reduced when rice and peanut crops absorbed NPs at the grain maturation stage. Higher concentrations of MP considerably decrease plant growth and physiological activities, indicating a positive correlation between exposure dose and toxicity. Some researchers have shown that MPs can affect physiological and biochemical traits, as well as plant growth parameters through a variety of mechanisms. For example, a lower concentration of MPs, 5L1, increased root hydraulic conductivity, and higher PS treatment, 200L1, reduced the chlorophyll B and total chlorophyll content in wheat seedlings, Li al. 2023 Bay. 3 concentrations, 100, 300, and 500 L1, of carboxyl-tagged PSNPs invaded cotton roots, causing upregulation of genes related to antioxidant activity and inducing oxidative stress. Significant upregulation of genes involved in was observed at a higher dose of 300 LPSNPs in the above experiment, Li al. 2024. The PSCOOH treatment triggered the biosynthesis pathway, in turn stimulating the buildup of flavonoids and lignin. An altered sucrose metabolism was also observed in response to PSCOOH exposure at a higher concentration, Li al. 2024. Within the plant, translocation is also dose-dependent, as studied by Li al. 2019, who found that there were only a few sporadic fluorescent signals in the tissues of lettuce stems and leaves, with PSNPs sticking to one another in the vascular bundle, exhibiting grape or chain aggregation, and microbeads adhering to one another in the leaf tissue in the form of dispersion. This implies that the vascular bundle can only carry trace amounts of MNPs to the vascular systems of stems and leaves, Li al. 2019. MPs are ubiquitous not only in the terrestrial environment, but also in the atmosphere, al. 2022. Atmospheric MPs have been absorbed by the plant leaves through the stomatal and cuticular openings, al. 2023, al. 2023, al. 2021, sun al. 2021. In a recent study, a dose-dependent response was monitored by Li al. 2025. They reported the widespread occurrence of PET and PS polymers as a ruling factor in their absorption by leafy plants under field conditions. The concentrations were higher in the leaves of plants grown in locations near the Dacron factory proximal to a landfill site as compared to those grown in parks and university campuses, Li al. 2025. In addition to field plants, they experimented on leafy vegetables, brassica, L. sativa, and bay, planted in open-air fields and under greenhouse conditions. Likewise, the field-grown plants and the vegetable crops grown in open fields accumulated more PET and PS than the greenhouse vegetables. It was also observed that the outer leaves of these vegetables absorbed higher quantities of PET and PS than the inner leaves. Li al. 2025 also demonstrated the maize leaves exposed to dust collected from the Dacron factory, containing 1.05103G1 of PET, in a microcosm experiment accumulated 5 and 7 times higher magnitudes of PET at the 5th and 10th day, respectively. Upon having the dust concentration, almost double the amount of PET was absorbed on the 10th day. These observations indicate that plant leaves are the primary unit of vegetable crops, and the likelihood of MPs entering the food chain is greater via this pathway. This also warrants investigations on MP accumulation in herbivores and humans, taking into consideration the health and ecological risks. In experimental conditions, it is difficult to mimic the environmental concentrations of MNPs. Nevertheless, besides a range of particles available at varied densities, the plants in a terrestrial environment are under constant chronic exposure, and this should be taken into consideration while estimating the risk to the plants and indirectly to their consumers. 224 Surface chemistry charge. Environmental elements like ultraviolet radiation, heat radiation, chemical oxidation, and biodegradation cause the MNPs to undergo a variety of surface changes. Carboxyl groups COOH are the most prevalent functional groups formed due to surface oxidation and functionality acquisition. Additionally, plants are more likely to absorb carboxyl-modified polystyrene microplastics, PSCOOH, with a negatively charged surface. It thus becomes important to investigate the uptake of MPs with carboxyl-tagged groups or charged particles by plants. Tomato leaves were exposed to differently charged nanoplastics, where positively charged MPs entered the leaf tissue and dispersed to the mesophyll cells with more devastating effects. Al. 2023. They caused growth inhibition, an increase in antioxidant enzyme activity, and altered gene expression. PSNPs tagged with amino and carboxyl groups were absorbed by rice seedlings. Post-absorption, PSCOOH affected ion transport and terpene biosynthesis in rice seedlings, whereas PSNH2 impacted the synthesis of macromolecules. Al. 2022. Carboxyl-modified PSNPs were found invading cotton roots. Li al. 2024. The treatment with PSCOOH activated the biosynthesis pathway, resulting in flavonoid and lignin accumulation, as well as modified sucrose catabolism. Li al. 2024. Collected both positively and negatively charged NPs. The uptake of amino-modified polystyrene nanoplastics with positive surface charges was restricted as the media and root exudates facilitated the aggregation of particles. Therefore, compared to negatively charged acid-modified nanoplastics, positively charged nanoplastics accumulated at relatively low levels in the root tips, but they also caused a greater accumulation of reactive oxygen species and more effectively impeded plant growth and seedling development. In contrast, the in xylem were frequently found to contain negatively charged NPs. These findings provided direct evidence that NPs can accumulate in plants, depending on their surface charge. Sun al. 2020. A quantitative estimation of MP in lettuce leaves indicated the toxicity was largely determined due to the surface functional group, and not only the accumulating coparticles. Su al. 2022. Contrastingly, the trace element copper as an additive to the soil, along with PSNPs, caused a reduction in its uptake at the 7th and 42nd day of exposure in pea plants. Al. 2022. 225 exposure time. The absorption and translocation of MPs differed according to the duration of the exposure. Longer exposure times typically result in higher MP accumulation and may be more pronounced detrimental effects on plant growth, even if the effects of MP exposure on plants are complicated and dependent on a number of variables. MNPs were absorbed by the plants after 7 days of sowing, indicating the ability of crops to uptake them at a very early growth stage. Gong al. 2021. Also, PSNPs of 100 and 200 size were observed till the petiole of the strawberry seedling on the 7th day. On the 14th day, direct observation of PSNPs was not evident. Al. 2023. Pea crops grown in MP-contaminated soil for 7 days showed 110% absorption of MPs. Al. 2022. A further chronic exposure maintained 107% absorption. PS beads were found in the stele on the secondary roots after 12 hours, and in the wheat's vascular tissue and epidermis after 48 hours. Li al. 2020. A dose-dependent MP uptake and effect was also recorded in cotton roots. Li al. 2024. A 7-day exposure of PSNPs to the roots of rice seedlings, the uptake of particles. Li al. 2023. While a 10-day exposure facilitated the accumulation of smaller PSNPs. 226 Polymer type. The uptake of microplastics, MPs, and their subsequent effects on plants are greatly influenced by the type of polymer they absorb. Polymer type is expected to affect the physiological and metabolic systems of crops. Most of the studies have explored the effects of PS particles. These have proven adverse effects on plant growth, nutrient uptake, photosynthetic capability, and other physiological parameters. Other polymer types have frugally been investigated. Among different plastics such as PS, PE, PP, PMMA, PVC, PET, PC, PA6, PA66, PLA, and PBAT, only PVC and PE were the dominant NPs accumulated in 4 crop types. Compared to stem and melon crops, the degree of NP enrichment in legume and leaf crops was higher, al. 2024. Al. 2022 reported the absorption of PI spheres in cortical tissues of roots and stems of sweet potatoes. The prevalence of PET or PS particles accumulated in field-grown plants, leafy vegetable crops, and maize leaves was reported, al. 2025. The effect of real-world MNPs, Ps, polyamide PA, polypropylene PP, low-density polyethylene LDPE, polyethylene terephthalate PET, polyurethane PU, polystyrene PS, polycarbonate PC of different shapes, films, foams, and fragments, was investigated on the growth of carrot seedlings, al. 2021. Both the shape and type of polymer affected the shoot biomass. It increased when exposed to all the polymer types except PS and PA. PET films recorded the highest biomass, followed by LDPE foams and PP films. Fragments in general also increased the shoot biomass. Foams, particularly LDPE and PS, reduced the shoot biomass. Similar effects were observed for roots, with double the intensity. PU foam exerted the maximum positive effect on root biomass, followed by LDPE films, PP fragments, and PET films. Irrespective of the shape, the MPs increased both the root and shoot biomass in carrots. Real-world MNPs comprise not only different types, but also additives such as plasticizers, blowing agents, and stabilizers to provide flexibility, roughness, durability, etc., which might also play a role in perturbing the plant growth. 2.3 Analytical methods for visualizing and tracking MP and NP uptake. Comprehending the uptake and translocation of MNPs by plants has grown in importance. Accurate tracking and quantification of MNPs in plants is made possible by the development of microplastic detection methods, including optical and electron microscopy, in addition to spectroscopy. Each of these methods has special benefits for illuminating the biophysical and biochemical relationships between plant tissues and MNPs. Al. 2023. The selection of detection techniques is critical to the precise identification of MNP absorption and translocation. The diverse size, shape, and polymer types make it difficult to standardize detection techniques. For the effective extraction of MNPs from plant tissues, researchers are looking into a number of approaches, including chemical and enzymatic digestions and density separation to segregate MNPs from the matrix. Observing the absorption and transport process of microplastics in plants under a microscope presents numerous challenges as well. For example, the small size and variety of shapes of MNPs make it challenging to identify and differentiate them from plant matrices. MNPs have been found in tissues using conventional microscopic methods like light and electron microscopy. However, these methods can only provide morphological information, as both natural and polymers closely resemble one another morphologically and often lead to false positives. 231 factors affecting the analytical ability. 2311 Plant complexity. The extraction of MNPs from the plant matrix is a crucial step. The digestion of organic matter in plant tissues for MNP extraction presents significant technical challenges due to the complex matrix of plant materials, which includes cellulose, lignin, and other recalcitrant biopolymers. Conventional chemical digestion methods, such as alkaline e.g., KOH acidic Ig, HNO3 or oxidative e.g., H2O2 treatments, often fail to fully degrade the plant's organic components without compromising the integrity of certain plastic polymers. Hurley al. 2018, in their study highlighted that incomplete digestion can leave residual organic particles, complicating MNP identification via spectroscopic techniques. Additionally, aggressive reagents like HNO3 or high-temperature treatments risk degrading susceptible polymers such as PET, PA, Col-Al. 2014 or acid, PLA, leading to underestimation of MNP in organic-rich matrices. Enzymatic digestion, while gentler, struggles with efficiency in rich tissues, requiring prolonged incubation times and is likely to leave plant residues, al. 2017. Moreover, validation of digestion protocols is exacerbated by the variability in plant tissues, necessitating species-specific optimization to avoid misidentification. These issues underscore the need for standardized, non-destructive methods tailored to plant matrices to ensure accurate MNP quantification. 2312 Miscellaneous transport mechanisms. An additional degree of complexity is introduced by the different transport pathways found in plant cells and tissues. Because MNPs can transfer across various parts of a plant, i.e., between the roots, stem, leaves, and fruits, it is challenging to elucidate the distribution and movement of MNPs in the plant system. Nevertheless, it is still unclear what the most dominant mechanisms governing the uptake, transport, and storage of MNPs in plant tissues are. It becomes imperative to conduct studies to identify MNPs in different plant parts to have a comprehensive understanding of the scale of MNP pollution in plants and to underpin regulatory mechanisms for MNP reduction in food chains. 2313 Lower concentration within plant tissue. Another obstacle to accurately quantifying and identifying MNPs in plant tissues is the lower occurrence. Existing detection techniques such as microscopy and spectroscopy differ in terms of resolution, sensitivity, and specificity. At times, they fail to provide high-confidence estimations whether the MNPs reported are a result of underestimation or the uptake mechanism itself. Consequently, it becomes crucial to distinguish MNPs from background noise and to develop techniques that can achieve lower detection limits. Some of the techniques used so far include microraman spectroscopy, microfourier transform infrared spectroscopy, FTIR, attenuated total reflectance Fourier transform infrared spectroscopy ATR FTIR, laser direct infrared LDIR imaging, analysis TGA, and optical and scanning electron microscopy, to name a few. 232 Microscopic methods. 2321 Optical microscopy. Although simple, cost-effective, and ideal for preliminary observation, its restricted resolution would not make it suitable for identifying extremely tiny particles. Al. 2008. Besides, the MP identification with optical microscopy is based on morphological characteristics. Al. 2022, which cannot provide polymeric confirmation, and at best one can say possible MPs. 2322 Scanning electron microscopy. Scanning electron microscopy, SEM, can produce high-resolution images and decipher morphological details of MNPs in plant tissues. In a study, SEM was coupled with fluorescent imaging to trace the uptake and translocation of PSNPs in rice and peanut grains. Al. 2022. Another study demonstrated tracking of 200 PSNPs in wheat seedlings using enhanced dark-field microscopy coupled with SEM, Li al. 2023 B. PSNP absorption and translocation from leaves to roots were traced using SEM and transmission electron microscope, TEM, in lettuce leaves, al. 2021. PS beads were located on the stele of the secondary roots after 12 hours, and in the wheat's vascular tissue and epidermis after 48 hours, by SEM Li al. 2020, and PSNPs were confirmed via SEM in dried cucumber tissue, Li al. 2021 B. The absorption of PSNPs tagged with europium lanthanides was observed in tomato leaves, and their transportation to roots was traced using SEM al. 2023. 2323 Confocal laser scanning microscopy. It is a powerful technique for tracking the transport pathways of MNPs and visualizing their spatial localization within plant tissues. This approach commonly uses fluorescent dyes to mark the particles and creates a three-dimensional image of the MNP embedded within the plant tissue. Fluorescent signals assist in tracking the MNPs absorbed in plant tissues. Confocal microscopy, in combination with a fluorescent dye Nile red, was used to demonstrate the uptake of NPs by the root tissue of cucumber and its further transportation to stem, leaves, and fruits. Li al. 2021. Absorption of PSNPs in rice roots was also confirmed by confocal microscopy. Al. 2022. Fluorescent signals of PSNPs were observed in BY2 cells under a confocal microscope. Al. 2012. 2324 Transmission electron microscopy, TEM. TEM has limited application in the detection of MPs or NPs, as extensive sample preparation steps are involved, as well as the restricted field of vision. Yet the morphology and primary size of PSCOOH were visualized via TEM imaging in cotton crops. Li al. 2024. To assess the actual size of the PS microspheres, a drop of the Nano-PS solution, 1GL1, was applied on TEM grids coated with allowed to settle and allowed to dry. The major and minor axes of TEM images were measured using the ImageJ tool to assess the particle diameters. Al. 2020 TEM was used to monitor the ultrastructural changes caused by the absorbed NPs in tomato leaves. Al. 2023. 233 Spectroscopy. Spectroscopic techniques, mainly vibrational spectroscopy, Raman, and infrared, are commonly used techniques for microplastic analysis in environmental samples. 2331 Fourier transform infrared spectroscopy. Fourier transform infrared spectroscopy, FTIR, is often used to identify the polymer type within environmental samples, including biological samples that have been digested. Although the method is mostly used to find the buildup of MNPs in marine biota, it is still not widely used for evaluating plant samples. 2332 Raman spectroscopy. Raman spectroscopy is another approach to molecular characterization. MPs can be distinguished from other particulate matter using Raman spectroscopy. Similar to FTIR, this method provides accurate identification, but it is particularly useful when combined with microscopic techniques for a more thorough investigation. Microraman spectroscopy is non-destructive in most cases and known to be effective for characterizing particles up to one size. 2333 Advanced Coherent Anti-Stokes Raman Scattering. More recently, the highly advanced coherent anti-Stokes Raman scattering is being observed as a novel tool to track the uptake of NPs by plant cells. Al. 2024. 2334 Inductively Coupled Plasma Mass Spectrometry, ICP-MS. This method provides information about the composition of MNPs. It provides additional information on the constituents present in the MNPs, as well as its quantity in terms of mass. Luo al. 2022 used this technology in a groundbreaking study to investigate how plants absorb MNPs. The study clarified the possible use of inductively coupled plasma mass spectrometry, ICP-MS, in environmental impact studies by successfully demonstrating its value in tracking and measuring NP absorption in plant species. Doping the NPs with lanthanide chelates offered a flexible approach for tracing the movement of MNPs within the plants. Luo al. 2022. Using time-gated luminescence and the time-resolved fluorescence of the chelate, europium-tagged polystyrene (PS) particles in the roots and shoots of wheat and lettuce were visualized. SEM was used to confirm the presence of PS within the plant roots. The researchers examined the uptake of these PS particles by wheat and lettuce using quantitative analysis with ICP-MS. Further, this technique was used to confirm the measurable levels of NPs absorbed by cucumber plants. Li al. 2021b. The NPs were tagged with palladium. 2335 Pyrogecy coupled with mass spectrometry, GCMS. Pyrolysis gas chromatography mass spectrometry, GCMS, shows promise as a method for measuring NPs, especially in samples with complex environmental matrices and low concentrations. Al. 2024. This approach provides significant benefits for the precise detection and measurement of all the plastics, including nanoplastics. Using cucumber as the model species, a novel method was devised to measure the uptake of nanoplastics in plants by combining alkaline digestion, cellulose precipitation, and ultrasonic leaching, followed by GC-MS analysis Li al. 2021b. The chemical composition and mass concentration of NPs in various crops, cowpea, flowering cabbage, rutabagas, and quail, were ascertained using a method that combined nitric acid digestion, multiple organic extractions, and pyrolysis gas chromatography mass spectrometry (GC-MS) quantification. The chemical composition and mass concentration of NPs in various crops, cowpea, flowering cabbage, rutabagas, and quail, were ascertained using a method that combined nitric acid digestion, multiple organic extraction, and GC-MS quantification. Although the accumulation levels varied considerably due to the crop type, the results demonstrated that PVC, PET, PE, and PA66 NPs could be absorbed by the crop species Li al. 2024. Contrary to the above two studies, due to the presence of naturally occurring styrene monomers in plant roots, wheat, and inadequate detection limits, GC-MS was not successful. In each species' root surface, 40 and 1 polystyrene spheres were accumulated, especially at the root tip. Nevertheless, the interior root structure showed no signs of plastic particles. Taylor al. 2020. 2336 Micro-X-ray Fluorescence, XRF. An innovative analytical method for examining the interactions between plants and nanomaterials is XRF. By offering lateral resolution in multi-elemental detection, XRF provides crucial information about the fundamental processes of these elements: absorption, movement, and accumulation in plant systems. Additionally, X-ray computed tomography is a non-destructive imaging technique that makes it possible to rebuild the scanned specimens in 3 dimensions. The study of plant root properties has made considerable use of XRF due to its ability to efficiently negate surface and need minimal sample preparation. To see the NPs in wheat roots, a synchrotron XRF was used. The uptake and translocation of NPs to the shoots could be. The NPs were collected in the root tip and the root maturation zones along the epidermis. Globular formations were detected by synchrotron-computed nano-CT, but as they were seen in both the treated and control roots, they could not be recognized as nanoplastics. An inorganic tracer PED was doped with the NPs that helped elucidate the plant NP interactions. Del Real al. 2022. 2.4 Mechanism of MP-NP uptake in crops. Since plant tissue is essentially a complex mixture of biopolymers, and several parameters influence MNP uptake and transport in plants, it is difficult to understand the precise mechanisms and ascertain their fate within a species experimentally. Despite the lack of research on this aspect, 4 mechanisms, i.e. transport, crack entry mode, endocytosis, and stomatal entry, are believed to play roles in the uptake and translocation of MNPs in crops. Al. 2024, Al. 2021. A brief overview of each mode is given in the following section. The internalization of NPs into plant roots and their subsequent migration to the aerial portion are deemed possible. Al. 2023. 241 Endocytosis. It has been demonstrated that endocytosis is a successful mechanism for MNPs to enter cells. Phagocytosis, pinocytosis, and receptor-mediated endocytosis are the 3 categories of endocytosis that may be distinguished based on the size of the material entering cells and the endocytosis process. Cells swallow solid particles, including PSNPs, into vesicles known as phagosomes through a process known as phagocytosis. A study established that PSNPs can be taken up by cultivated sycamore cells and delivered to the core vacuoles through phagocytosis. Phagocytosis is more commonly employed by immune cells to absorb and eliminate invading particles in humans. However, this has also been seen in plant cells. Al. 2006. The vacuoles of sycamore cells cultured with fluorescence MNPs for 12 hours displayed numerous bright spots of fluorescent signals, as observed under a confocal microscope. This suggested that the vacuoles were the final destination of MNPs following endocytosis. Al. 2006. It was also observed that PSNPs cluttered strongly and persistently adhered to the cell walls. This significantly hindered PSNP absorption. This challenge was overcome by combining the protoplasts of cultivated sycamores with a growth medium that contained PSNPs. Following an overnight incubation period, PSNPs were discovered outside of several cells and in the vacuoles. However, the endocytosis of plant cells to MNPs cannot be strongly supported by this experiment, as the sycamore cells lack the cell wall as a barrier. Numerous biological functions in animal cells, including polarity, motility, signaling control, and proper cell development, have been linked to independent endocytosis, al. 2011. Building on this hypothesis, and group had earlier demonstrated the internalization of glucose via independent endocytosis into the protoplast of BY2 cells in 2012. In a subsequent study, explored the engulfment of fluorescent PSNPs, 20 in BY2 cells. 15 minutes following the addition of fluorescence nanoplastics, BY2 cells showed clear, brilliant fluorescent signal patches under a confocal microscope. The very mobile, brilliant spots were dispersed widely throughout the cytoplasm after traveling along the threads. The fluorescence signal distribution in the cells was not substantially different from that in the cells incubated with 20 nanoplastics, and the 40 nanoplastics were equally quickly internalized, al. 2012. The findings also demonstrated that BY2 cells with cell walls may 40 nanoplastics. However, the size of vesicles considerably inhibits the endocytosis of some large MNPs, more than 100. According to other studies, if the restrictions on the cell wall are eliminated, cell protoplasts can even internalize MNPs up to 1,000 in diameter, al. 2012 and 2012. The two experiments mentioned above demonstrated that endocytosis is a mechanism by which nanoplastics can enter plant cells. However, in both studies, the endocytosis method depended on the creation of separate cell cultures, and there is not enough data to confirm this uptake mechanism for the entire plant. 242. Transport. The cells in the apical meristem of plant roots serve as the first line of defense against MNPs as they regulate cell division and differentiation, have high cell activity, are highly sensitive to external stimuli, and can secrete large amounts of mucus and secretions in response to an external signal. The mucus layer essentially captures the nanoparticles, creating a barrier for internal transfer, al. 2014. Besides this, the water channel plays a key role and absorbs the particles through gaps in the cell walls of the epidermal layer, which are further transferred to the vascular bundles, xylem, sun al. 2020. The external force required is supplied by transpiration, which is the process by which water is expelled from the plant through stomata on the leaf surface. Smaller particulate matter, including MNPs, is drawn with water from the roots upwards towards the shoots by the negative pressure or surface tension created in the plant as a result of water loss from the leaves. This process facilitates the transfer of MNPs with water through the porous plant cell walls. Transpiration pull plays a major role in the plant uptake and translocation of plastic particles, al. 2024. This is the predicted pathway of NP translocation from roots to aerial parts of cucumber, Li al. 2021. Transport of PSNPs from lettuce roots to leaves was established by Li al. 2019. It was revealed in their experiment that lettuce was unable to absorb 1 microbeads. However, a significant number of fluorescence signals were discovered within the cell walls when exposed to microbeads, 0.2. According to the findings, the MPs must first reach the level to pass through the barrier, subsequently moving along the free spaces of root cells and entering the root cortex or even the vascular bundles. The endodermic ring, on the other hand, prevents the transfer from the cortex to the vascular bundle. Therefore, external forces were believed to push the MNPs via en route to penetrate the endoplasmic plasmalemma, Li al. 2019. In a subsequent study, the PSNPs first entered the root system and thereafter transferred to the above-ground parts in lettuce, sativa, and wheat, Li al. 2020. The PS beads were observed inside the apical meristem of the roots, as well as along the entire lateral root cap. Li al. proposed that these particles in the mucilage of the root cap allow diffusion into the apical meristem tissue and enhance their perception of the cell wall, which is extremely unstable because of ongoing cell division. Li al. 2020. Sun al. 2020 demonstrated that MNPs can be transported through the IN. The study also showed that the transport of MNPs is significantly influenced by their surface charge. In particular, it was found that positively charged nanoplastics, 71, did not behave in the same way as negatively charged nanoplastics, 55, which were able to effectively enter plant vascular bundles via the pathway. MPs infiltrated through the roots of pea plants growing in MP-exposed soil. These were further translocated to the aerial parts. Al. 2022. A quantitative study on PSNP exposure from roots to shoots reported a very limited translocation, 3% in wheat and lettuce leaves. Luo al. 2022. It was further recorded that once absorbed via the roots and translocated to vascular bundles, xylem tissue of roots, they easily move upwards to stems and leaves with the water and nutrient flow. Electrostatic interactions may cause positively charged plastic nanoparticles to be trapped in plant secretions, or they may adhere to regions like root hairs and edge cells that have protective negatively charged mucosal coats. Furthermore, the transport mechanism may potentially be impacted by the chemical characteristics of MNPs. For instance, because of their poor water solubility and high water partition coefficient values, certain polymeric polymers with long alkyl chains and large molecular weights might be more challenging to absorb through the pathway. Therefore, to improve our comprehension of the extracellular transport mechanism of PSNPs, more research on the transport process of MNPs with various physical and chemical properties is required in the future. 243 Crack entry mode. A study on wheat and lettuce plants found that PS and PMMA particles could enter the plant roots through the cracks formed during lateral root formation. Li al. 2020. Effective absorption depends upon the polymer type and crack penetration. MNPs typically cannot diffuse into the intercellular space and pass through plant cell walls if their particles are bigger than the cell wall pores, 3.550, and intercellular plasmodesmata, 50-60. However, the ongoing cell division leads to the formation of porous tissue at the apical meristem, allowing the diffusion of MNPs. At the cell separation stage, pores are formed between the lateral root and epidermal cells, allowing the passage of MNPs into the root stele. Strong fluorescent signals were found in the cracks at lateral roots 5100 from the root tip by Li al. 2020, indicating that these ruptures serve as the main entry points for MPNPs into the xylem of lettuce and wheat roots. Within 2 hours, PS and PMMA entered the xylem duct, traveled through the xylem by the transpiration pole, and finally arrived at the wheat cortical tissue 12 hours later. The vascular system of the roots and stems was the primary location for MNPs that entered through these fissures, according to confocal pictures of wheat cross-sections. It is important to remember that granular plastics, mechanical flexibility might be the key to successful absorption. Nevertheless, studies on the process of crack penetration are lacking, and the findings of Li al. 2020 build our knowledge of a novel mode of MNP uptake and translocation. Future studies should also account for polymer type and crop species. 244 Stomatal entry. All three of the above-described absorption and translocation mechanisms involve MNPs that are absorbed in the roots of plants and move upwards from the roots to the shoots. MPs are absorbed by the crops through the aerial parts as well. A study recently found that maize leaves can absorb NPs and transport them downwards from leaves to roots. Sun al. 2021. Potential routes for nanoparticles to penetrate plant leaves include stomatal and cutaneous uptake. According to SEM data, PSNPs mostly showed up in and around the stomata on day 7, indicating that stomatal opening may be one way PSNPs penetrate the vasculature. Additionally, the investigation discovered that, following 2 days of exposure, NPs were found to be more prevalent in the stems, but less prevalent in the roots. This suggests that the sequence of NP translocation was from the leaves to the stems, and then from the stems to the roots. The high concentration of PSNPs in and around the stem's vascular system supported the leaf-to-root translocation through the vascular bundle, as seen in the fluorescent microscopy images. Unlike the xylem in the roots, the phloem, the main channel for transporting nutrients and water, is responsible for PSNP migration in the case of foliar uptake. Similar observations for PSNP absorption and migration were recorded in maize leaves, Li al. 2025. The absorbed MPs migrated from the bundle sheath to the phloem with the osmotic exchange in vascular tissue, according to high-spectral imaging, HIS, and confocal images of transverse sections of vascular tissue of maize stem. The possible source of MNPs for foliar stomatal uptake is aerosols. And coworkers reported the absorption of PSNPs through the leaves of lettuce, sativa, and its transport downwards to the roots. This reduced the micronutrients and essential amino acid content of the lettuce plant. Vascular bundles are the pathways for translocating the NPs to plant roots when entered through the leaves. This was also observed in the maize crop maize, Sun al. 2021. Foliar absorption and translocation to roots were recorded in tomato plants by and coworkers, al. 2023. In another study, foliar uptake and spread via stomatal openings were recorded in maize and soybean seedlings, al. 2023. However, the foliar uptake is largely defined by the leaf characteristics, Li al. 2025. High levels of PET polymer were found in the leaves of hibiscus, 1.23105 per GDW, and brassica, 5.32104 per GDW, out of the 12 plants that were examined at the Dacron factories. This was thought to be connected to faster respiration in these plants, which caused a greater flux of airborne MNPs to enter the leaves. Particles are more likely to enter leaves directly by gas exchange when transpiration rate and stomatal conductance are high, showing that leaves have a high stomatal exchange capacity. This implies that one of the primary pathways for absorbing PET is stomatal respiration. In addition, the size of stomatal pores in different plant species is an order of magnitude higher than the atmospheric MNPs, which allows an easy passage into the leaves. This was well demonstrated in the stomatal closure experiment of Lei and group, Li al. 2025. To demonstrate the passage of MNPs from leaves to other plant parts, a simulation experiment was conducted on maize seedlings. The PSNPs first accumulate on the leaf surface and then are internalized via the stomatal openings, migrating to the mesophyll cells and further into the trichomes. The absorption was using laser ablation inductively coupled plasma mass spectrometry, LAICPMS, whereas the passage was monitored through high-spectral imaging, HSI. Larger fluorescent signals were observed at the trichome tip compared to its base, indicating that trichomes served as a sink for the PSNP deposition in the plant system, Li al. 2025. 2.5 Limitations and knowledge gaps. There are very few studies conducted so far on MNP in crop systems, and most of the studies done so far to elucidate absorption and adsorption are experimental. However, this is important to improve our understanding of the process of uptake, transport, and toxicity assessment. The analytical challenges and technological limitations needs to be overcome. For example, issues of organic matter digestion, matrix interferences, spatial resolution under the microscope, limitations in spectral capabilities of FTIR, microraman, LDIR to identify smaller-sized particles, and of the GCMS, ICPMS to provide concentration in terms of numbers and sizes limits application to real-world environmental samples. A quantitative understanding of MNPs under real-world conditions should be used to underpin the hazard and risk assessment of these particles to human and non-human biota. Nevertheless, the accurate quantification and visualization of MPs and NPs in higher plants remains an extensive challenge that remains sparingly explored at this point. The majority of the experimental studies have used polystyrene nanoparticles in a hydroponic medium. Plants grow in a complex environmental matrix and are often exposed to various types of MNPs. Experimental studies on other types of MNPs are extremely challenging, yet desirable. Characterization of MNPs absorbed from natural soil or atmosphere is difficult. To date, studies isolating and characterizing MNPs from natural environments have been negligible. Adsorption and absorption of MPs and NPs in crops. Species, polymer type, absorption, references, bin, 100 PS beads, root tip cells, L. 2019, wheat and sativa lettuce, 202 PS and 202 beads, PMMA. Root steel shoots, Lee L. 2020, wheat, 100 PS beads, root and shoot xylem leaf veins, L. 2021, cucumber, 100-700 PS. Not studied, Lee L. 2021, cress, 50-500-4800 PS MNPs. Bosker L. 2019, sativa lettuce, PS NPs. Absorption of NPs through stomata and translocation to roots. L. 2021, maize, carboxyl-modified PSNPs and amino-modified PSNPs. Absorption via the stomatal opening. Sun L. 2021, wheat and maize. Polypropylene particles, PP. Accumulation in roots of wheat and stem of maize plant. L. 2023, Italian lettuce, radish, wheat, and corn. PSNPs 100 and PSNPs 5. Absorption in roots. Gong L. 2021, citrus root stalks. PSNPs 20 and 50. In root stalks. L. 2025, barley, wheat, carrot, sativa lettuce. PSNPs 500. MPs affecting lettuce and carrot. L. 2023, wheat, PSNPs 200. Wheat root xylem cell wall and in the xylem vessel to the shoots. Lee L. 2023 Bay. Peanut, sativa, rice. PSNPs 80. PSNP translocation from the root and accumulation in the grains at the maturation stage. L. 2022 J. Solanum, tomato. PSSO3H, PS, FPSSO3H green, FPSNH2 green, and PSNPs. Tomato leaves. L. 2023. Sativa rice. PSNPs 80 and PSNPs 1. Root steel stem vascular bundles and leaf veins, and mostly aggregated on cell walls and in the intercellular regions. L. 2022. Sativa rice. PSCOOH and PSNH2. Absorption of PSCOOH, and PSNH2 in rice roots was confirmed by confocal microscope. L. 2022. Strawberry. PSNPs 100-200. PSNPs entered the roots and further translocated to the vascular bundles of petioles. L. 2023. PSNPs 20. PSNPs entered the roots and moved to the aerial parts. L. 2022. Maize and glycine max, soybean. PSNPs 80 and 500. Larger sized remained on the leaf epidermis, whereas a few particles were present in the cytoplasm, or 80 migrated to the maize leaf interior and soybean leaves. L. 2023. Cotton. Red fluorescent PSCOOH, al. 2023, Li al. 2019-2024, and non-fluorescent PSCOOH with a particle size of 120. PSCOOH invaded cotton roots. Li al. 2024. Lettuce. Green polystyrene microplastic microbeads with 200 diameter, 488, 525. Roots. Su al. 2022. And lettuce sativa. PSNPs 200. Accumulation in roots, limited translocation in shoots. Luo al. 2022. Sweet potato. PE spheres 5. PE and P fluorescent spheres were only observed in cortical tissues of roots and stems. L. 2022. Maize. Small polystyrene PS beads 0.2, 0.5 and 1 and large PS beads 2 and 5. More PS beads were absorbed by the root maturation zone than by the root tip zone. Li al. 2023. Cucumber. Polystyrene PS and polymethyl methacrylate PMMA nanoplastics 100. Uptake by roots and their translocation to other tissues. Li al. 2021 b. Cowpea flowering cabbage, rutabagas and qua. Poly-PVC, polyethylene terephthalate, PET, polyethylene PA and PA66. Stems, leaves in flowering cabbage samples and peas and pods in cowpea samples. Yi al. 2024. Allium cepa onion. Red polystyrene microspheres 50. PS spheres were internalized in different compartments of root tissue. Al. 2020. Sativa. 100 and 500 PSNPs. Absorption by roots and translocation to stems and leaves. Al. 2024. Carrot. 100 and 200 PSNPs. Absorption by roots and translocation to aerial parts. Dong al. 2021. Maize. PET and PSNP oligomers. Absorption of the proactively exposed or European plastic particles by maize L leaves through stomatal pathways, as well as their translocation to the vascular tissue through the pathway, and accumulation in trichomes was identified. Li al. 2025. Taro. PSNPs 50 and 100, PSNPs 200 and 500. PS particles of diverse sizes displayed differential root adsorption and penetration, with PSNPs capable of penetrating the root epidermis, whilst PSNPs were wholly excluded. Su al. 2025. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: OS Al 2018, Microplastics and Nanoplastics in Aquatic Environments, Aggregation, Deposition, and Enhanced Contaminant Transport. Environ Technol 52-4-1704-1724 PubMed. Al 2021, Uptake and Accumulation of Nano-Microplastics in Plants, a Critical Review. Nano 11-11-2935. VU 2012, Independent endocytosis contributes to uptake of glucose into BY2 protoplasts. Plant J74 578-584 PubMed. Al 2012, Uptake of fluorescent nanobeads into BY2 cells involves dependent and independent endocytosis. FEBS 586-236-263632 PubMed. J. Pilling D. 2019, The State of the World's Biodiversity for Food and Agriculture. FAO. Bosker T. al. 2019, Microplastics accumulate on pores in seed capsule and delay germination and root growth of the terrestrial vascular plant. Chemosphere 226, 774, 781 PubMed. Cole M. al. 2014, Isolation of microplastics in biota-rich seawater samples and marine organisms. Rep 41452, 8 PubMed Central. Zial 2023, Micro-Nano-plastics uptake, toxicity and detoxification in plants, challenges and prospects. Environ 268 115676 PubMed. Del Real AEP, al. 2022, Assessing Implications of Nanoplastics Exposure to Plants with Advanced Techniques. J. Hazard Mater 431-28356 PubMed. Dongwei al. 2021, Uptake of Microplastics by Carrots in Presence of as III, Combined Toxic Effects. J. Hazard Mater 411-125055 PubMed. al. 2023, Combined Approaches for Detecting Polypropylene Microplastics in Crop Plants. J. Environ 340-7119258. E. al. 2006, Fluid Phase Uptake of Artificial Nanospheres and Fluorescent Quantum Dots by Sycamore Cultured Cells, Evidence for the Distribution of Solutes to Different Intracellular Compartments. Plant Signal 14196-200 PubMed Central. L. al. 2020, Exploring the Interaction between Polystyrene Nanoplastics and Allium cepa during germination, Internalization in Root Cells, Induction of Toxicity and Oxidative Stress. Plant 149-17177, PubMed. Gong W. al. 2021, Species-Dependent Response of Food Crops to Polystyrene Nanoplastics and Microplastics. Total Environ 796, 148750 PubMed. P. al. 2008, Nanoparticles as Smart Treatment Delivery Systems in Plants, Assessment of Different Techniques of Microscopy for Their Visualization in Plant Tissues. Bot 101, 1187, 195 PubMed. S. al. 2023, Foliar Uptake and In-Leaf Translocation of Micro-Nano-plastics and Their Interaction with Wax. Environ Nano 10-4, 1126, 1137. N. al. 2022, Microplastics in the Atmosphere, a Review. J. Environ Expo Assess 116. NB al. 2019, Are We Speaking the Same Language? Recommendations for a Definition and Categorization Framework for Plastic Debris. ACS Publications. AA al. 2017, Microplastics in and Terrestrial Environments, Evaluating the Current Understanding to Identify the Knowledge Gaps and Future Research Priorities. Total Environ 586, 127, 141 PubMed. Z. al. 2023, The Review of Nanoplastics in Plants, Detection, Analysis, Uptake, Migration, and Risk. AC Trends Annal 158-116889. Z. al. 2024, Internalization, Physiological Responses and Molecular Mechanisms of Lettuce to Polystyrene Microplastics of Different Sizes, Validation of Simulated Culture. J. Hazard Mater 462-132710 PubMed. XF al. 2014, Rhizosphere Interactions, Root Exudates, Microbes and Microbial Communities. Botany 92-42-67-275. Hurley RR al. 2018, Validation of a Method for Extracting Microplastics from Complex Organic-Rich Environmental Matrices. Environ Technol 5213-7409-7417 PubMed. K. al. 2025, Impact of Polystyrene Nanoplastics on Physiology, Nutrient Uptake, and Root System Architecture of Grown Citrus Plants. Nano Impact 30-7100-536 PubMed. B. al. 2023, Impacts of Soil Microplastics on Crops, a Review. Soil 180-110-4680. B. A. 2024, Microplastic and Nanoplastic in Crops, possible adverse effects to crop production and contaminant transfer in the food chain. Plants 13-17-2526 PubMed Central. Ex al. 2019, and of polystyrene microplastics on higher plant. Environ 258-31-838 PubMed. M. al. 2022, Evidence and Impacts of Nanoplastic Accumulation on Crop Grains. Adv. 933-2-202336. CK al. 2014, Increasing Homogeneity in Global Food Supplies and the Implications for Food Security. Proc. Acad. 111-400-14006 PubMed Central. CK al. 2022, The Plants That Feed the World, Baseline Data and Metrics to Inform Strategies for the Conservation and Use of Plant Genetic Resources for Food and Agriculture. Food and Agriculture Org. CK al. 2022b, Crop Genetic Erosion, Understanding and Responding to Loss of Crop Diversity. New 233-184-118 PubMed. D. al. 2022, Translocation and Chronic Effects of Microplastics on Pea Plants in Copper-Contaminated Soil. J. Hazard Mater 436-129-194 PubMed. Lee L. al. 2019, Uptake and Accumulation of Microplastics in an Edible Plant. Chin Bull 6499-28934. Lee L. al. 2020, Effective Uptake of Plastics by Crop Plants via Crack-Entry Mode. Sustain 3-11-9-29-937. Lee Z. al. 2021, The Distribution and Impact of Polystyrene Nanoplastics on Cucumber Plants. Environ Raise 28-160-4216053. Lee C. al. 2021 b. Quantification of nanoplastic uptake in cucumber plants by pyrolysis gas chromatography mass spectrometry. Environ Technol 88633-638. Lee H. al. 2023, Uptake and Distribution of Microplastics of Different Particle Sizes in Maize Seedling Roots. Chemosphere 313-13749-1 PubMed. Lee R. al. 2023, b. Visual Tracking of Label-Free Microplastics in Wheat Seedlings and Their Effects on Crop Growth and Physiology. J. Hazard Mater 456-13-1675 PubMed. Lee W. al. 2024, Uptake and Effect of Carboxyl-Modified Polystyrene Microplastics on Cotton Plants. J. Hazard Mater 466-1335-81 PubMed. Lee Y. al. 2025, Leaf Absorption Contributes to Accumulation of Microplastics in Plants. Nature 640-118. J. al. 2021, Foliar-Plied Polystyrene Nanoplastics, PSNPs Reduce the Growth and Nutritional Quality of Lettuce, Sativa L. Environ 280-11697-8 PubMed. B. al. 2024, Uptake of Microplastics and Impacts on Plant Traits of Savoy Cabbage. Environ 272-11608-6 PubMed. Y. al. 2022, Uptake and Translocation of Nanomicroplastics by Rice Seedlings, Evidence from a Hydroponic Experiment. J. Hazard Mater 421-126700 PubMed. MGJ al. 2017, Enzymatic Purification of Microplastics in Environmental Samples. Environ Technol 51-24-14283-14292 PubMed. YM al. 2021, Microplastic Shape, Polymer Type and Concentration Affects Soil Properties and Plant Biomass. Front Plant 12616645 PubMed Central. Luo Y. al. 2022, Quantitative Tracing of Uptake and Transport of Plastics in Crop Plants using Lanthanide Chelates as a Dual Functional Tracer. 1744-24-431 PubMed. A. al. 2021, Adsorption, Uptake and Toxicity of Micro and Nanoplastics, Effects on Terrestrial Plants and Aquatic Macrophytes. Environ 284-117-183 PubMed. R. al. 2022, Microplastics in Agricultural Systems, Analytical Methodologies and Effects on Soil Quality and Crop Yield. Agriculture 12-81162. K. Al. 2011, Independent Endocytosis, Mechanisms and Function. Cell 23-4413-420 PubMed. L. Al. 2022, Impact of Polyethylene on Soil Physicochemical Properties and Characteristics of Sweet Potato Growth and Polyethylene Absorption. Chemosphere 302-134734 PubMed. R. Al. 2023, Toxicity Mechanisms of Nanoplastics on Crop Growth, Interference of Microbes, and Evidence for Foliar Penetration and Translocation. Environ Technol 5821010102-1 PubMed. X. Al. 2024, Impact of Microplastics on Plant Physiology, a meta-analysis of dose, particle size, and crop type interactions in agricultural ecosystems. Total Environ 955-177245 PubMed. Sun XD Al. 2020, Differentially Charged Nanoplastics Demonstrate Distinct Accumulation in 15.9.755.760 PubMed. Sun H. Al. 2021, Foliar Uptake and Leaf-to-Root Translocation of Nanoplastics with Different Coating Charge in Maize Plants. J. Hazard Mater 416-125854 PubMed. Taylor S.E. Al. 2020, Polystyrene nano and microplastic accumulation at and wheat root cap cells, but no evidence for uptake into roots. Environ Nano 7719421953. S. Al. 2022, Micronanoplastic in the Aquatic Environment, Problems and Challenges. Animals 123297, PubMed Central. J. Al. 2022, Effects of Polystyrene Nanoplastics with Different Functional Groups on Rice, Sativa L. Seedlings, Combined Transcriptome, Enzymology and Physiology. Total Environ 834-155092 PubMed. Suzy Al. 2022, Toxic effects of microplastics in plants depend more by their surface functional groups than just accumulation contents. Total Environ 833-155097 PubMed. Suji Al. 2025, When nano and microplastics meet taro roots, their size-dependent adsorption, penetration, and promotion on secondary wall reinforcement. Environ Technol 59-8345 PubMed. EQ Al. 2024, Identification and Quantification of Nanoplastics in Different Crops using Pyrolysis Gas Chromatography Mass Spectrometry. Chemosphere 354-141689 PubMed. Z. Al. 2024, Uptake and Transport of Micro-Nanoplastics in Terrestrial Plants, Detection, Mechanisms, and Influencing Factors. Total Environ 907-16815 PubMed. LJ Al. 2023, Species-Dependent Responses of Crop Plants to Polystyrene Microplastics. Environs 335-1222-43 PubMed. C. Al. 2023, Potential Translocation Process and Effects of Polystyrene Microplastics on Strawberry Seedlings. J. Hazard Mater 449-1310-19 PubMed. 3. Sample collection, preparation, and identification of microplastics in soil, issues and recommendations. Abstract. The omnipresence of microplastics (MPs) in agricultural soils, driven by practices such as compost and fertilizer addition, sewage sludge application, plastic mulching, and irrigation, is the main input of MPs to soil and poses significant risks to soil health and food safety. The paper evaluates methodologies from 39 global studies to identify gaps and inconsistencies in MP sampling, preparation, and identification protocols. Key findings reveal diverse sampling strategies, with composite sampling across depths 0-30 and grid quadrant approaches recommended to account for soil heterogeneity. Pretreatment methods, including organic matter removal via 30% H2O2 or enzymatic digestion, and density separation using Na or Ni, vary widely, impacting MP recovery rates. Identification techniques predominantly combine microscopy with spectroscopic methods, FTIR, Raman, though challenges persist in false positives, polymer degradation, and nanoparticle detection. Disparities in reporting units, IG. MP versus hinder data comparability, complicating risk assessments and policy formulation. Quality assurance measures such as procedural blanks, contamination controls, and spiked recoveries are inconsistently applied, underscoring the need for standardized protocols. Recommendations: harmonized sampling designs, extraction workflows, and integration of advanced techniques like laser direct infrared spectroscopy for accurate quantification. Establishing global standards is imperative to generate reliable datasets, inform regulatory frameworks, and mitigate agricultural plastic pollution effectively. Keywords. 3.1 Introduction. The ubiquitous presence of microplastics in agricultural soils as a result of the use of sewage sludge, sludge-based fertilizers, composts, plastic mulch films, and for irrigation has emerged as a critical environmental concern for both soil health and food safety. For assessing the risks and generating data across regions, harmonized and standardized methodologies are needed. Some efforts have been made. AL. 2024, AL. 2020 to harmonize methodologies for sampling, extraction, identification, and quantification that are essential to assess the level of microplastic contamination and ecological risks. Robust, harmonized methods for soil MP analysis are vital to enable cross-national data comparability and track progress toward environmental targets. AL. 2019 emphasized the need to standardize protocols so countries can generate consistent and reliable data to map plastic contamination trends, inform policy decisions, and accelerate global mitigation efforts to reduce plastic pollution. The global efforts to establish the legally binding plastic treaty underscore the need for standardized monitoring and reporting frameworks, UNEP 2025, as emphasized at the 5 United Nations Environment Assembly with the establishment of the Intergovernmental Negotiating Committee, INC. The first part, INC 5.1, of the 5th session took place from 25 November to 1 December 2024 in Republic of Korea. The second part, INC 5.2, took place from 5 to 14 August 2025 in Geneva, Switzerland. In this chapter, we have attempted to critically evaluate the methods employed by various workers. 39 studies have been highlighted to identify the differences and data quality objectives. 3.2 Sample collection. Soil being a heterogeneous matrix requires appropriate considerations to select a representative site for microplastic determination. However, the criteria for sample site selection needs to be aligned with the research objectives. AL. 2024, AL. 2020 B 2021-2023, AL. 2020 and 2024. Selecting an appropriate site for soil sampling requires a comprehensive assessment of the area's historical use, particularly practices like agricultural plastic mulching, municipal waste disposal, and irrigation with treated, as these directly influence MP presence. For a realistic assessment, both sources and dispersed origins should be evaluated. On large spatial scales, the topography, soil type, and land use land cover are important considerations. The time of sample collection is also a critical factor. Heavy rainfall can wash out the lighter MPs into the waterways. AL. 2022. In agricultural soils where plastic mulch, sewage sludge, or compost is applied, sampling should be done before the next planting season. If the edge effect and carryover are not the objective of the study, samples should be taken centrally within fields. AL. 2018, whereas others have suggested that samples be taken on all 4 corners and from the center of a quadrant to make a composite sample. Yang AL. 2021 AL. 2021. The ISO 18401/02 is designed for soil sampling ISO 2017 and is applicable for MPs, employing random, stratified, or targeted approaches based on research goals. AL. 2020. 321 Sampling design. Based on the review of the sampling strategies used in the studies, it is observed that most of the studies adopted a grid-based sampling strategy or a quadrant system to ensure collection of a representative sample. Summary of the methodology adapted for microplastics in soil by different workers. Country region. Sampling. Sludge samples. Sample extraction. Identification. Units reported. Quality control. Matrix. Sampling depth. Pretreatment. Matrix. Treatment. Predigestion. Flotation. Filtration. Post-oxidation. Reference. Nanjing and region, China. Soil samples. Soil was collected from agricultural lands with no history of sludge application and treated use. Surface soils were collected using a stainless steel shovel. Samples were air-dried and sieved through 5mm stainless steel sieves. Microplastics larger than 1 were manually removed from the sieve. Collected from 3 WWTPs. Samples were air-dried and sieved through 5mm stainless steel sieves. Microplastics larger than 1 were manually removed from the sieve. 30% H2O2 at 70 C to remove organic matter ohm. Samples heated until nearly dry. Solutions tested. Na 1.2 G3 to 1.5 G3, Na 1.8 G3. Shaken for 1 initial and 30 min repeat, settled for 48. Supernatant siphoned and combined. Vacuum filtration using 20-pore size nylon membrane filter. PTFE and glass fiber membranes were avoided due to shedding. MPs washed with 30% H2O2 plus H2SO4 31VV at 70 C to remove residual ohm. Stereo microscope. Observed shape fiber fragment bulk color and size 0.025 m. Image array is used for size classification. FTIR microfourier transform infrared spectroscopy. ATR mode for 1 resolution, 32 scans. Spectra were compared with those in the polymer and additives databases. 3 random 2 areas were analyzed per membrane. MP abundance, items soil or sludge. Contamination prevention. Glassware only, rinsed with water. Researchers wore cotton lab coats. Flasks covered with aluminum foil during flotation. Membrane selection. Tested quartz, glass fiber, PTFE, and nylon membranes. Selected nylon to avoid fiber shedding. Replicates 3 parallels per treatment. Oxidation validation. Tested virgin polymers PE, PP, PS, PA, ABS, PET to ensure no degradation during oxidation. FTIR verification. Non-plastic particles e.g. black carbon were excluded via spectral analysis. Li al. 2019. Shanghai, China. 20 vegetable farmlands were samples. GPS coordinates recorded for each site. 0.3 shallow layer and 3.6 deeper layers, measured with calipers. 1 of soil per sample, visible debris 5 removed. Stored in aluminum boxes to avoid plastic contamination. Dried soil at 70 C for 24 hours. Density separation using Na 1.19 G3 and for 2 minutes. Stirred for 30 minutes, settled for 24 hours. Filtered through 20 nylon membrane filter. Repeated 3 times for complete extraction. Treated supernatant with 30% H2O2 at 50 C for 72 hours. Visual classification using stereo microscope, SMZ25 for shape, fiber, fragment, film, pellet, and color. Size categories, microplastics 5 m, mesoplastics 5 m 2. Polymers identified using FTIR. In transmittance mode, 4675-1, 32 scans. Spectra were matched to polymer database, 70% match threshold. 99 randomly selected particles were analyzed. Microplastic mesoplastic abundance in items 1 of dry soil. Recovery test samples were spiked with PP, PE, PA, PET, PVC, PC, ABS, PMMA, and PS microplastics. Recovery rates were 90% for PP, PE, PA, PC, ABS, PMMA, and PS. PET and PVC not recovered due to its density higher than Na. Glass metal equipment rinsed with Q water. No plastic containers used. Researchers wore cotton lab coats and gloves. Samples stored in closed containers to avoid airborne contamination. Triplicate blank tests confirmed no microplastics in controls. 2018. And a buffer zone, China. 5 agricultural soils in the lake basin. Collected 6 subsamples per plot using a narrow spade from 2 depths. 0.5 and 5.10. Composite samples were sieved through a 10 mesh. Air-dried at 25 C, roots and large debris removed. Composite agricultural soil. Wet sieving of air-dried soil through 0.25 and 0.05 m sieves. After that, the samples were centrifuged for 10 minutes at 2300 rpm to separate aggregates. The 2 were considered as large macroaggregates, 0.252 m as small macroaggregates, 0.05025 m as microaggregates. Samples treated with 35% H2O2 and 10% SO4 at 50 C to remove organic matter. Saturated Na with a density of 1.8 G3 solution for density separation. Supernatant filtered through stainless steel meshes, 0.25, 0.05. Visual classification using dissection microscope at 40 categorized into size range of 10.1, 1025 m, 0.25005 and shapes were identified as fiber, fragment, and film, while pellets and foams were excluded. No polymeric as done. And 2018. Xinjiang, China. Quadrat sampling. Composite samples from a quadrat measuring 200-130 depth from 593 sites were collected. Soil samples were manually collected from the top 30. A questionnaire was sent to 672 farmers. 593 responded giving information of crop type, mulch film thickness, mulching years, etc. Ultrasonic cleaning to remove soil particles. Blotting paper is used to absorb moisture. The samples were then air-dried and weighed. Visual identification was done and no spectroscopic methods were used. The results were reported as film abundance in Ha1 for individual sites and in metric tons for the regional total. Large sample size to reduce bias. Ultrasonic cleaning to ensure accurate weight measurements. Compared results with national standards, GBT 25413-2010. But no mention of procedural blanks or contamination controls during lab analysis. And potential self-reporting bias in questionnaire data. 2016. Szeged, Hungary. Soil samples from greenhouse and farmlands. The area was divided into 15 areas of 52.9 m and 3 areas were randomly selected for sampling. Soil samples were collected from 2 depths, i.e. 0.20 and 2040, using metallic auger. Soil samples were oven-dried, homogenized, sieved, and composite samples were used. Visible debris on the surface was hand-picked by 2 observers. The collected plastics were precleaned and stored in large bags. Organic matter was digested using 30% H2O2 and reagent. 2 was used for density separation. Extracts were filtered through nylon and filters, dried. Materials were soaked in tap water for 48 hours, washed, sieved, dried, separated, counted, and measured. Microscopic examination of filters. Suspected microplastic particles were confirmed using the hot needle and Raman spectroscopic analysis. Were reported in Ha1 and categorized by size 0.510, 15, 510, 10, 15, 15. Microplastics were reported as MP1. Cleaning the auger before each sampling, avoiding sample mix, and using minimal plastic materials. Rinsing laboratory apparatus with distilled water 3 times, wearing cotton lab coats and gloves, and covering samples with aluminum foil to prevent contamination. And 2022. Shenyang Agricultural University, China. Arable land. Soil cores were taken from random locations in each plot using a coring drill of 8.5 diameter from 0-10, 10-20, 20-40, 40-60, 60-80, and 80-100. Soil samples were sieved through a 5-metal mesh to remove residues and roots, and air-dried. 20 g of air-dried soil samples was mixed with density separation solution, sonicated, filtered, and treated with 30% H2O2 solution, heated and filtered again. 2 solution was used for density separation. The supernatant was filtered through a membrane filter, dried. Stereo microscope used for identification. The polymeric was done using FTIR. Microplastics were classified into films, fibers, and granules. Size and color were also reported. MPM2 for an MP1 of soil for microplastics. Soil stored in cotton bags. Metal and glass was used and washed with pure water and covered with aluminum foil. All the solutions were filtered and cotton lab coats were worn. 3 replicates without soil were run concurrently to check for potential plastic contamination during extraction. No plastics were detected in these blank control samples. Positive control samples were used to test the efficiency of the extraction method, achieving recovery rates of 87% 3% for film microplastic and 90% 7% for fiber microplastic. Li al. 2022. China. Experimental soil where PS was added. Seeds were placed in sterilized beakers with PSMP solutions and grown in a climate-controlled atmosphere for 14 days at 25.1°C and 75% humidity. Transmission electron microscopy (TEM) and scanning electron microscopy (SEM) were used to observe PSMP distribution in rice seeds, roots, and buds. L1. Samples were fixed, rinsed, dried, and coated for SEM observation. TEM samples were embedded, sliced, and dispersed on copper mesh. L. 2021. Changsha, China. Agricultural soil. 020. The soil was air-dried, debris removed and passed through a 10 steel sieve, and stored in dark conditions. Yisheng Al. 2021. Prefecture, Japan. 19 paddy fields in the river alluvial fan, 5 points per field, 4 corners and center, using a 15 diameter core sampler. 015 divided into 2 layers, 010 and 1015. 1 soil sample was also taken from the center for chemical analysis. The soil samples were dried at 60 C for 2 days. Wet sieving was performed by mixing with tap water, stirring, settling overnight, sieved using 1 mesh. Sieved through 1 sieve. Visual sorting of microcapsules based on the criteria. 2 thrame. And color white-yellow discoloration, spherical hollow capsules. SEM used for analyses of surface morphology of microcapsules. FTIR for polymer identification. Reported in soil and GM2. The results were also reported as pieces soil and pieces M2. 2 additional individuals, visual sorting to minimize errors. Spiked samples were used, and 85-95 recovery. L. 2021. Tainan City, Taiwan. 5 farmlands a with different crops and mulch. Each farm is divided into 3 subplots, composite samples collected from 5 subsamples per subplot. 0.5 top layer and 2025 bottom layer. Air-dried, homogenized, and sieved using 1 and 5 stainless steel sieves. 30% H2O2 used overnight to degrade organic material. Na solution stirred, settled for 2 hours and filtered through 1 glass microfiber filters. Stereo microscope used to classify MPs by shape, fibers, fragments, films, foams, pellets, microbeads, and color. ATR-FTIR used for polymeric identification. MPM2. Control farm as a background control. Control soil sample ignited at 500 C to remove impurities tested for contamination during transportation. Spiked samples were also analyzed. L. 2021. Regions Tamil, India. Agricultural soils from areas that have been mulched for 10 years. 10, 11, 20, and 2130. A stainless steel probe was used to collect 15 soil cores, composited. Control samples virgin soil, taken 500 m away. The equipment was cleaned with 70% ethanol. Samples were air-dried, powdered, and stored at 4C. Soil sieved using stainless steel sieves, pore sizes, 5 to 1. Digested with 30% H2O2 at 50 C for 72 hours. Floating organic matter separated via saturated Na solution. Filtered, dried, and plastic weight calculated as WW1, W2, initial and final filter weights. Stereomicroscopy, shapes identified as films, fibers. Further identification of surface morphology and elemental composition was done using semi-DX. G1 soil and also MP soil. Glass containers, nitrile gloves, and cotton lab coats were used. Virgin soil samples for baseline comparison. 5 replicates for enzyme activity assays. The equipment was sterilized with 70% ethanol between samples. And 2021. City, South Korea. 100 sites covering forest N8, traffic roadside N19, residential N5, and agricultural N68 areas. Subdivided into orchard, paddy field, upland, and greenhouse. Systematic 2.5 grid. 05. Hand auger used to collect 3 replicates per site. Samples stored in stainless steel containers. Oven dried at 60 C for 48 hours. Mesoplastics separated using a 5M sieve. Treated with SO4, H2SO4, and H2O2, heated at 75 C for 24 hours. Microplastics 5M extracted using 2 solution 1.7 G3, stirred, settled, and repeated thrice. Filtered through 0.45 cellulose acetate membranes. Digital stereo microscope used to count and classify by shape, fragment, film, fiber, sphere, and color, black, red, green, etc. Polymers identified using FTIR by matching spectra to reference databases. MP1 soil categorized by size, 1, 5, 5, and polymer types reported as percentages, e.g. SBR 43%, PP 22%. Stainless steel tools and containers used. Triplicate samples per site. FTIR analysis on 60 representative samples to confirm polymer composition. L. 2021. Swiss floodplain, Switzerland. Remote high mountain soil and from populated regions. Collected from topsoil layers, depth unspecified, using standardized soil sampling protocols. Mixed samples from each site were analyzed, 3 replicates per site. Custom-built setup involving a vacuum pump, magnetic mixer, and aeration system. Tested HNO3 90C 48H for organic matter digestion. Combined with centrifugation, rubber discs are used to prevent resuspension of mineral particles. Particles filtered through membranes, 0.45 porosity. Polymer identification using Raman spectroscopy, e.g. PP, PI, PVC, PET. FTIR validation. MP1 of soil and categorized by size as small microplastics, 1 m, large microplastics, 1 5 m. Mesoplastics, 5 m. Filter to rule out contamination. Recovery tests were conducted. Triplicate samples per site. Chemical resistance testing after HNO3 treatment. Negative controls. And 2018. Switzerland. 11 agricultural drainage sites, 8 passive flow systems, 3 basin systems. Flowing water was directly collected into 3L pre-cleaned glass containers. Basin water was sampled with a pre-cleaned metal bucket, transferred to glass containers. 5 sites sampled to assess variability. Backwashed with 15 ml 60% H2SO4 for 30 minutes. filtered through 8 cellulose nitrate membrane filters. Centrifugation 3000 rpm 30 min to isolate MP. Supernatant filtered through 0.2 filters for FTIR analysis. FTIR spectroscopy, particles 100 analyzed. MPL1 with mean standard deviation. Process 2.5 LQ water as a blank with mean blank 0.8 MPL1. Detection limit, mean blank plus 3 SD22 particles L1. Recovery test with 100% recovery of spiked PA, PP, and PVC particles, 1 tum. 1 sample in triplicate, 1 in duplicate, mean RSD 54%. Temporal replicates, same site, different dates, mean RSD 72%. For minimizing contamination, lab equipment rinsed with Q and ethanol, sample preparation under HEPA filtered laminar flow hood. L. 2022. Germany. Experimental agricultural farms where 190 t of sludge per hectare was applied. MPG1. L. 2022. Ilia County, Greece. Agricultural fields and 5 uncultivated blank samples. 030 using stainless steel shovel. Air-dried, sieved through 5 mesh, stored in aluminum containers. Treated with 30% H2O2 at 70 C for 2 days to remove organic matter. Saturated Na 1.18 G3, mixed with 150 G soil, stirred, rested, and filtered through 520 sieves. Repeated until no floating material. Stereo microscope to identify 25 m. ETR-FTIR to identify polymer type. SEM for analyzing surface degradation of MPs. MP1 classified into 2 classes. 20 to 500. 500 to 5 m. Blank samples. Triplicates for each sample. Stainless steel tools, aluminum containers, visual exclusion of non-BMF MPs. To avoid contamination. L. 2021. Murcia, Spain. 3 fields sampled that had a long-term use of LDPE, PAC, and biodegradable mulch over 12 years. 010 and 1030 depths. 10G soil or 5G compost mixed with water, centrifuged 3000 rpm 10 min, filtered through 2.5 filter. Treated with H2O2 and heated 130 C to differentiate MPs from organics. Visual examination using a stereo microscope. Particles are classified by shape, color, and heat response. ImageJ software is used to quantify particle count and size 30 tum. FTIR spectroscopy to identify polymers. MP1 and M2 1 particle area. Filed blank samples, 3 replicates per sample. Instrument validation. Detects only light density MPs 30. Potential underestimation of non-floating plastics. Van Al. 2021. Netherlands. 2 farms with loamy sand, 7 years of compost, clay 20 years of compost. Each farm had 3 fields, 5 points per field. 010 and 1030 depths. Municipal organic waste and garden greenhouse waste. 10G soil or 5G compost mixed with water, centrifuged 3000 rpm 10 min, filtered through 2.5 filter. Treated with H2O2 and heated 130 C to differentiate MPs from organics. Visual examination using a stereo microscope. Particles are classified by shape, color, and heat response. ImageJ software is used to quantify particle count and size 30 tum. FTIR spectroscopy to identify polymers. MP1 and M2 1 particle area. Filed blank samples, 3 replicates per sample. Instrument validation. Detects only light density MPs 30. Potential underestimation of non-floating plastics. Van Al. 2021. Switzerland. Processed organic waste from municipalities, gardens, and households. Samples at 3 stages: incoming organic waste, conveyor belt, sieving residues, and final solid. Sampling was conducted over 5 days, June-August 2017. 15 samples total, 4.5 L each, collected every 40 minutes over 2 hours. Bulk density measured for compost and samples. Washed samples under running water over a 6 mesh to separate plastics. Dried retained material at 40 C for 4 days. Visually inspected dried samples to collect plastic pieces 1. Microscopic examination and classification into plastic bags, packaging materials, etc. FTIR spectroscopy for identification of polymers. Tons 1 for material flow analysis. Plastic concentrations as a percentage of wet organic waste in percent and total accumulation in Swiss soils reported in tons. Monte Carlo iterations to quantify variability and uncertainty in plastic content. L. 2021. Tanzania. Soils from irrigated farms. ETR-FTIR. L. 2022. Mauritius. Agricultural soils collected from 3 sites. 010 and 1020. Each site is divided into a 2020 M. 40 samples per grid composited into a single sample. Samples were dried, sieved, and analyzed. Grab sampling from 3 WWTPs. Sludge 1L was collected after primary-secondary treatment. 500 ml was collected before discharge. Samples were stored in glass bottles. Sludge samples were mixed with water, centrifuged, and digested with H2O2. The effluents were directly mixed with H2O2, digested and filtered. H2O2 digestion, 7 days to remove organic matter. Flotation with distilled water and Na 1.19 G3, followed by centrifugation. Filtered through 0.45 cellulose nitrate membranes. Microscopic examination to categorize MPs by shape, fiber, fragments, flakes, films, spheres, color, and size, 0.255. ETR-FTIR for polymer identification of particles, 0.5. MP1 for soil. MPL1 for effluent. MP1 wet weight for sludge. Spiked samples with known plastics to calculate recovery rates, 3 replicates. Blank samples analyzed. Lab equipment rinsed with ethanol, use of gloves and aluminum foil used to cover glassware. L. 2021. Tunisia. 4 agriculture soils with organic farming control mulched, soil irrigated with treated. 1020 depth. Earthworms were exposed to soil spiked with MPs 100 for 7 and 14 days. MPs and earthworms were digested using 10% KOH. Density separation using saturated Na 1.19. The earthworm samples were density separated by Ki. Sieved through 300 mesh to retain particles, 1/300. Earthworm samples were filtered through 0.223 cellulose nitrate filters. Microscopic for color shape. FTIR and Raman microspectroscopy for polymer identification. MP1 in soil. MPG1 tissue for earthworm. Rinsing equipment with mildew water. Blank samples. 10 replicates. L. 2021. Chile. Agricultural soil with varying degrees of sludge application histories. 0.5 applications over 10 years, from 31 fields and a control site, no sludge applied. 0.25 sampled with a metallic auger, 3 replicates per field. Dried at 40 C, sieved with Tomb sieve and stored in PET jars. 7 samples collected from fields undergoing sludge applications during the study. Dried milled sieved 1 and stored in PET jars. Sequential use of Na 5M 120G3 and 2 5M 155G3 solutions to float microplastics. 5G of soil and 1G of sludge is mixed with deionized water, stirred, centrifuged, and filtered. Supernatants filtered through No. 42 filters, retention 8. Microscopic visual identification, and classified into fibers, fragments, films, or pellets based on morphology. No spectroscopic confirmation was done. MPG1 in soil sludge, DW. MP weight estimated using particle dimensions and assumed polymer densities. Reagent blanks were included in each batch to detect lab contamination. Ignited soil samples tested for transport, storage, contamination, and recovery test. 5 samples were analyzed 5 times, the coefficient of variation 12%. L. 2019. Ontario, Canada. Soil from 4 agricultural fields, 3 treated, 1 control. 05, 510, and 1015, using a stainless steel core 5 diameter. Soil cores wrapped in aluminum foil, frozen, then oven-dried 65°C, biosolids refrigerated before drying. Collected directly from application trucks hoses during spreading. Reagent used to remove organic content. Sequential use of sodium tungstate, Na2WO4, solutions to float microplastics MPs. Isolated MPs filtered onto glass fiber filters. Microscopic examination to classify MPs by shape. Polymer identification using ATR-FTIR for particles 300 and FTIR for smaller particles fibers. MP1 for soil and biosolids reported in MP1 and MPL1. Mass particle dimensions, IG. Fragment volume as ellipsoids, fiber volume as cylinders. Aluminum foil covers during drying. Spike samples PA, PVC, PET fibers showed recovery rates of 80–97%. Lab coats and controlled airflow in processing areas. Procedural blanks were analyzed to account for background contamination. Triplicate analysis of composite soil samples, standard errors reported. L. 2020. Mexico. Arable land. L. 2021. Shanxi, China. Agricultural soils. 010. 6 composite samples per site, each composed of 3 subsamples collected 3 m apart to a 2 quantity. Stored in clean metal bottles and refrigerated. The soil was oven-dried at 70°C for 24 hours. H2O2 was used for organic matter digestion. Heated at 65°C, 12 hours. 50G soil mixed with Na 1.2G3 and 2 1.5G3 solutions. The supernatant was collected after 24 hours. Filtered through 0.45 filter paper, dried and stored for analysis. Microscopic examination to identify type, size, and shape. Followed by FTIR spectroscopy for polymer identification. SEM for surface characterization. MP1. Glass metal tools used. Equipments rinsed with water and samples wrapped to avoid airborne fibers. Blank experiments confirmed no MPs in controls. Ding L. 2020. Tibetan Plateau, China. 17 farms. 03 and 36 layers. Visible debris 3 was removed. Samples were stored in aluminum foil bags. Sediment soil were oven-dried 70°C 24H, sieved tomb. Digested with 30% H2O2 and 0.05 MII, solution at 75°C for 72 hours to degrade organic matter. Density separation using saturated Na 1.2G3. Supernatants collected 3 times for thorough extraction. Filtered through 0.45 membranes. Microscopic examination to classify MPs by shape, size, and color. Raman spectroscopy for polymer composition. MP1. Tools rinsed with water, glassware heated at 400°C, laminar flow cabinets used during experiments. Triplicate Q water blanks analyzed. L. 2020. Schleswig-Holstein, Northern Germany. Farmland 15 sites. 010, 1020, and 2030. Boreholes were drilled at 4 corner points of a 40 m square per site. 540 soil samples, 36 per site, totaling 123 of soil. Stored in glass containers to avoid contamination. Soil soaked in water, homogenized and sieved through a 1 steel sieve to retain particles 1. For organic matter removal, the aggregates dissolved manually, excess water removed with syringes. Sieve material was examined under a stereo microscope for MP15 and classified by shape and color. FTIR spectroscopy for polymer composition. MP1. Glass metal tools used, lab coats worn, instruments rinsed between samples. Spiked soil samples used for recovery assessment and blank samples analyzed. Harms L. 2021. Xinjiang region, China. Agriculture fields with cotton plantation and 5, 15, and 24 years of mulching. 05-520-2040. 5-1M plots per field, triplicate soil cores at different depths and stored in aluminum bags. Digested with H2O2 density separation using Na 1.85 G3. Air-dried soil mixed with Na, agitated, settled, and supernatants collected. Flotation was repeated thrice. Filtered through 7 glass fiber filters. L. 2020. Schleswig-Holstein, northern Germany. Farmland boreholes were drilled at 4 corners of a 40 m agriculture fields. 010, 1020, and 2030. Soil soaked in water homogenized and sieved through a 1 steel sieve to retain particles 1. Organic matter removal was done by manually dissolving the aggregates and excess water removed with syringes. Sieve material was examined under a stereo microscope for MP15 and classified by shape and color. The polymers were confirmed using an FTIR spectrometer. MP1. Stored in glass containers to avoid contamination. Glass metal tools used, lab coats worn, instruments rinsed between samples. Spiked samples for recovery calculations. Blank samples were also analyzed. L. 2018. Shandong and Suzhou, Jiangsu, China. Agricultural soils. 010. Plant debris was removed, air-dried, ground, and sieved with a 1 sieve. Digestion with 30% H2O2 at 70 C to remove organic matter. Na 1.2 G3 was used for density separation. Filtration through 20 nylon membranes. Identification of polymers using laser direct infrared LDIR spectroscopy in the size range of 21000. MP1. Avoided plastic tools, cotton lab coats worn, glassware pre-washed with HNO3, acetone, or hexane. Blanks processed. Triplicate extraction. Li L. 2021. Jiangxi Province, Southeast China. Agricultural plots with long-term repeated pig manure application. 020 and 2040. Plant debris removed, samples air-dried, homogenized, and sieved, e.g. 5 or 1 30% H2O2 to degrade organic material. Na saturated solution for density separation. Filtration through a 0.45 glass fiber filter. A stereo microscope was used to count, and particle morphology and polymers were identified by using FTIR. MP1. Yang Al. 2021b. Murcia, Spain. 6 vegetable fields. 010. Each field had 3 parcels, with 3 sampling points per parcel. Sheep faces was collected. Samples were air-dried. High organic matter hindered complete particle recovery. Density separation using distilled water. Soil was shaken, centrifuged, and supernatant filtered. Ultrasonic bath used to break aggregates. Microscopic examination and images magnification. Images were taken before after heating, 130 C for 10S, to identify plastics via shape, color, brightness, and heat response. MP1. Using stainless steel tools. Blank samples reported no contamination. However, no recovery tests performed. L. 2021. In Province, Korea. Agricultural soil. MP1. L. 2021. Town City, Xinjiang, China. Agricultural soil with varying period of mulching 0, 5, 15, and 30 years. 0-20. 5 samples per site were collected using a mixed method from a 0.101 m. The samples were air-dried, sieved through meshes, tomb 0.9, 0.28, 0.15 m, and homogenized. 98% H2SO4 treatment to oxidize organic debris. Water was used to disintegrate soil aggregates and density, separated by distilled water. Vacuum filtration with quantitative filter paper. Electrostatic separation by rubbing glass rods against silk to collect small particles. SEM was used to identify MPs and ATRFTIR used for polymeric identification. 1. Recovery rates tested with spiked samples. Stainless steel glass tools, lab coats, gloves, deionized water rinsing. Soil samples processed as control and triplicate experiments for extraction efficiency. Li L. 2020. Gansu and Xinjiang, northwest China. Farmland with varying degrees of mulching. 0, 10, 10, 20, and 2030. Collected 3 quadrats, 150-30 per field divided. Microplastics Me, soil samples 1 per layer collected from pit sides, homogenized, air-dried, and sieved tomb. Extracted via flotation in distilled water, centrifugation, 14,400 G, 5 cycles. Filtration 3 filter, and thermal treatment, 130 C heating to melt LDPE particles. Microscopic identification before and after melting, smallest detected size, 0.49. MP1. Stainless steel glass tools, PP bags for storage, cotton lab coats, and gloves. Field samples were processed as control. Additionally, distilled water samples were processed as blank during MP extraction. Triplicate samples analyzed. Method restricted to low-density plastics and did not detect high-density plastics. L. 2020. City, China. Agricultural soils. 05, 510, and 1025. Samples were collected using a stainless steel shovel. Samples were sieved, 5 m, to remove stones and debris. Reagent was used for organic matter digestion under pH 3.5 and 40 C ice bath. 200 G soil was mixed with saturated Na solution 1.2 G3 and left to settle. Supernatants were collected after 24 hours. The solutions were centrifuged, and MPs were filtered onto 20 glass fiber filters. A stereo microscope was used for size, shape, and color identification. FTIR was used for polymer identification. MP1. Non-plastic tools, aluminum foil covers, cotton lab coats. Quartz sand was processed as laboratory blanks. Spiked samples were used for soil recovery rates. Triplicate samples were used for recovery estimations. L. 2021. Hangzhou Bay, China. Farm soil collected from 15 areas. 0-10. Samples were collected using a stainless shovel. Organic matter was digested with H2O2 30% at 70 C. The density separation was done using Na-16G3. Dispersed soil in sodium phosphate, followed by saturated Na solution with continuous airflow to float microplastics and filtered onto 20 glass fiber filter. Stereo microscope used to identify MPs and polymer identification using FTIR. MP1. Non-textile lab attire, glassware, and dedicated microplastic lab. Deionized water was analyzed as blank. Spiked samples were used to calculate recoveries. Duplicates were analyzed. Joe al. 2020. Spain 11 with sewage sludge applications, 5 without sampled. Agricultural soil and sewage sludge. 010 and 1030. Collected from 4 treatment plants. Samples were dried at 40 C for 72 hours. Ni was used for density solution of heavier density MPs and lighter MPs. Were using centrifuge with distilled water at 3000 RPM for 10 minutes. Filtered using 11 pore size. Microscopic examination done pre-post heating, 12130 C. MPs were identified by increased circularity, transparency, and shininess. FTIR analysis for polymer identification. MP1. Cotton lab coats, dedicated microplastic lab. Deionized water was analyzed as blank to correct the results. Spiked samples were also analyzed to assess recovery. Duplicates were also analyzed. Organic matter interference noted, no natural blank samples available. Van den Berg al. 2020. Province, China. Agricultural soils from citrus orchards. 05, 515, and 1525. Dewatered sludge from 3 treatment plants. Digestion with 30% H2O2 at 65 C for 72 hours. Density separation using 2 and Na solutions, 15 min to remove adhered particles. Filtration through 25 and 0.45 filters. Identification based on morphology and FTIR for identification of polymer. MP1. Cotton lab coats and nitrile gloves were used. Containers rinsed with water, openings covered with aluminum foil. Blank samples were analyzed as well as triplicates. L. 2020. While samples are collected, it should be kept in mind that most agricultural farms undergo tilling and furrowing that often disturbs the topsoil, and the presence of MPs might not solely be due to vertical migration. 322 Soil collection. Most of the studies utilized a quadrant-based sampling approach, usually sampling the surface layer 010 using metal or stainless steel spoons, shovels, or scoops. Al. 2024 Al. 2019 Al. 2020 Ding Al. 2020 He Al. 2021 Bello Al. 2025. However, to collect a deeper soil profile, 30 or more, sediment corers, augers, or samplers are usually used. Al. 2020 Weber Al. 2021. Most researchers have excluded plastic components to prevent cross-contamination, which is essential, so samples should be stored in metal or glass containers. Depending on the tools, like augers may necessitate combining multiple cores from adjacent sites to make a composite sample, as larger sample size is needed for representative samples for MP in soils. Alternatively, larger pile-driving probes can be used, though they will be expensive. Weber Al. 2022. In most studies, the surface microplastic concentration is higher than the deeper layer. Al. 2018 reported 78-1291 MP1 in surface soil and 62.5-1297 items 1 in the deeper layer. However, it should be considered that agricultural soils are often tilled, so the top layer is most likely not undisturbed. Van den Berg Al. 2020. On the other hand, coastal or floodplain soils are usually undisturbed, and the top 5 is representative of surface MP contamination in soil. Al. 2018 Su Al. 2020. 323 Soil sample handling. A large sample volume of should be collected to enhance representativeness and accommodate replicates for moisture, recovery rates, and physicochemical testing. Al. 2020. Post-collection, samples should be stored in non-plastic containers, e.g. glass jars, stainless steel jars, aluminum foil trays, and sealed to prevent contamination. Joe Al. 2020. Containers must be clean, dry, and labeled with location, depth, date, and collector details, and preferably stored at 4C. 3-4 Pre-treatment. The soil samples are to be cleaned by removing roots and large debris prior to drying and processed to generate standardized moisture-free baseline data for MP in soil. Different research groups have used varied strategies from air drying at room temperature to oven drying and freeze drying. Details are summarized in Table 3.1. Al. 2018 dried the samples at 70°C for 24 hours, while Van den Berg al. 2020 followed ISO standards and samples were dried at 40°C for 72 hours. Several studies have highlighted the deterioration of MP due to higher temperatures. Al. 2020 AB 2022 AB 2024. Al. 2023 Li al. 2024. Deterioration is reported in polyethylene PE and polyamide PA just over 50°C, while 70°C is generally safe for most other polymers. Hurley al. 2018. Hence, to minimize structural changes, drying temperatures should remain below 60°C, preferably 40°C. Freeze drying, though an alternative, is less practical due to limited throughput. Al. 2023, and often the clay-rich soils become too hard stone-like, making the MP extraction cumbersome and impractical. Sieving is performed by most workers, however, the choice of sieves is often varied. Some researchers have used a cascade of sieves to fractionate different size fractions, while others have used a tomb sieve that allows smaller particles to pass and retains those tomb. The MPs in the 2-5 range can be visually isolated. A major challenge lies in retaining nanoparticles and fine MPs during separation, as their small size increases the risks of loss or thereby skewing quantification. He al. 2018. The different approaches used for sieving have been summarized in Table 3.1. The study from China Nanjing and Switzerland used coarse sieving with 1/5 sieves to remove debris and MPs. In another study from Lake Basin, China, a fine sieve of 1 was used, retaining MPs and excluding aggregates. In studies reported from Spain and Taiwan, the debris including roots, stones, and was manually removed. Enhancing recovery requires refined techniques, such as employing finer meshes or specialized filtration membranes optimized for capturing sub-millimeter MPs. These adjustments improve accuracy in detecting and characterizing MPs, offering deeper insights into their prevalence and behavior in soil ecosystems. 3.3 Sample preparation. The agricultural soil, especially where the sewage, sludge, compost, and fertilizers are applied, is organic rich, and for accurate quantification of MP in soils, organic matter ohm removal is a crucial step. Al. 2020 a 2021, 2022 a B 2024. Li al. 2024 al. 2021. The organic matter removal should precede the density separation. It has been observed that in-density separation often are inefficient as MP embedded in organic matrices, or ohm adhered to MPs like PET, nylon, etc. have a similar density range 114G3 and 2018. It is quite complex to remove ohm without compromising the integrity of polymers, as some of the processes are exothermic and poorly controlled processes, when temperature gets very high, can compromise the integrity of plastic polymers. In the case of agricultural soils, the ohm is also enriched with diverse plant and animal residues that have very different properties and react differently. The more reactive fraction of ohm includes rapidly decomposable components such as lipids, proteins, and sugars, and 2005, which can interfere with MP detection and must be eliminated during sample pretreatment. Organic matter removal typically involves chemical treatment with acids, alkalis, oxidizers, or enzymatic digestion, and 2018 and 2017, al. 2017, al. 2020, Thomas al. 2020. The choice of density separation fluid is equally important for the success of MP segregation from the matrix. Most researchers use sodium chloride Na, which has a density of 1.2 G3 as it is cost-effective. However, it has limited efficiency for high-density polymers. Also, it is not clear how many researchers have used analytical grade Na, since 94.4% of table salt is known to have MPs, al. 2023. Some studies have used distilled water, sodium bromide Na, calcium chloride 2, zinc chloride 2, zinc bromide, and sodium iodide Na to name a few. The efficacy of MP removal is quite high with Na compared to Na, but its cost is prohibitive, approximately 70 times costlier than Na in some countries. While 2 is not very environmentally friendly, it has been observed that some research groups do a density separation in a single step, e.g. a study from Mauritius using Na, while others have done a sequential separation, repeating the density separation several times using 2 or Na, e.g. the study from Chile and Ontario, Table 3.1. Organic matter digestion can be achieved through various chemical methods, including acids, hydrogen peroxide H2O2, and reagent. The use of 65% nitric acid HNO3 or H2SO4 effectively removes ohm, achieving 1% residual organics after 24 hours at 90 C, but it risks degrading polymers like acrylonitrile butadiene styrene ABS, polyamide PA, and polyethylene terephthalate PET. Among the studies reviewed, a Swiss floodplain study used acid digestion. Various workers have also used alkaline solutions, such as a 1,1-KOH-Na mixture, which can mitigate plastic degradation while degrading ohm. In contrast, hydrogen peroxide H2O2 is widely used for ohm oxidation, with studies employing concentrations of 30–35% to disperse soil aggregates and digest organics, achieving up to 72% recovery for microplastic MP when applied to high-ohm soils. For instance, 35% H2O2 effectively dispersed 72% of MPs bound to aggregates, though prolonged treatments, e.g. 72 hours at 23 C, may be required. This is the most commonly used method. Several studies reported from China, Chile, and Greece, Table 3.1, have used H2O2 with temperatures ranging from 50–70 C and reaction time varying between 24 and 72 H. This reaction is exothermic, and it is highly recommended that samples be put in an ice bath to lower the temperature and preserve the polymer integrity. This reagent, an advanced oxidation method combining H2O2 with 2+ under acidic conditions, pH 3.5, generates hydroxyl radicals that degrade ohm with near-complete efficiency, 110% at ambient temperatures. This method has shown promise in organic-rich sediments, recovering 90% of polyethylene, PE, without high-temperature inputs, though it remains under evaluation for broader soil MP separation applications. This reagent provides high degradation efficacy under mild conditions. Each method requires context-specific optimization to minimize plastic damage and maximize organic clearance. The studies from Ontario, Canada, and China, Table 3.1, used reagent for recalcitrant organics. Further research is needed to standardize these protocols, particularly for based approaches. The filtration of soil samples for microplastic analysis is a critical step that requires careful selection of filter types, pore sizes, and polymer compositions to ensure efficient capture and accurate identification. Membrane filters, commonly fabricated from polymers such as polycarbonate, nitrocellulose, or mixed cellulose esters, polytetrafluoroethylene, PTFE, and nylon, are widely employed due to their distinct chemical and physical properties. Polycarbonate membranes are favored for their smooth, uniform surface and high chemical resistance, facilitating clear microscopic imaging and Fourier transform infrared, FTIR, or Raman spectroscopy without spectral interference. Nitrocellulose filters, while cost-effective and suitable for routine use, may require caution due to potential biodegradability in harsh chemical treatments. PTFE membranes, known for their exceptional resistance to aggressive reagents, are ideal for organic solvent-based digestion processes. Pore sizes typically range from 0.45 to 5, with 0.45 being standard for capturing small microplastics, 1, though larger pores, e.g. 1.25, may be used to prevent clogging from soil particulates, sometimes in tandem with prefiltration steps. The choice of pore size balances the need to retain target microplastics while managing sample load and filter longevity. The choice of pore size should also take into account the techniques to be used for identification, i.e., if an ATR-FTIR is to be used, MPs 300 are usually not attempted, while if micro-Raman spectroscopy is used, technically one can identify polymer up to one size. Polymer selection also considers compatibility with downstream analytical techniques. For instance, nylon's hydrophilic nature suits aqueous solutions, whereas PTFE's inertness avoids spectral overlap with common synthetic polymers like polyethylene PE or polypropylene PP. If Nile red solution is to be used for staining the MPs, a polymer filter is to be avoided. Glass fiber filters, though, are occasionally used for high-throughput sieving, but lack the precision of polymer membranes. Among the studies reviewed, the filter type is documented whenever provided in Table 3.1. In the study from Switzerland, cellulose acetate filter with 0.45 pore size was used, which is prone to degradation during processing. The study indicated that nanoplastics were captured, but the risk of clogging was high. On the other hand, the studies from China have used nylon membrane filters and glass fiber filters in a wide range of pore sizes from 0.45 to 25. High-quality nylon filters of 20 were shown to be efficient in a study from Shanxi, China, whereas in another study from Xinjiang, China, the large pore filters 50 were reported to have probably underestimated small MPs. Ultimately, the interplay of filter material, pore size, and soil matrix characteristics ensures optimal recovery of microplastics while minimizing contamination and analytical interference, crucial for reliable environmental monitoring. 3.4 Microplastic identification. The identification of MPs is usually done in two steps: a microscopic examination followed by a polymeric characterization using one of the chemical characterization approaches. 3.4.1 Microscopic characterization. The microscopic identification of MPs is the most prevalent approach using a compound, dissection, stereomicroscope, or UV microscope. It provides a first overview of the likely MP's presence in a sample based on visual inspection and physical characteristics. Al. 2020-2022. The absence of cellular structure, consistency and thickness along the length of the particle, consistent, no bending or tapering, clarity and higher relief, to name a few, are characteristics of a polymer particle. Based on the microscopic examinations, the shape of possible MPs is also identified as fragment, film, and sphere. Several researchers have highlighted the use of fluorescent staining dyes, such as Nile Red Hidalgo Al. 2012, to improve the detection of MPs under a UV microscope. However, it has been shown by subsequent workers that the staining is not exclusive to MPs only. A lot of natural materials like wood, wool, chitin, and natural also are stained, leading to significant misidentification. 20-70% of smaller MPs 100 Song Al. 2015. In the reviewed studies, Table 3.1, most of them have used microscopic examination. Some have done of MPs into fragments and films, like the study from Shanghai, China. In another study from Murcia, Spain, the MP size determination was done using ImageJ software. Despite its accessibility and low cost, microscopic identification alone is considered insufficient for definitive MP identification and has resulted in false positives where organic fibers have frequently been as MPs. 3.4.2 Polymeric characterization of microplastics. To overcome the issue of false positives, it was that polymer validation is crucial. Shim Al. 2017. The most commonly applied techniques for polymer validation are Fourier transform infrared, FTIR, and micro-Raman spectroscopy. Al. 2021. Additionally, automated digital imaging systems and machine learning algorithms are increasingly integrated to reduce human bias and enhance throughput. Al. 2020 Burrs Al. 2023. 3.4.2.1 Fourier transform infrared, FTIR spectroscopy. The Fourier transform infrared spectroscopy identifies polymers by detecting bond-specific infrared absorption, differentiating MPs from organic or inorganic contaminants. Al. 2017. The common operational modes in FTIR include reflectance and transmission, where the transmission mode requires thin, transparent samples, whereas the reflectance mode can work with irregularly shaped and opaque particles. Al. 2020. In the study from the Netherlands, the transmission mode was used, and the standard particle size was 500 table 3.1. The most commonly used FTIR for microplastic analyses is attenuated total reflectance FTIR, ATR-FTIR, which is quite effective for larger particle sizes 300, and was used by the study conducted in Greece, table 3.1. In the ATR-FTIR, we have to put the sample manually on the holder, and it is quite cumbersome if a large number of MPs are present in the sample. The micro-FTIR is coupled with microscopy, and it can effectively identify particles as small as 10. Current models of micro-FTIR often allow semi-automated mapping and can streamline workflows and improve throughput. The data generated are often referenced against spectral libraries, and different workers use different thresholds. The most commonly accepted threshold is 70% match. Raman spectroscopy. The use of micro-Raman spectroscopy enables identifying MPs down to 1 with micro-Raman systems. AL. 2016. The underlying principle behind the instrument leverages the Raman effect, frequency shifts in scattered light, to identify polymers by analyzing vibrational modes and molecular structures. Smith and Dent, 2019. It generates unique spectral fingerprints non-destructively in most cases, but there are reports of MP burning from prolonged laser exposure. A study reported in Table 3.1 from the Tibetan Plateau used micro-Raman and detected pigments and additives as well. The technique struggles with fluorescent additives or pigments, necessitating rigorous sample purification. However, the fluorescence interference is often mitigated by applying baseline correction algorithms and using advanced detectors. Despite its strengths, high specificity, spatial resolution, and non-destructive nature, Raman spectroscopy faces limitations such as weak signal intensity, lengthy data processing, and complex sample preparation. These micro-Raman systems are more costly compared to an ATR-FTIR and micro-FTIR. 3423 Pyrolysis gas chromatography mass spectrometry, GCMS. Pyrolysis gas chromatography mass spectrometry, GCMS, has been used by some research groups. The GCMS thermally decomposes MPs under oxygen-limited conditions, identifying polymers via their degradation products, AL. 2018. Double-shot GCMS enhances efficiency by performing sequential thermal desorption at varying temperatures. Combined with pressurized liquid extraction (PLE), it achieves low detection limits 14 G1 for tire particles and effectively quantifies PE, PP, PMMA, and PS, AL. 2020. Another novel technique recently developed is the pyrolysis gas chromatography coupled to mass spectrometry, GCOMS, TORS AL. 2024. The GCOMS has been optimized for several polymers including methacrylate PMMA, nylon 66, polypropylene PP, nitrobutadiene rubber NBR, polyvinyl chloride PVC, polyethylene terephthalate PET, acrylonitrobutadiene styrene ABS, polyethylene PE, polycarbonate PC, and polystyrene PS TORS AL. 2024. The use of GCMS allows the generation of data as polymer mass in the matrix, and is often incomparable with the concentration data reported in number per unit mass or volume. The other issue is the technique doesn't provide insight into the size of MP or nanoplastic, which is again quite crucial for toxicity assessment. However, we have not seen any instance of its usage for MP determination in soil. 3424 Laser Direct Infrared Spectroscopy, LDIR. The emergence of LDIR as a transformative tool for microplastic research in the past few years is not only based on its ease of use and faster processing time, but also on its technological superiority. The LDIR utilizes a high-resolution camera that is capable of resolving particles up to 10, and coupled with the quantum cascade laser, QCL, its response time is quick and almost instantaneous. It acquires the entire infrared spectrum for an MP in just 1 second ISAC and 2025. The technique provides an excessive advantage in terms of time and sample preparation compared to any other conventional technique, FTIR, micro-Raman, or GCMS, making it very valuable for matrices where there is a large number of MPs. Within the studies reviewed, only the study from Shandong, China, has used LDIR for 21000 MPs. 3425 Thermal analysis. Thermal analyses such as analysis, TGA, and differential scanning calorimetry, DSC, are destructive techniques that are used for MP characterization, Isaac, and 2025. These techniques chemically characterize MPs by assessing thermal degradation profiles, AL. 2017. The efficacy of the thermal analysis is limited in differentiating between similar polymers, like PVC, polyurethane, PET, and polyesters. Despite these constraints, DSC remains advantageous for its simplicity and rapid results. 3426 Scanning electron microscopy, SEM. The scanning electron microscope, SEM, paired with the energy dispersive X-ray spectroscopy, EDS, is an imaging technique that analyzes MPs, surface morphology, and elemental composition, and 2014. However, its application is limited by high costs, time-consuming protocols, and challenges in identifying non-distinct particles, AL. 2020, making it less suitable for routine monitoring. In a study reported within this review, a study from Tamil, India, used SEM-EDS for studying the surface morphology and elemental composition of MPs. The complex sample preparation, including drying and conductive coating the sample, can obliterate the MP morphology as well. It is a destructive technique with limited capability of polymer identification. 3427 Liquid chromatography mass spectrometry, LCMS. Liquid chromatography mass spectrometry, LCMS, has emerged as a powerful analytical tool for identifying and quantifying microplastics, submicron particles, or chemically degraded polymers. The technique leverages chromatographic separation to isolate analytes, followed by mass detection, often employing ionization, ESI, for polar polymers or additives like phthalates. However, LCMS enables targeted analysis of polymer-specific degradation products, additives, or monomers, offering high sensitivity and specificity in complex environmental matrices. While LCMS excels in detecting dissolved or chemically extracted components, its application requires rigorous sample preparation, including enzymatic or oxidative digestion to remove organic interference without altering target polymers. It is prudent to highlight the challenges in universal polymer applicability and its excellent ability to detect PET and PS. LCMS complements existing methods by providing quantitative insights into particles and additive leaching, advancing environmental monitoring and toxicological studies of microplastics. The information provided will not include size and shape data and will be comparable to information derived from GCMS. 3428 Atomic force microscopy, AFM. The AFM generates nanometer resolution images by scanning samples in contact or non-contact modes. When integrated with Raman or IR spectroscopy, it provides simultaneous topographic and chemical data. For instance, AFMR detects thermal expansion from IR absorption, translating it into frequency patterns via Fourier analysis that can be used for MP identification, AL. 2017. However, it is not very commonly used until now. 3.5 Quantification of microplastics and reporting units. The quantification of MPs in the absence of standardized methodologies and reporting units has introduced significant challenges in data comparability and interpretation. Researchers employ diverse analytical techniques and units of measurement, leading to the generation of incomparable datasets, making any temporal assessments challenging and complicated. This issue is particularly pronounced in soil and agricultural systems, where heterogeneous matrices amplify disparities. Despite these issues, most researchers, about 80% of the studies reviewed, have reported MP abundance in terms of MP1. Among the studies reviewed in this paper, a study from Taiwan reported MP abundance in surface soil as MPM2. In some studies, like from Xinjiang, China, where mulch was added to soil, the MPs are reported as GM2. The results from studies where GCMS, LCMS, and TGA are used results are often reported as 1, though they are not frequently used for MP in soils. 3.6 Quality assurance and quality control. Robust quality assurance and quality control, QA/QC protocols are essential to ensure the integrity of microplastic MP analyses across all stages, from field sampling to laboratory processing and identification. Contamination risks arising from airborne MPs, laboratory equipment, or reagents must be systematically minimized to safeguard the precision and validity of results. To address these challenges, stringent measures should be implemented, including the use of metal tools and avoiding plastic materials. Most of the studies reviewed in this paper have avoided using plastic tools. Several workers have reported thorough cleaning of instruments with Q water and used cotton lab coats. Most workers have covered the samples with foil to minimize airborne contamination during sample preparation, and few have used laminar flow cabinets and maintained clean air environments, supported by high-efficiency particulate air HEPA filtration systems to reduce airborne contamination. Al. 2022, Al. 2020. Procedural blanks, including container and solution blanks, are processed identically to samples to monitor background contamination. About 90% of the studies reviewed in this communication have used blanks. Additionally, recovery tests using spiked samples have been used by many research groups. High recoveries of PEPP 80-95% have been reported by workers using Na2, while low recovery was reported for PET PVC, essentially as they used Na and these polymers are denser than the separating fluid. One such report was from Shanghai, China. Another important aspect of QA/QC is the replicate samples. The study from Germany and Spain analyzed triplicate samples, whereas Tanzania and Mexico analyzed a single sample. The QA/QC strategies are to be strictly followed to enhance the reliability of MP inventories. 3.7 Challenges and Recommendations. There have been significant differences among studies in sample collection, preparation, and identification. These differences are evident since the soil is a heterogeneous matrix, and also because there is a huge disparity in the research resources and scientific questions addressed. Based on the studies reviewed, it is observed that studies need to adopt standardized protocols. Some of the key considerations to be taken are summarized below. 371 Sampling Strategies. Since soil is a heterogeneous matrix, collection of representative samples is a key to generating realistic data. It is highly recommended to undertake composite sampling by combining multiple subsamples across the study area. In agricultural systems, where there is high plastic input due to the use of mulch, sludge application, compost, or use of for irrigation, due consideration should be given not to skew the sampling to the topsoil only. In order to capture the true extent of MP pollution it is recommended that stratified samples from 0-10, 10-20, 20-30, and 30-40 be collected to assess vertical distribution, especially in tilled fields. Depending on the size of the study area, the sampling can either be grid or random. It is extremely important to note down the GPS coordinates and all relevant information on agricultural practices like tillage, crops grown, irrigation practices, and whether soil additives, sludge, mulch, etc. have been used. 372 Extraction and Separation. From the published papers, it is explicit that most studies have done a density separation using distilled water, Na, sodium, NaPT, or zinc chloride 2. The recovery rates with distilled water are expected to be very low due to the negative buoyancy of most polymers. However, density separation is very high with 2, but it is corrosive for high recovery rates. We recommend Na, though it is much more expensive than Na. It has also been observed that centrifugation enhances MP removal efficiency. Additionally, has proven to be beneficial, but it should be low energy, else MPs can also disintegrate into smaller sizes. For the digestion of organic matter from soil, 30% H2O2 is quite effective. However, KOH or enzymatic digestion with cellulase or protease is effective and would minimize polymer degradation. For clay-rich soils, adding a dispersant like sodium during extraction improves the extraction of MPs. 373 Identification and Quantification. Most MP research groups use a multi-threaded approach since the mere microscopic examination is not sufficient for the identification of tiny plastic particles. The first step toward the MP identification is microscopic examination using a stereomicroscope, compound microscope, dissection microscope, or UV microscope to identify the morphology, size, shape. However, for polymer identification, one of the several analytical techniques discussed in this paper can be used. The most commonly used polymer identification techniques are ATR-FTIR 300, micro-FTIR 20, and microraman spectroscopy 1. Some advanced techniques like GCMS, GCOMS, and LCMS can provide mass quantification of MPs and even for nanoplastics. However, they have limited usage in MP quantification in soil. It might have high usage if food chain transfer from soil to edible plants is to be looked at. 374 Data reporting. The data is usually reported as particle count per unit mass of matrix, which is the soil in this case. Thus, the results are to be reported as MP1. Some research groups also report mass concentrations as 1, but that is only feasible in soils where high MP concentration is seen, i.e., sludge-applied or mulched soils. It is important to report the size range of MPs as well. In the case of soil, the metadata is also important, as details of soil texture, grain size, organic matter content, agricultural inputs, fertilizers, irrigation, and coordinates should be recorded. 375 Quality control. Looking at the wide range of methodologies and practices employed for MP determination in soils, the QA/QC becomes more so important to generate a reliable dataset. Use of cotton lab coats, glass and metal containers, and working in a laminar flow unit is highly recommended. Also, the use of both field and lab blanks will provide information for realistic correction of data. Some of the studies have used spiked samples to validate methods, and it is also highly recommended. 3.8 Conclusion. This summary of studies so far on microplastics in soil highlights the limited work carried out so far, even though gigantic amounts of MPs end up in agricultural lands as a result of the use of sewage, compost for amending low-productivity soils, use of for irrigation, and mulches for improved productivity. Only 39 studies were published, where details of the methodology are reported for MPs in soil. A quick overview highlights that the methods used for soil are modified methods for MP determination in marine and matrices. One very conspicuous difference between soil and other matrices is the heterogeneity of soil, which makes it imperative that representative samples are collected. The presence of fine-grained clastics, mainly clays, warrants specific steps to ensure the segregation of MPs from the matrix. The digestion of organic matter using 30% H2O2 or enzymatic digestion seems quite effective. The use of GCMS and LCMS for MPs in soil gives a very different level of information on the mass of polymers rather than number. Though not very popular, we have found LDIR to be very effective in the detection of MPs. It provides both the size information and numbers and type of polymers with reasonably high accuracy. There is certainly a need to harmonize methods to be used for MPs in soil for generating comparable datasets across spatial domains. Future work should address nanoplastics and biodegradable polymers, ensuring methodologies evolve with agricultural plastic use. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: Belofa al. 2025, Microplastics in Agricultural Soils. Sources: Impacts on Soil Organisms, Plants, and Humans. Environ Assess 19744-48 PubMed. Burrs N.D. al. 2023, merging holography, fluorescence, and machine learning for continuous characterization and classification of airborne microplastics. 2023-131. In al. 2021, low-density microplastics detected in sheep and soil, a case study from the intensive vegetable farming in southeast Spain. Total Environ 755 142653 PubMed. V. al. 2020, Microplastic Identification via Holographic Imaging and Machine Learning. ADVA 221900153. M. al. 2022, Microplastics in Agricultural Drainage Water, a link between terrestrial and aquatic microplastic pollution. Total Environ 806 150709 PubMed. M.W. 2018, Plastics in Soil, Analytical Methods and Possible Sources. Total Environ 612 422 435 PubMed. I. al. 2021, Assessing the Presence of Microplastic Particles in Tunisian Agriculture Soils and Their Potential Toxicity Effects Using as Bioindicator. Total Environ 796 148959 PubMed. CJR 2005, Soil Structure and Management, a Review. 124 1322. Y. al. 2021, Plastic Contamination of Forest, Urban and Agricultural Soils, a case study of city in the Republic of Korea. J. Soils Sediments, 21-112. F. al. 2019, Evidence of Microplastic Accumulation in Agricultural Soils from Sewage Sludge Disposal. Total Environ 671, 411 420 PubMed. J. al. 2020, Transfer and Transport of Microplastics from Biosolids to Agricultural Soils and the Wider Environment. Total Environ 724, 138334 PubMed. A and CB, Prater 2017 AFMIR, Technology and Applications in Nanoscale Infrared Spectroscopy and Chemical Imaging. Chemical Reviews 117-7, P51465173. Ding et al. 2020, The Occurrence and Distribution Characteristics of Microplastics in the Agricultural Soils of Shanxi Province, in northwestern China. Total Environ 721-37525 PubMed. K. al. 2023, Status of Operation Procedures for Soil Sampling to Analyze Microplastics. 3-115. E. al. 2017, Fast Identification of Microplastics in Complex Environmental Samples by a Thermal Degradation Method. Chemosphere 174, 572-584 PubMed. H. al. 2021, Quantification and Analysis of Microplastics in Farmland Soils, Characterization, Sources, and Pathways. Agriculture 11-330. S. al. 2020, Analysis of Microplastics in a Remote Region of the Tibetan Plateau, Implications for Natural Environmental Response to Human Activities. Total Environ 739, 140087 PubMed. M.B.M. 2017, Simultaneous Trace Identification and Quantification of Common Types of Microplastics in Environmental Samples by Pyrolysis Gas Chromatography, Mass Spectrometry. Environ Technol 51950525060 PubMed. L. al. 2020, a meta-analysis of methodologies adopted by microplastic studies in China. Total Environ 718, 135371 PubMed. Harmsike al. 2021, Amount, Distribution and Composition of Large Microplastics in Typical Agricultural Soils in Northern Germany. Total Environ 758 143615 PubMed. NB al. 2019, Are We Speaking the Same Language? Recommendations for a Definition and Categorization Framework for Plastic Debris. Environ Technol 533 1039104 PubMed. Hidi al. 2018, Microplastics in Soils, Analytical Methods, Pollution Characteristics, and Ecological Risks. AC Trends Anal 109 163 172. Hidi X J 2021, Methods for Separating Microplastics from Complex Solid Matrices, comparative analysis. J. Hazard Mater 409-12464-0 PubMed. L. Al. 2018, Optimization, Performance, and Application of a Pyrolysis GC-MS Method for the Identification of Microplastics. Anal 410-2566636676 PubMed. E. Al. 2021, Abundance of Above-Ground Invertebrates in Agricultural Systems under Glyphosate and Microplastics in Southeastern Mexico. Environments 811-130. Hidalgo v. Al. 2012, Microplastics in the Marine Environment, a review of the methods used for identification and quantification. EnvironTechnol 46630603075 PubMed. Y. Al. 2020, Agricultural Plastic Mulching as a Source of Microplastics in the Terrestrial Environment. Environ 261-14096 PubMed. Hurley R. Al. 2018, Validation of a Method for Extracting Microplastics from Complex Organic-Rich Environmental Matrices. EnvironTechnol 5213-7409741-7 PubMed. Isaac P.J. S. 2025, Laser Direct Infrared Spectroscopy, a cutting-edge approach to microplastic detection in environmental samples. 284-127284 PubMed. E.A. Al. 2021, Microplastics in Agricultural Soils, a case study in cultivation of watermelons and canning tomatoes. Water 13-16-2168. ISO 2017, ISO 18401, to Soil Quality Sampling Part 102, Selection and Application of Sampling Technique. In IS Organization EAD, First Edition 2017-01, Switzerland. BKKK S. Fowler SW 2023 Microplastics MPs in Marine Food Chains, Is It a Food Safety Issue? In F. EAD, Advances in Food and Nutrition Research. Academic Press 101-140. A. Al. 2016, Analysis of Environmental Microplastics by Vibrational Microspectroscopy, FTIR, Raman or both. Anal 408-8377 PubMed. N. Al. 2021, Accumulation of Microcapsules Derived from Coated Fertilizer in Paddy Fields. Chemosphere 267, 129185 PubMed. DLB 2021, Material Flow Analysis of Plastic and Organic Waste in Switzerland. Soil Use 3722, 77288. SK Al. 2021, Abundance and Characteristics of Microplastics in Soils with Different Agricultural Practices, Importance of Sources with Internal Origin and Environmental Fate. J. Hazard Mater 403-12399-7 PubMed. MV AM 2021, Effect of Plastic Film Mulching on the Distribution of Plastic Residues in Agricultural Fields. Chemosphere 273, 128590. M. Al. 2020, Microplastics as Pollutants in Agricultural Soils. Environ 265-1149-80 PubMed. MN, HC, G. 2022, Analysis of Macro and Microplastics in Riverine Riverbanks and Irrigated Farms in Tanzania. Arch Environ Toxicol 82-1142-157 PubMed. Lee J.Y. Al. 2024, A Comprehensive Review of Urban Microplastic Pollution Sources, Environment and Human Health Impacts and Regulatory Efforts. Total Environ 946, 174297 PubMed. Lee Q. Al. 2019, Separation and Identification of Microplastics from Soil and Sewage Sludge. Environ 254, 113076 PubMed. Lee W. Al. 2020, Microplastics in Agricultural Soils, Extraction and Characterization After Different Periods of Polythene Film Mulching in an Arid Region. Total Environ 749, 14142, 0 PubMed. Lee Q. Al. 2021, Are Microplastics Correlated to Phthalates in Facility Agriculture Soil? J. Hazard Mater 412-125164 PubMed. Lee S. Al. 2022, macro and microplastic accumulation in soil after 32 years of plastic film mulching. Environs 301, 18945 PubMed. M.Al. 2018, Microplastic and Mesoplastic Pollution in Farmland Soils in Suburbs of Shanghai, China. Environ 242, 855 862 PubMed. MGJ Al. 2017, Enzymatic Purification of Microplastics in Environmental Samples. Environ Technol 51 24 14283 14292 PubMed. S. Al. 2021, Micro and Nanoplastics Identification, Classic Methods and Innovative Detection Techniques. Front Toxicol 3636640 PubMed Central. F. Al. 2020, Effects of Plastic Mulching on the Accumulation and Distribution of Macro and Microplastics in Soils of 2 Farming Systems in Northwest China. Peer J8, E10375 PubMed Central. JN MGJ C 2020 Finding Microplastics in Soils, a Review of Analytical Methods. Environ Technol 54420782090 PubMed. A. Al. 2021, Microplastics in Outlets of Bandar Abbas City, Iran, a potential point source of microplastics into the Persian Gulf. Chemosphere 262, 128039 PubMed. Ed. Al. 2020, Identification and Quantification of Selected Plastics in Biosolids by Pressurized Liquid Extraction, combined with Double-Shot Pyrolysis Gas Chromatography Mass Spectrometry. Total Environ 715, 136924 PubMed. ZB HT 2023, Microplastic Contamination and Risk Assessment in Table Salts, Turkey. Food Toxicol 175 11369 8 PubMed. S. Al. 2018, Identification and Quantification of Macro and Microplastics on an Agricultural Farmland. Rep 8117950 PubMed Central. S. Al. 2020, Critical Assessment of Analytical Methods for the Harmonized and Cost-Efficient Analysis of Microplastics. 74910121047 PubMed. DEGD 2021 Microplastics in Agricultural Soils, Effluents and Sewage Sludge in Mauritius. Total Environ 798 149326 PubMed. IA 2022 Greenhouse Farming as a Source of and Microplastics Contamination in Agricultural Soils, a Case Study from Southeast Hungary. 71 14357. SSRC 2014 on the quantity and composition of floating plastic debris entering and leaving the estuary, southwest England. Mar Bull 81 155 60 PubMed. T. Al. 2022, Fate of Microplastics in Agricultural Soils Amended with Sewage Sludge. Is surface water runoff a relevant environmental pathway? Environ 293 11852 PubMed. MM 2018 Microplastics in Swiss Floodplain Soils. Environ Technol 52 6359 1359 8 PubMed. Shim WJ SC 2017 Identification Methods in Microplastic Analysis, a Review. Anal Methods 9913841391. Smith E. Dent G. 2019 Introduction, Basic Theory and Principles. In Smith E. Dent G. Modern Raman Spectroscopy. 120. Songwai K. Al. 2015. A comparison of microscopic and spectroscopic identification methods for analysis of microplastics in environmental samples. Marble 93 122 02209 PubMed. Z. Al. 2020. A simple method for the selective quantification of polyethylene, polypropylene, and polystyrene plastic debris in soil by pyrolysis gas chromatography mass spectrometry. J. Anal Pyrolysis 147 104803. AS. Al. 2022. Agricultural application of microplastic-rich sewage sludge leads to further uncontrolled contamination. Total Environ 806 150611 PubMed. Thomas D. Al. 2020. Sample Preparation Techniques for the Analysis of Microplastics in Soil, a Review. Sustainability 12/21/9074. TORS AG/S 2024, GCMS method for the target analysis of microplastics in air. J. Hazard Mater 469-1339-81 PubMed. S. Al 2020, a standardized protocols for microplastics determinations in environmental samples from the Gulf and marginal seas. Mar Bull 158-1113-74 PubMed. S. Fowler SW, T. 2020b Microplastic Particles in the Persian-Arabian Gulf, a review on sampling and identification. Mar Bull 154-111100 PubMed. S. Al. 2021, a review of microplastic distribution in sediment profiles. Mar Bull 163-111973 PubMed. S. Al. 2022, a micro-nanoplastic in the aquatic environment, problems and challenges. Animals 123297 PubMed Central. S. Al. 2022, B. Microplastics in Kuwait streams. Sustainability 1423-15817. AS. Fowler SW 2023, Environmental Microplastics, a significant pollutant of the Anthropocene. In Kane C. AM Microplastic Sources, Fate and Solution. Springer Nature Singapore 89105. S. Al. 2024, Sewage Sludge as Soil Amendment in Arid Soils, a Trace Metal, Nutrient and Trace Organics Perspective. Emerge 111100-420. UNEP 2025, Intergovernmental Negotiating Committee to develop an international legally binding instrument on plastic pollution, including in the marine environment. United Nations Environment Programme, 5th Session, Republic of Korea, 25 November 1 December 2024. Van den Berg P. Al. 2020, Sewage Sludge Application as a Vehicle for Microplastics in Eastern Spanish Agricultural Soils. Environ 261-11419-8 PubMed. Van B. Al. 2021, Sources of Light-Density Microplastic Related to Two Agricultural Practices, the Use of Compost and Plastic Mulch. Environments 8436. Weber A. Al. 2021, Ingestion and Toxicity of Microplastics in the Gastropod, No Microplastic-Induced Effects Alone or in Combination with Copper. Chemosphere 263-12-8040 PubMed. Weber C.J. A.P. 2022, Investigating the Dispersal of Macro and Microplastics on Agricultural Fields 30 Years After Sewage Sludge Application. Rep 121640-1 PubMed Central. P.A. Al. 2024, Soil Microplastic Analysis, a Harmonized Methodology. Crit Rev Environ Technol 5415-113-81163. Subi Al. 2020, Microplastics in the Soil Environment, Occurrence, Risks, Interactions, and Fate, a Review. Crit Rev Environ Technol 5021-2-1752222. Yang M. Al. 2021, Influences of Different Source Microplastics with Different Particle Sizes and Application, Rates on Soil Properties and Growth of Chinese Cabbage, Brassica L. Environ 222-112480 PubMed. Yang J. Al. 2021, B. Abundance and Morphology of Microplastics in an Agricultural Soil Following Long-Term Repeated Application of Pig Manure. Environ 272-11602-8 PubMed. L. Al. 2021, Distribution Characteristics of Microplastics in Agricultural Soils from the Largest Vegetable Production Base in China. Total Environ 756-143860 PubMed. MS 2024, Sewage Sludge Usage in Agriculture, Are We Introducing Microplastics in Food Chain? Soils, International Atomic Energy Agency 10278. GSYF 2018, The Distribution of Microplastics in Soil Aggregate Fractions in Southwestern China. Total Environ 642-1220 PubMed. D. Al. 2016, The Status and Distribution Characteristics of Residual Mulching Film in Xinjiang, China. J. Agric 15 1126392646. Al 2020, an overlooked entry pathway of microplastics into agricultural soils from application of sludge-based fertilizers. EnvironTechnol 54, 7424842555 PubMed. Al 2021, effect of polystyrene microplastics on rice seed germination and antioxidant enzyme activity. Toxics 98179 PubMed Central. Joby Al 2020, microplastics in agricultural soils on the coastal plain of Hangzhou Bay, East China, multiple sources other than plastic mulching film. J. Hazard Mater 388 121 814 PubMed. 4. And Protocol for Microplastics Determination in Soil and Sludge, Applied Soils. Abstract. Microplastics are emerging contaminants of concern, often associated with high concentrations in waste streams. An enormous quantity of dry sludge is generated globally and is often used as a soil amendment in agricultural areas in both the developed and developing countries. The concentration of microplastics, MPs, in sewage sludge varies globally in a wide range between 1 and 186.7260 mpg1. The methodologies used for MP determination in sludge and soils vary, making any realistic comparison infructuous. The International Atomic Energy Agency, IAEA, took the initiative to develop a simple and method under its Coordinated Research Project, CRP, D15021 to determine MPs in agricultural soils and intends to evaluate the fate and environmental impact of plastics in soil and crops. The methodology for MP determination in agricultural soils and sludge-applied soils is presented. Details are given on sample collection and the need for composite samples for non-homogeneous matrices like soil sample processing, including a preferred method for oxidation of organic matter, density separation fluids, and multi-tier sample identification techniques. Adaptation of the method will not only lead to the generation of comparable data for the CRP participants. It will also assist the 178 IAEA member states across the regions in generating analogous datasets on microplastics, MPs, in soil and sludge-applied soils. The data and information generated on MP inventories can be used to underpin the policy on safe sludge usage in agricultural soils. 4.1 Introduction. 4.1.1 Background. Plastics have become an integral part of modern society, offering a wide array of desirable properties such as lightweight, chemical resistance, durability, and affordability. The impact of microplastics, MPs, in terrestrial ecosystems, particularly in soils and soils amended with sludge, has been relatively overlooked. The primary sources of MPs in terrestrial ecosystems were observed with the combination of sludge and municipal solid waste composts, considered resourceful components for land application as a substitute for traditional, and 2023. Sewage sludge from treatment plants emerges as a major contributor to MP pollution in soil, as it contains both primary and secondary MPs. Despite its potential as a valuable soil additive due to its organic and nutrient content, concerns have arisen regarding the spread of pollutants through sludge application in agriculture. The MPs have the potential to be transported by the wind and as rain overflows to nearby lands and aquatic systems, besides the vertical movement in the soil profiles due to infiltration of irrigation water and rainwater. Globally, approximately 45 million tons of dry sludge are produced annually, Al. 2020 from treatment plants, with a significant portion being used in landfills, incinerated, or applied to soil as a. This practice has raised environmental concerns, particularly regarding the fate and impact of MPs in soil and crops. These MPs can potentially cause phytotoxic effects and can be directly and indirectly linked to human health. Therefore, quantifying them in the soils and sludge is novel information for managing soils and the environmental quality of respective regions. There is a need to develop a harmonized method for identifying MPs in soil and sludge-applied soils to generate reliable data for plastic pollution. Microplastics can persist in soils for a long time, with estimates ranging from 15 to 34 years of residence time, and Richards 2005, Weber al. 2022. A recent study highlights the uncontrolled contamination of adjacent land due to sludge application, with 44% of the MP load on sludge-applied land found on nearby untreated land, suggesting spillover effects reaching depths of 60-90 in the soil profile in 2024. These are important considerations when collecting soil samples for MP assessments. The lack of standardized protocols for assessing MPs in soil and sludge-applied soil has hindered reliable data collection and comparison across studies. Recognizing this need, the Joint FSHO-AEA launched a coordinated research project, D15021, to evaluate the fate and environmental impact of plastics in soil and crops. As part of the International Atomic Energy Agency's IAEA initiative, a method is developed that deals with the issues emanating from sample collection, sample processing, and techniques used in identification and reporting units in soils and sludge-applied soils. The scientifically sound data would facilitate informed decision-making and design of mitigation strategies to combat MP pollution in terrestrial environments. 4.1.2 Objective of the Protocol. The protocol establishes a method for collecting, processing, and reporting MP abundance in soil samples. 4.1.3 Scope of the Operational Protocol. This procedure is applicable for sampling, processing, and determining the abundance of MP particles, 1 to 5 and with densities 1.8 G3 in the top 10-20 of a soil profile. 4.1.4 Decision Tree for selecting the approach. Decision tree for MP research. The decision tree depends on the various types of MPs. Define the scope of MP analysis. 5. Proceed with visual identification and manual sorting question. Is this size fraction sufficient for the study? If yes, analyze. If no, proceed to smaller sizes. 5. Proceed with visual identification and manual sorting. Question: is this size fraction sufficient for the study? If yes, analyze. If no, proceed to smaller sizes. 1.5 Use sieving or filtering techniques, followed by optical microscopy for preliminary analysis. 1. Use sieving or filtering techniques, followed by optical microscopy for preliminary analysis. 1.1 Use microscopy coupled with spectroscopic methods, e.g. FTIR or Raman or LDIR, for identification and quantification. 1.1 Use microscopy coupled with spectroscopic methods, e.g. FTIR or Raman or LDIR, for identification and quantification. 1. Nano-plastics proceed with advanced techniques, e.g. SEM-TEM, DLS, or AF4 coupled with spectroscopy. 1. Nano-plastics proceed with advanced techniques, e.g. SEM-TEM, DLS, or AF4 coupled with spectroscopy. If an optical microscope is available, conduct visual analysis for size, shape, and though not essential research question, is qualitative data on MPs sufficient? If an optical microscope is available, conduct visual analysis for size, shape, and though not essential. Research question: is qualitative data on MPs sufficient? ATR FTIR, attenuated total reflectance Fourier transformed infrared spectroscopy, analyze the chemical composition of particles 300, suitable for polymer type identification and quantification. ATR FTIR, attenuated total reflectance Fourier transformed infrared spectroscopy. Analyze the chemical composition of particles 300, suitable for polymer type identification and quantification. FTIR microfourier transformed infrared spectroscopy, analyze the chemical composition of particles 20, suitable for polymer type identification and quantification. FTIR microfourier transformed infrared spectroscopy. Analyze the chemical composition of particles 20, suitable for polymer type identification and quantification. Raman spectroscopy use for particles as small as 1 best for detailed polymer and additive identification. Raman spectroscopy use for particles as small as 1 best for detailed polymer and additive identification. SEM-TEM scanning or transmission electron microscopy analyze surface morphology or ultrastructure for micro and nanoplastics coupled with EDX for elemental composition, though limited capabilities for polymer identification. SEM-TEM, scanning or transmission electron microscopy. Analyze surface morphology or ultrastructure for micro and nanoplastics, coupled with EDX for elemental composition, though limited capabilities for polymer identification. GCMS pyrolysis gas chromatography, mass spectrometry identify polymer types through thermal degradation. However, this has limited application, as there will be no information on the size and number of particles suitable for bulk composition analysis. GCMS pyrolysis gas chromatography, mass spectrometry identify polymer types through thermal degradation. However, this has limited application, as there will be no information on the size and number of particles suitable for bulk composition analysis. AF4 MALS-DLS, asymmetric flow field flow fractionation with multi-angle light scattering or dynamic light scattering analyze nanoplastic size distribution and stability. AF4 MALS-DLS, asymmetric flow field flow fractionation with multi-angle light scattering or dynamic light scattering. Analyze nanoplastic size distribution and stability. Counting techniques with filters and microscopes and hot needle tests. Counting techniques with filters and microscopes and hot needle tests. Quantify MPs in terms of particles per unit volume or mass. Quantify MPs in terms of particles per unit volume or mass. Use FTIR, Raman spectroscopy, LDIR, or pyrolysis GC, MS depending on the size range of interest. Use FTIR, Raman spectroscopy, LDIR, or pyrolysis GC, MS depending on the size range of interest. In this case, the smaller MPs and nanoplastics will be more important due to their higher surface to volume ratios. Smaller MPs using microraman and NPs using AF4 MALS-DLS or tests with leachate analyses. In this case, the smaller MPs and nanoplastics will be more important due to their higher surface to volume ratios. Smaller MPs using microraman and NPs using AF4 MALS-DLS or tests with leachate analyses. Use spectroscopic analysis FTIR Raman combined with adsorption experiments to examine interactions with chemicals such as heavy metals, persistent organic pollutants, POPs, pesticide residues, pharmaceuticals, and others. Use spectroscopic analysis FTIR Raman combined with adsorption experiments to examine interactions with chemicals such as heavy metals, persistent organic pollutants, POPs, pesticide residues, pharmaceuticals, and others. 4.2 Theoretical basis. The procedure is based on the analysis of MPs in three size fractions, 1/300, 300 to 1, and 1 to 5. The sampling focuses on MPs collection from soil 10-20 depth using a composite sample. The survey design approach allows an unbiased assessment of the target agricultural and non-agricultural soil, irrespective of its size and composition. The analysis of MPs includes sieving, density separation, the removal of organic matter, and reporting the total count of MPs using a microscope and ATR-FTIR, FTIR, microraman, or LDIR. The method targets synthetic polymers with variable specific densities of 1,8G3. This is reflected in the use of a saturated solution of Na 1.8G3 to separate MPs from the sampled soil. Na is selected due to its high density. Alternative salts of higher densities may be used for subsequent extractions if users desire and should be reported in the metadata sheet. After separation by density, the chemical digestion of the supernatant is carried out with H2O2 1535% or KOH to eliminate organic matter and reduce its interference in the count of MPs. 4.3 Materials, reagents, and equipment. All materials used for sampling, storage, and analysis must be glass or metal. 4.3.1 Equipment and materials for field work. Pencil and logbook data from the field. Pencil and logbook data from the field. GPS for sampling points, WGS84, coordinates in decimal degrees. GPS for sampling points, WGS84, coordinates in decimal degrees. Batteries plus extra. Batteries plus extra. Camera. Measure tape at least 20 m long. Measure tape at least 20 m long. A 50-50 square frame divided into 4 sections of 25-25. The frame can be made either of wood or metal, and metal or wooden stakes can also be used to delimit the sampling area. A 50-50 square frame divided into 4 sections of 25-25. The frame can be made either of wood or metal, and metal or wooden stakes can also be used to delimit the sampling area. 10L metal buckets. 10L metal buckets. Shovel suitable for surface soil collection. Shovel suitable for surface soil collection. Auger. Metal or glass containers with lids of at least 2 capacity. Metal or glass containers with lids of at least 2 capacity. Tape of paper adhesive for sample labeling. Tape of paper adhesive for sample labeling. Permanent ink markers. Permanent ink markers. Foil. 432 laboratory equipment and materials. Oven temperature 200 C. Oven temperature 200 C. Muffle furnace for cleaning laboratory glassware. Muffle furnace for cleaning laboratory glassware. Oven for drying samples, temperature 50 C. Oven for drying samples, temperature 50 C. Analytical balance, sensitivity 0.0001 G. Analytical balance, sensitivity 0.0001 G. Sieve shaker for cascade sieving, suitable for sieves at least 20 in diameter and 5 in height. Sieve shaker for cascade sieving, suitable for sieves at least 20 in diameter and 5 in height. Magnetic stirrer for solutions. Magnetic stirrer for solutions. Vacuum pump. Vacuum pump. Stereo or compound microscope or dissection microscope, preferably a UV microscope, minimum 40 and preferably 100x magnification. Stereo or compound microscope or dissection microscope, preferably a UV microscope, minimum 40 and preferably 100x magnification. Laminar flow hood recommended. Laminar flow hood recommended. Stainless steel or trays for drying samples. Stainless steel or trays for drying samples. Stainless steel sieves at least 20 in diameter and 5 high, with 45, 63, 125, 250, 300, 500, 1 tomb, 3 and 5 metal mesh. Stainless steel sieves at least 20 in diameter and 5 high, with 45, 63, 125, 250, 300, 500, 1 tomb, 3 and 5 metal mesh. Glass beakers of various volumes, 605,000 ml. Glass beakers of various volumes, 605,000 ml. Foil. Watch glass to cover beakers. Watch glass to cover beakers. Magnetic glass stirring bars. Magnetic glass stirring bars. Glass filtration system for 45 m diameter filters, filtration funnel, base with filter holder and clamps. Glass filtration system for 45 m diameter filters, filtration funnel, base with filter holder and clamps. Flask of at least 1 L. Flask of at least 1 L metal filters 45 m diameter and 25 pore size. Metal filters 45 m diameter and 25 pore size. Fine-tipped anti-static stainless steel twisters. Fine-tipped anti-static stainless steel twisters. Glass pipette. Glass pipette. 7652 1 slide for microscope. 7652 1 slide for microscope. Paper adhesive tape for sample labeling. Paper adhesive tape for sample labeling. Washing bottle with filtered distilled or water, filtered with 0.45 filter. Washing bottle with filtered distilled or water, filtered with 0.45 filter. Cotton lab coat. Cotton lab coat. Gloves and safety glasses for preparation and handling of work solutions. Gloves and safety glasses for preparation and handling of work solutions. 433 reagents and solutions. Water filtered by 0.45 or smaller. Water filtered by 0.45 or smaller. NaI analytical grade. NaI analytical grade. Liquid detergent. Liquid detergent. Hydrogen peroxide 1535% H2O2. Hydrogen peroxide 1535% H2O2. Saturated NaI solution 1.8 G3. Saturated NaI solution 1.8 G3. 4.4 Sample collection in the field. Soil, being a non-homogeneous matrix, needs special consideration while sampling. The soil sampling strategy laid down by ISO 18401/2017 is relevant to sampling for MPs in soil. The sampling can be for the hotspots, systematic grid or AL. 2018, random or stratified AL. 2019, very much depending on the research question, whether one is looking at baseline levels in soils or sludge-applied soils or spillover from agricultural farms, treatment plants, roads, precipitation, and even aeolian deposits. A critical point to consider is the sampling depths, as they can significantly differ due to management practices such as plowing 18,401/2 I-2017. The minimum sampling depth in Germany is recommended as 30 BBODV 1999, whereas in most studies on MPs in agricultural soils, the top 5 is sampled AL. 2018 AL. 2018. The US EPA and USDA recommend taking control samples of the same soil type from a pristine area non-affected by the contaminant of concern, AL. 2012 US EPA 2020. However, because of the omnipresence of MPs and their transport via aerosols with precipitation, it is recommended that random samples of non-agricultural areas away from urban populations should be taken to reduce the risk of bias due to sludge application or carryover. 441 General considerations for sampling. Sampling should only be carried out under suitable weather conditions. Sampling should be avoided under heavy rain, immediately after heavy rain, when the fields are flooded and under conditions of heavy dust, gusts, snow cover, and frost. For the purpose of inventories and baseline sampling should ideally cover different soil types and vegetative covers, including bare or sparsely vegetated arable land, low-growth grassland, e.g. shortly after mowing, forest, orchards, etc. 442 Site selection and description. Prior permissions should be obtained if sampling is done from private property or areas with controlled access. Prior permissions should be obtained if sampling is done from private property or areas with controlled access. Record the land cover, agricultural management practices, plowing, furrowing, application, plastic mulch, pest control, sludge addition, proximity of road, and any other relevant information. Record the land cover, agricultural management practices, plowing, furrowing, application, plastic mulch, pest control, sludge addition, proximity of road, and any other relevant information. Provide a map, excerpt, or sketch of the sampling area, including the location of the sampling grid. Provide a map, excerpt, or sketch of the sampling area, including the location of the sampling grid. If surface plastic contamination, littering, films, etc. is visible, document it with photos. If surface plastic contamination, littering, films, etc. is visible, document it with photos. Check if there are existing data from previous surveys for the Site S, and verify whether they still reflect current conditions during sampling. Any changes observed during site assessment should be noted in the relevant parameters. Check if there are existing data from previous surveys for the Site S, and verify whether they still reflect current conditions during sampling. Any changes observed during site assessment should be noted in the relevant parameters. 443 On-site sampling. A soil sample with a depth of 1020 should be collected using a stainless steel auger of 3.5 diameter, and several samples should be collected to make a composite sample that is more representative of a site and overcome the issue of MP heterogeneity in soils. A soil sample with a depth of 1020 should be collected using a stainless steel auger of 3.5 diameter, and several samples should be collected to make a composite sample that is more representative of a site and overcome the issue of MP heterogeneity in soils. The sampling fields should be divided into 3 subplots, and a composite subsample of 15-30 samples should be drawn from each subplot, covering up to 1 ha. At least 3 aliquots should be collected from composite samples as replicates. The sampling fields should be divided into 3 subplots, and a composite subsample of 15-30 samples should be drawn from each subplot, covering up to 1 ha. At least 3 aliquots should be collected from composite samples as replicates. Large pebbles, stones, and wood pieces should be removed during the sample collection. Large pebbles, stones, and wood pieces should be removed during the sample collection. Each subsample should be with a legible permanent marker or with a waterproof label on at least 2 sides of the container. Each subsample should be with a legible permanent marker or with a waterproof label on at least 2 sides of the container. However, if the vertical migration of microplastics in soils is to be studied, a core should be collected using a 10 steel barrel and sliced at each. However, if the vertical migration of microplastics in soils is to be studied, a core should be collected using a 10 steel barrel and sliced at each. In this case, each core should be considered individually. The soil samples should be stored in pre-cleaned wide-mouth glass jars or containers, and initial wet weight should be recorded. The soil samples should be stored in pre-cleaned wide-mouth glass jars or containers, and initial wet weight should be recorded. The samples are to be stored at room temperature until further analyses. It is recommended that with each sampling campaign, a field background sample be taken from a non-agriculture area away from urban populations and major roads to reduce the risk of bias due to sludge application or carryover. It is recommended that with each sampling campaign, a field background sample be taken from a non-agriculture area away from urban populations and major roads to reduce the risk of bias due to sludge application or carryover. 4.5 Sample processing. Fractionation into 3 size groups. Density separation. Organic matter removal digestion with H2O2 or KOH. 1.120, 120, 2.2 300, 2300, 3.31000, 3001000. 451 Pretreatment of soil samples. Dry samples in the oven at 50 degrees to constant weight. Ambient temperature should be reported in the metadata note. To avoid contamination of the samples by MPs in the laboratory environment, cover the sample with foil during drying. Make some perforations to allow water to evaporate. Dry samples in the oven at 50 degrees to constant weight. Ambient temperature should be reported in the metadata. Note, to avoid contamination of the samples by MPs in the laboratory environment, cover the sample with foil during drying. Make some perforations to allow water to evaporate. Once samples have dried and reached a constant weight, record the dry weight of each sample in the corresponding data sheet. Once samples have dried and reached a constant weight, record the dry weight of each sample in the corresponding data sheet. Separately, place each sample in the automatic sieve shaker and cascade sifting using at least 300 1 and 5 sieves for a minimum of 15 minutes. However, we highly recommend using a complete sieve set to provide better resolution for smaller MPs. Separately, place each sample in the automatic sieve shaker and cascade sifting using at least 300 1 and 5 sieves for a minimum of 15 minutes. However, we highly recommend using a complete sieve set to provide better resolution for smaller MPs. Recover the fractions retained in the base for size fraction 1 to 300, sieves of 300, 300 to 1 and 1 to 5 and transfer them to respective beakers. Recover the fractions retained in the base for size fraction 1 to 300, sieves of 300, 300 to 1 and 1 to 5 and transfer them to respective beakers. Discard any material retained on the 5 missives, but take a photo and record the information as metadata. Discard any material retained on the 5 missives, but take a photo and record the information as metadata. 452 Density separation and extraction of microplastic particles. Add saturated and filtered 0.45 Ni solution, G3, to a large glass beaker 1000. Ensure that the solution is about 5 times the volume of the sample. Add a glass magnetic stirrer. Add saturated and filtered 0.45 Ni solution, G3, to a large glass beaker 1000. Ensure that the solution is about 5 times the volume of the sample. Add a glass magnetic stirrer. Pour the soil fraction into the glass beaker. Pouring in this way allows the particles to start separating. Top up with more Ni solutions if they are insufficient. Pour the soil fraction into the glass beaker. Pouring in this way allows the particles to start separating. Top up with more Ni solutions if they are insufficient. Add a drop of pre-filtered liquid detergent as a surfactant to the mixture to prevent particles from adhering to the walls of the beaker. We recommend using aqueous sodium solution for the samples in a glass beaker. Joe Al. 2020, Al. 2019, to help dissolve aggregates and lumps. Add a drop of pre-filtered liquid detergent as a surfactant to the mixture to prevent particles from adhering to the walls of the beaker. We recommend using aqueous sodium solution for the samples in a glass beaker. Joe Al. 2020, Al. 2019, to help dissolve aggregates and lumps. Cover the glass jar with foil or watch glass and stir gently on a magnetic stirring plate for 20-30 minutes. Cover the glass jar with foil or watch glass and stir gently on a magnetic stirring plate for 20-30 minutes. After agitation, allow the sample to stand overnight. After agitation, allow the sample to stand overnight. Filter the supernatant through a 0.8 metal or an filter 47 diameter using a vacuum filtration system. Filter the supernatant through a 0.8 metal or an filter 47 diameter using a vacuum filtration system. Once the entire sample has been filtered, rinse the walls of the flask or filtration funnel and the filter using pre-filtered distilled water to collect any remaining particles and eliminate possible traces of salt precipitates that may have formed during the process. Once the entire sample has been filtered, rinse the walls of the flask or filtration funnel and the filter using pre-filtered distilled water to collect any remaining particles and eliminate possible traces of salt precipitates that may have formed during the process. Stop the pump and let air into the filtration system to remove the vacuum. Stop the pump and let air into the filtration system to remove the vacuum. Note, if desired by individual laboratories, a second separation with a denser solution could be performed on the remaining sediment. This will allow them to collect supplementary data to align with any other in-house protocols. 453 Organic matter removal. This reaction should be performed in a fume hood and on ice as this is exothermic. This reaction should be performed in a fume hood and on ice as this is exothermic. Transfer the sample on the filter to 200 beaker with a magnetic stirrer. Transfer the sample on the filter to 200 beaker with a magnetic stirrer. The sample should be kept in an ice bath, and the H2O2 should be added in a ratio of 1:1 until no bubbles are observed. However, we recommend adding H2O2 bit by bit. If the sample has not turned clear, more H2O2 may be added. The sample should be kept in an ice bath, and the H2O2 should be added in a ratio of 1:1 until no bubbles are observed. However, we recommend adding H2O2 bit by bit. If the sample has not turned clear, more H2O2 may be added. 4.6 Identification and quantification of microplastics. Once the sample is density separated and organic matter is removed, it should be filtered on a silver or membrane filter, and a multi-tier identification process must be undertaken. If the LDIR is to be used for polymeric, a gold filter will be used. 461 Microscopic identification. The first step is identification under a microscope, considering the particles that show the absence of any cellular structure, consistency in, higher relief and sharp edges. Note the abundance of natural due to roots and the addition of sewage sludge make it very challenging to differentiate between plastic polymers and matrix interference. The first step is identification under a microscope, considering the particles that show the absence of any cellular structure, consistency in, higher relief and sharp edges. Note the abundance of natural due to roots and the addition of sewage sludge make it very challenging to differentiate between plastic polymers and matrix interference. It is recommended that the particles be marked as tentative MPs after microscopic examination. It is recommended that the particles be marked as tentative MPs after microscopic examination. 462 Spectroscopic. Looking at the complexity of the chemical composition of MPs and morphology, merely the microscopic examination cannot confirm its presence with a high degree of certainty. It is recommended to check 10–20% of the particles on the filter if they are over 500, and all the particles if they are less than 500 to confirm their synthetic fingerprint synthetic polymer, plastic, using one of the techniques below. Looking at the complexity of the chemical composition of MPs and morphology, merely the microscopic examination cannot confirm its presence with a high degree of certainty. It is recommended to check 10–20% of the particles on the filter if they are over 500, and all the particles if they are less than 500 to confirm their synthetic fingerprint synthetic polymer, plastic, using one of the techniques below. The four most commonly employed techniques are the attenuated total reflectance Fourier transformed infrared spectroscopy (ATR-FTIR) is effectively used in analyzing MPs of 300 here. Each single particle is investigated individually. The other technique is the micro-Fourier transformed infrared spectroscopy (FTIR), which allows analyses of the MP over the filter sample directly and has an advantage when identifying polar groups. It is often more powerful and can identify MPs up to a finer resolution of 1020 to 300 AL. 2016, the Raman spectroscopy provides the highest resolution of 1 AL. 2021, and a better response for nonpolar bonds. Laser direct infrared (LDIR) chemical imaging system is another very useful technique, but here the filtration system is a 25mm apparatus with gold filters. It is very effective for detecting particles 50 in size. However, 70–80% of particles are in the unassigned category and require a careful spectral evaluation. Note, another technique that can be quite useful for identifying polymers is the pyrolysis gas chromatography mass spectrometry, GC-MS. Unlike FTIR and Raman, this destructive technique is quite efficient in identifying polymer types, but not in the quantification of MPs in terms of size, shape, and number, making any comparison difficult with published and widely reported MP data in soil. The four most commonly employed techniques are the attenuated total reflectance Fourier transformed infrared spectroscopy (ATR-FTIR) is effectively used in analyzing MPs of 300 here. Each single particle is investigated individually. The other technique is the micro-Fourier transformed infrared spectroscopy (FTIR), which allows analyses of the MP over the filter sample directly and has an advantage when identifying polar groups. It is often more powerful and can identify MPs up to a finer resolution of 1020 to 300 AL. 2016. The Raman spectroscopy provides the highest resolution of 1 AL. 2021, and a better response for nonpolar bonds. Laser direct infrared (LDIR) chemical imaging system is another very useful technique, but here the filtration system is a 25mm apparatus with gold filters. It is very effective for detecting particles 50 in size. However, 70–80% of particles are in the unassigned category and require a careful spectral evaluation. Note, another technique that can be quite useful for identifying polymers is the pyrolysis gas chromatography mass spectrometry, GC-MS. Unlike FTIR and Raman, this destructive technique is quite efficient in identifying polymer types, but not in the quantification of MPs in terms of size, shape, and number, making any comparison difficult with published and widely reported MP data in soil. 4.7 Reporting. The abundance of MPs in soil should be reported based on the area or mass, preferably both. The abundance of MPs in soil should be reported based on the area or mass, preferably both. Determine the abundance of MPs per M2, MPMP M2100625 M2. Determine the abundance of MPs per kilogram of dry soil MPMP 11. The number of microplastic particles identified in the procedure target shall be subtracted from the values obtained in the samples of the corresponding batch. 1. The number of microplastic particles identified in the procedure target shall be subtracted from the values obtained in the samples of the corresponding batch. 4.8 Quality control. Carefully clean all working material with running water and detergent, and rinse with filtered distilled water. Carefully clean all working material with running water and detergent, and rinse with filtered distilled water. Decontaminate all glass material in a furnace at 500 C for 46H to eliminate contamination. Decontaminate all glass material in a furnace at 500 C for 46H to eliminate contamination. Keep the materials protected with foil after cleaning until their use to prevent cross-contamination. Keep the materials protected with foil after cleaning until their use to prevent cross-contamination. Be careful not to generate cross-contamination during sampling and preparation due to using the same material, shovels, buckets, etc. Be careful not to generate cross-contamination during sampling and preparation due to using the same material, shovels, buckets, etc. Thoroughly clean the work area with 70% technical alcohol so it is free of dust or microplastic particles. Thoroughly clean the work area with 70% technical alcohol so it is free of dust or microplastic particles. Avoid having multiple personnel in the work area during the testing process. Avoid having multiple personnel in the work area during the testing process. Avoid using synthetic clothing. Use 100% cotton lab coats or easily distinguishable, such as orange and green, used in traffic uniforms. Avoid using synthetic clothing. Use 100% cotton lab coats or easily distinguishable, such as orange and green, used in traffic uniforms. Clean metal filters with 100% ethanol and verify under stereo microscope before use. Clean metal filters with 100% ethanol and verify under stereo microscope before use. Avoid exposing samples to air more than necessary. Avoid exposing samples to air more than necessary. Ideally, sample processing should be performed in laminar flow hoods. Ideally, sample processing should be performed in laminar flow hoods. All working solutions must be filtered with a 0.45 pore size filter before use. All working solutions must be filtered with a 0.45 pore size filter before use. 481 Blank analysis. Running a procedural blank using a 100-gram soil sample baked at 500 C for 4-6 hours and 1 L of filtered water is recommended. Running a procedural blank using a 100-gram soil sample baked at 500 C for 4-6 hours and 1 L of filtered water is recommended. The blanks should be subjected to the entire analytical process together with the samples. The blanks should be subjected to the entire analytical process together with the samples. At least one procedure blank shall be analyzed for each batch of 10 samples maximum, i.e., if the working batch is greater than 10 samples, a second blank must be performed. At least one procedure blank shall be analyzed for each batch of 10 samples maximum, i.e., if the working batch is greater than 10 samples, a second blank must be performed. 482 Positive controls or standard reference material. It is recommended to spike a soil sample that was baked at 500 C with the known number and type of polymers. It is recommended to spike a soil sample that was baked at 500 C with the known number and type of polymers. With each batch, at least one positive control should be analyzed. With each batch, at least one positive control should be analyzed. If standard reference material, SRM, is accessible, it can be used instead of a positive control for each batch of analyses. If standard reference material, SRM, is accessible, it can be used instead of a positive control for each batch of analyses. 483. Repeat the microplastic detection and counting process. The counting of MPs on the filter should be repeated by a second analyst. The counting of MPs on the filter should be repeated by a second analyst. Compare the results obtained on a randomly chosen filter. Compare the results obtained on a randomly chosen filter. Laboratories should determine the coefficient of variation of possible MPs identified by microscopic examination by different operators, and the variance should be reported. We recommend that 10% be considered the maximum for accepting the results. Laboratories should determine the coefficient of variation of possible MPs identified by microscopic examination by different operators, and the variance should be reported. We recommend that 10% be considered the maximum for accepting the results. If there is over 10% variation, it should be given to the third operator and fourth. If there is over 10% variation, it should be given to the third operator and fourth. 484. Proficiency test. Laboratories are highly encouraged to participate in proficiency tests to evaluate the analytical performance of the laboratory. Laboratories are highly encouraged to participate in proficiency tests to evaluate the analytical performance of the laboratory. Authors are thankful to the Kuwait Institute for Scientific Research for supporting the study under Project M127C and to the International Atomic Energy Agency for the award of the research contract No. 26,641 entitled Assessment of Microplastic Input and Transfer to Agricultural Soils by Sewage Sludge Application under the Coordinated Research Project CRP, Assessing the Fate and Environmental Impact of Plastics in Soil and Crop Ecosystems Using Isotopic Techniques, D15021. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license, and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1840102, I-2017, Soil Quality Sampling Part 102, Selection and Application of Sampling Techniques. International Organization for Standardization, Geneva, Switzerland. Technical Report. Bibad v. 1999, Federal Soil Protection and Contaminated Sites Ordinance. Number on the basis of 6, 8 paragraphs 1 and 2, and 13 paragraph 1 sentence 2 Federal Soil Protection Law of 17 March 1998. Federal Law Gazette, Berlin, Germany. IP 502. F. Al. 2019, Evidence of Microplastic Accumulation in Agricultural Soils from Sewage Sludge Disposal. Total Environs 671, 411 420 PubMed. N. Al. 2020, Thermochemical Conversion of Sewage Sludge, A Critical Review. Prog Energy Combust 79100-843. O. Al. 2019, Marine Litter and Microplastic Pollution on Mangrove Soils of the Colombian Caribbean. Mar Bull 145 455 462, PubMed. Hurley R. Al. 2018, Validation of a Method for Extracting Microplastics from Complex Organic-Rich Environmental Matrices. EnvironTechnol 5213, 740974117 PubMed. A. Al. 2016, Analysis of Environmental Microplastics by Vibrational Microspectroscopy, FTIR, Raman, or both. Anal 408-8377 PubMed. M. Al. 2018, Microplastic and Mesoplastic Pollution in Farmland Soils in Suburbs of Shanghai, China. Environ 242, 855-862 PubMed. S. Al. 2018, Identification and Quantification of Macro and Microplastics on an Agricultural Farmland. Rep 8117-950, PubMed Central. P. Al. 2012, Natural Resources Conservation Service. National Soil Survey Center, Lincoln. Field Book for Describing and Sampling Soils, version 3. S. Al. 2021, a review of microplastic distribution in sediment profiles. Mar. Bull 163, 111973 PubMed. US EPA 2020, LSASD Operating Procedure for Soil Sampling, Technical Report LSASD PROC 300 R4. Laboratory Services and Applied Science Division. Weber CJ AP 2022, Investigating the Dispersal of Macro and Microplastics on Agricultural Fields 30 Years After Sewage Sludge Application. Rep 12-16401 PubMed Central. MS 2024, Sewage Sludge Usage in Agriculture, Are We Introducing Microplastics in Food Chain? Soils, International Atomic Energy Agency 10278. SU 2023, Using Sewage Sludge as Alternative, Effects on Turf Performance of Perennial Ryegrass. Sustainability 15-18-13597. Zhou B. Al. 2020, Microplastics in Agricultural Soils on the Coastal Plain of Hangzhou Bay, East China, Multiple Sources Other Than Plastic Mulching Film. J. Hazard Mater 388-121-814 PubMed. KAV Richards BK 2005, Synthetic Fibers as an Indicator of Land Application of Sludge. Environ 138-22, a 1211 PubMed. 5. A Critical Perspective on Nanoplastics in Soil and Crop Systems. Abstract. Nanoplastics have emerged as a significant emerging contaminant of the Anthropocene. The ubiquitous presence of nanoplastics attracted considerable attention due to their potential impacts on soil and crop systems. The nanoplastics can be primary and secondary in origin. Their interaction and fate in soil depend on the physicochemical properties, including size, shape, surface charge, and polymer type. Nanoplastics can both adsorb and leach contaminants, altering soil chemistry and increasing the bioavailability of toxic substances to plants and microorganisms in the rhizosphere. Nanoplastics interferes with soil-plant microbe interactions, often bringing changes in rhizosphere microbial community composition and function, negatively impacting soil health and crop productivity. Experimental evidence on nanoplastics uptake by roots exacerbates their accumulation in other tissues, including edible plant parts, posing risks to food safety and human health. Nanoplastics are reported to induce oxidative stress in plants and soil microorganisms, impairing key physiological processes and reducing crop yields. Reports of nanoplastic within the food chain underscore the need for risk assessments. Despite a growing body of evidence, significant knowledge gaps remain, especially in the detection, quantification, and of nanoplastics in the environment. Even though pyrolysis GCMS can help identify the polymer, the approach provides no information on the shape, number, and size of the nanoplastics, which is a severe constraint in assessing nanoplastic contamination and toxicity, which is size-dependent. Significant efforts are needed before any realistic ecological impact assessment can be undertaken to understand their long-term environmental and health implications better. Keywords. 5.1 Introduction. With the progress in research on microplastics, 5 in size, there are increasing efforts to understand the fate of even smaller plastic particles, the nanoplastics, Al. 2016. The upper size limit of nanoplastics is still being discussed, with the literature variously suggesting either 100 or 1,000, Al. 2018 A. B. Lee Al. 2020 A. Alexander Al. 2016 Al. 2018. A reliable report of the likely presence of nanoplastics in the environment was first put forward by Al. 2016, suggesting that microplastics can fragment under solar radiation. The presence of nanoplastics within soil and crop systems has emerged as a critical issue, Al. 2023, as they potentially present a more insidious form of contamination for multiple reasons, i.e., their enhanced toxicity, their colloidal and stability under a variety of environmental conditions, ability to move across cell membranes, and most importantly, the difficulties in isolating and identifying them in environmental samples. Due to small size and unique physicochemical properties, Al. 2021, Al. 2019, nanoplastics pose distinct challenges to soil health, Wu Al. 2020, Hurley and 2018, crop productivity and human health. They can originate from a variety of sources, both primary and secondary. Primary nanoplastics are intentionally manufactured at the nanoscale for use in industrial applications, Stevens Al. 2013, Al. 2020, including abrasives, inclusions in cosmetics, Al. 2017, fillers in coatings and drug delivery systems, and Prado 2013, Al. 2015, Ali Al. 2020. These particles often enter soil systems through irrigation, land application of sewage sludge, Al. 2020, flooding and atmospheric deposition. Secondary nanoplastics, on the other hand, are formed through the degradation of larger plastic debris in the environment, Al. 2021, and one of the conspicuous sources of smaller plastics is mulch, Al. 2024, Al. 2016, Bao Al. 2024, Al. 2024. Mechanical weathering and biological activity, Al. 2023, can break down in microplastics into nanoplastic particles, Al. 2020, Al. 2019, Al. 2019. Agricultural practices, such as using plastic mulching films and pesticide containers, contribute significantly to soil nanoplastics accumulation. Based on the 88.999% of microplastic retained in sewage sludge, Al. 2020-2022, it can also be a significant source of nanoplastics. However, data on nanoplastic inventories are scarce due to challenges such as matrix interference in their analysis. Sewage sludge is rich in organic compounds, dissolved solids and microorganisms, Al. 2023. Two agricultural practices are primarily responsible for introducing micro and nanoplastics into agricultural soil. The pervasive use of plastics in agriculture exacerbates this issue. For instance, plastic mulches, widely used to conserve moisture and control weeds, degrade over time, releasing microplastics and eventually nanoplastics into the soil, Al. 2023, Al. 2019, Al. 2019, and the application of biosolids as that transfer the NPs present in sewage sludge directly into agricultural soils, and 2018. 5.2 of nanoplastics in soil systems. The of nanoplastics in soil is influenced by their physicochemical properties, including size, shape, surface charge, and due to their small size, nanoplastics have a large surface area-to-volume ratio, which enhances their reactivity and interaction with other soil components. Nanoplastics can adsorb metals on the surface and absorb persistent organics in the bulk, Al. 2013 a B. 2014, potentially altering the chemical properties of the soil. Additionally, their hydrophobic nature can influence soil water retention and transport processes, affecting soil structure and function. The interaction of nanoplastics with the microorganisms in soil can result in changes within the microbial community composition and function, Al. 2024. These interactions can have far-reaching effects on soil fertility and health, as the soil microbes play a pivotal role in maintaining soil structure, nutrient cycling, and decomposition of organic matter, Al. 2024, Al. 2024. The vertical migration of nanoplastics with the irrigation, return flow, or infiltration with precipitation can transport them to deeper soil layers and even to underground aquifers. The mobility of nanoplastics in soil is influenced by several factors, such as soil texture, moisture content, and organic matter. Understanding the fate and transport of nanoplastics in soil is essential for assessing their long-term environmental impacts. Extracting nanoplastics, especially from organic-rich soils, is challenging, Al. 2021, hence the scarcity of nanoplastic inventories in soils, Hurley and 2018. A detailed review by Al. 2021 on agricultural soil in France that has been contaminated with plastic debris for about 30 years appears to be a proof of concept, but lacks an inventory of the site. They extracted nanoparticles from soil samples using soil water extraction with ultrapure water in a 1:4 ratio, stirred at 300 rpm for 72 hours without any pH adjustment. Al. 2021. The samples were filtered on 0.8 cellulose acetate filters. Al. 2024, and the water extract was fractionated utilizing asymmetric flow-field flow fractionation, AFF, where the accumulation wall was a Pease membrane. The use of AFF coupled online to static light scattering, AF4UV SLS, in the study suggests the colloidal populations in two size ranges of 2150 and 15500, whereas the GCMS was used to identify polymers. As in the French agricultural soil amended with sewage sludge, NPs are likely ubiquitous in other regions' agricultural farms and soils. In another study, nanoplastics were reported in the soil profile 055. Al. 2024. Al. 2018 computed a lifetime addition of 2.363 tons per hectare of microplastics to agricultural soils, which Al. 2023 as a nanoplastic and an annual addition rather than a lifetime. Nevertheless, microplastic degradation may result in nanoplastic. Still, its quantification is impossible as the nanoplastic formation rate will depend on the type of polymer, soil type and conditions to microbial degradation, such as organic matter and moisture content. The microplastic inventories were higher in the topsoil, i.e. 78 items 1 compared to 62.5 items 1 in deep soils. Al. 2018. However, Al. 2018 also indicated that the larger plastics were found in the topsoil, while the deeper soils were enriched with smaller microplastic size fractions. With this consideration, should we expect nanoplastics inventories to be higher in the soil beneath? This can partly be due to the movement of NPs through the interstitial spaces in the soil profile, with the irrigation return flow. 5.3 Impact on crop systems. The presence of nanoplastics in soil can directly and indirectly affect crop systems. One primary concern is plants' potential uptake of nanoplastics. Lee al. 2021. The first evidence of nano-bead in crops came in 2012. Al. 2012, where it was reported that 20 beads were taken up quickly by BY2 cells, while the 100 size beads were excluded from uptake by turgescent and cells. Al. 2012. On the other hand, the protoplasts could 1,000 size beads. Studies have shown that nanoplastics and smaller MPs can be absorbed by plant roots. Dong al. 2021. Li al. 2021. Bs. Al. 2022 and translocated to various plant tissues, including leaves. Dong al. 2021. Sun al. 2021. Stems. Al. 2022. Sun al. 2021. Al. 2020 and fruits. Li al. 2020 B. 2021 B. This uptake can occur through various complex mechanisms and pathways, including uptake by root pores from soil colloids and endocytosis. According to a study, Al. 2012, bead was only partially hindered by a specific inhibitor while completely blocked it. This suggests that endocytosis happens through both dependent and independent pathways, supporting the view that independent endocytosis is widespread in plants. The distribution and movement of nanoplastics NPs in soil are significantly influenced by soil colloidal, which governs their transport, retention, and aggregation. Al. 2021. Soil colloids, including clay minerals, organic matter, and metal oxides, interact with NPs through electrostatic forces, van Waals interactions, and cation bridging, affecting mobility. Al. 2021. Nanoplastics adsorb onto colloids, forming that can lead to, as larger aggregates are filtered out in the soil matrix. Al. 2018 B. Al. 2023. Furthermore, environmental factors such as soil pH, moisture content, ionic strength, and organic matter levels influence colloidal stability. Stable colloids can transport attached nanoplastics deeper into the soil profile, potentially reaching groundwater, while conditions promoting flocculation can result in surface deposition. Su al. 2023. Thus, the dynamic interplay between soil colloidal and nanoplastic properties is critical for understanding contaminant dispersion. Al. 2023, with significant implications for environmental risk assessment and management practices. The translocation of nanoplastics within plants raises concerns about their accumulation in edible plant parts, potentially entering the food chain and posing risks to human health. In a study, peat moss sphagnum, exposed to 50 polystyrene beads, demonstrated preferential adsorption of large aggregates on the leaf surface. Additionally, single nanoparticles were within which are empty cells containing pores ranging from 5 to 10 in diameter, and in the cytoplasm. Al. 2018. Nanoplastics ranging in size from 50 to 500 were also detected in garden cress. These nanoparticles obstructed the seed capsule's pores, with a pronounced accumulation on the root hairs. Bosker al. 2019. These particles were also detected on the leaves and epidermal surfaces. Bosker al. 2019. In another study, 20 polystyrene beads were detected within the midrib and veinlets of mung bean, with prominent aggregation observed in the veins, indicating nanoplastic translocation from the soil into the plant body, and in 2020. Additionally, nanoparticles were observed along the vessel walls in the exposed leaves, and in 2020. However, the possibility of atmospheric deposition and endocytosis cannot be ruled out. In another experimental study, 50 and 500 polystyrene beads were applied to soil planted with great duckweed. The nanoplastic beads were predominantly aligned along the root shafts and tips, with a uniform distribution observed across the entire root surface. Al. 2020, suggesting their likely uptake into plants. In another experiment using Allium cepa, garden onion, uptake of 50 polystyrene beads was reported. Al. 2020, where the nanoplastics accumulated within the cellular compartments, including vacuoles and the cytoplasm of the root epidermis, resulting in a reduction in root growth. The of 100 polystyrene beads in bean was reported. Similar to great duckweed, the nanoplastics were found within the root tips. Al. 2019, due to either endocytosis or colloidal transfer, elucidating the potential translocation of nanoplastics from the soil into the plants. Al. 2019. Wheat was exposed to 202 polystyrene beads in another experimental study. These beads were detected in the stems and leaves, providing evidence of the ability of nanoplastics to move through the plants. Al. 2020b. In an additional experiment by the same group, both and sativa lettuce were treated with 202 beads composed of polystyrene and polymethylmethacrylate, PMMA. Nanoplastics were detected in the roots, shoots, xylem, and leaf veins, further indicating effective translocation of nanoplastics from soil to the crop. The presence of nanoplastics within different parts of the crops underscores their ability to impact both plant physiology and food safety. In another study, the barley roots readily absorbed PMMA beads of 96.75058 diameter. Li al. 2021 c. Suggesting the capability of nanoplastic incorporation into plant roots and likely influence in nutrient uptake and effect on plant health. Studies have shown different of positive and negative charges on 200 polystyrene beads in. The negatively charged beads were mainly within the stele of the maturation zone, root tips, and the border cells of the root. Sun al. 2020. Meanwhile, the positively charged beads were on the root hairs and within intercellular spaces. These results underpin the importance of surface charge in controlling the nanoplastic uptake and distribution in plant tissues. In both wheat and exposure to 40 and 1,000 polystyrene beads resulted in a pronounced accumulation along the root surface, with a particularly notable concentration at the root tip. Taylor al. 2020. This evidence, along with other reports, suggests that root tips are the main point of uptake of nanoplastics. The studies included here explicitly highlight the importance of particle size in adhesion uptake and endocytosis, providing significant insights towards the mechanisms of nanoplastic from the soil into monocot and dicot plant species. Evidence of enhanced antioxidant activity and activated carbon metabolism has been reported due to the of 20 polystyrene beads in the roots of sativa rice. Joe al. 2021. Based on the published information, it can be hypothesized with reasonable confidence that nanoplastics in the rhizosphere, al. 2022, can impact plant growth and development. The nanoplastics in the soil region surrounding plant roots can alter root morphology, affecting plant growth. Roy al. 2022. The nanoplastic exposure impedes root elongation and affects root hair growth and nutrient uptake. Con al. 2024, al. 2025. Such physiological changes reduce overall plant health and lower crop yields. Al. 2023. Nanoplastics are also known to affect soil-plant microbe interactions, potentially disrupting beneficial symbiotic relationships, such as those with mycorrhizal fungi and nitrogen-fixing bacteria. Moreover, nanoplastics can interact with other soil contaminants like metals and organics, potentially enhancing their bioavailability and toxicity to plants. For example, nanoplastics can absorb heavy metals. Su al. 2023 b. al. 2024 and organic pollutants. Al. 2021 absorbed by nanoplastics may facilitate their uptake by plant roots and increase their accumulation in plant tissues. Al. 2022 b. This co-contamination can have synergistic effects, exacerbating the toxic effects of pollutants on crops and compromising food safety. Al. 2021 b. 5.4 Concerns. With the extremely large specific surface area, nanoplastics release additives that are added to plastics manufacturing at a faster rate. The lipophilic additives on leaching can penetrate cell membranes and potentially bioaccumulate. Al. 2017. Additionally, residual monomers from producing plastics, solvents, and additives may leach out of the plastic matrix, posing chronic toxicological risks to plants and organisms. Al. 2023 and 2024. Al. 2024. There is an immediate need to assess the leaching rates of these additives from different polymers under ecologically relevant environmental conditions. The available information is not comprehensive enough to evaluate the actual risk it may pose. Hydrophobic contaminants like hydrocarbons, polycyclic aromatic hydrocarbons, PAHs, ethers, PBDEs, biphenyls, PCBs, and pharmaceuticals. Shen al. 2019 in the soil or water are adsorbed over nanoplastics due to their high partition coefficient. Sun al. 2023. Organic contaminants adsorbed on nanoplastics of different sizes. Polymer size in contaminants. Adsorption G references. Polystyrene 70. Biphenyls 180. 6.6110133 a B al. 2014. Biphenyls 126. 2.691076B. Biphenyls 77. 1.051031B. 6.8 a B al. 2016. Benzoapyrene 33.8B. Benzo B 42.6B. Benzo K 33.1B. Benzoanthracene 7.9B. Benzo GHI 20B. 50. Phenanthrene 2B. Ma L 2016. 300-400. Tetracycline 44.8B. 1 Als 2019. Polystyrene pristine 40. 5.6B 3.34C. L 2020. A126C. Polystyrene aged. 5.4B 3.75C. A871C. Polystyrene humic acid pH 6. 300-400. Tetracycline 51B. 1Ls 2019. Polystyrene 2 pH 6. 37.5B. Polystyrene COOH 200. 5.2B. L 2021. 500. 4.3B 3.82C. A 1L1Ns. B isotherm modeling. C kinetic modeling. Experimental data on polystyrene nanoplastic and metal toxicity on biota. Size in metal. Significant findings from treatments of. References 10. Cadmium. The concurrent exposure to nanoparticles NPs and cadmium seed markedly accelerated mortality in grass carp, with varying degrees of tissue damage observed in the gills, liver, kidneys, and muscles, most severe at concentrations of 20 L1 seed combined with 300 L1 NP. Additionally, treatment with NPs alone at 30 L1 led to increased superoxide SOD activity in both the kidney and liver. In contrast, peroxidase POD activity was elevated exclusively in the kidney. L 2022 C 100 spherical. At 0.05 seed L1, there was a significant reduction in Euglena gracilis growth, enhanced toxicity with synergistic effects. Metabolic disorders and oxidative stress are the main toxic mechanisms. L 2022 500 spherical. Copper. Significant increase in toxicity compared to nanoplastic or alone. Oxidative stress, cytoplasmic vacuolation and destruction of chloroplasts in chlorella. TJ65 and NIES 35. 1 ALS 2021 87.17106 spherical. No adsorption of copper ions was detected on PSCOOH nanoparticles. However, changes in their surface charge and hydrodynamic diameter indicate the formation of an ecocorona and a subsequent loss of the cell's native morphology at an exposure level of 10 psL1 in the presence of copper. Furthermore, the nanoparticle's ability to interact with exudates from and adhere to its cell wall suggests that their transfer through the food chain is plausible. L 2019 50 and 55 spherical. Exposure suppressed the growth of, intensifying inhibition as exposure duration and concentration increased. Oxidative damage was evident at PSNP concentrations exceeding 50 L1 and levels of at least 1.5 L1, with the combined exposures exhibiting a synergistic effect. L 2022 100 spherical. Zinc. At environmentally relevant concentrations, nanoplastics and zinc do not exhibit a combined interactive effect on communities. However, zinc alone induces a discernible alteration in community structure. In contrast, nanoplastics appear to have no significant impact. Zinc exposure leads to a marked initial reduction in phototrophic microorganisms, though photosynthetic activity eventually recovers, accompanied by a shift in the dominant taxa from to chlorophytes. L 2022 arsenic. Consequent to non-environmental concentrations, 1L, there was an interactive effect of nanoplastics and arsenic. Fresh weight and growth rates were significantly reduced. However, the negative effects at lower concentrations were mainly due to arsenic exposure, responded to stress by regulating amino acids and organic acids. Li al. 2023. The synergistic effect of nanoplastics and arsenic was higher than their single toxicity on end. The nanoplastics were observed in the leaf cells of these submerged macrophytes. Tang al. 2022. Lid. In intestinal cells, co-exposure to nanoparticles at 20 and 200 L1 alongside 50L1 lead, demonstrated that the 200L1 nanoparticle treatment had the most pronounced impact on macrophages, whereas lead exposure predominantly affected enterocytes. L 2022 50 200 500 Spherical gold. Smaller nanoparticles were observed to penetrate both developing embryos and their chorion. Exposure to nanoplastics resulted in modest alterations in survival, hatching rates, developmental abnormalities, and cell death. The synergistic effects were notably more pronounced with increasing dose and decreasing particle size. Signs of oxidative stress and mitochondrial damage were also reported. Li al. 2019. 1000 spherical. Chromium. NP1820 and VI at 2 and 5 ppm for 72H showed low mortality of Daphnia magna at NP13 3%, 2 ppm IV individually, but the synergistic effect of 2 led to 74.5 mortality, and when concentration was 5 ppm absolute mortality was observed. Microbial diversity was changed significantly. L. 2022. The impacts of nanoplastics on soil and crop systems are not yet fully understood, but emerging evidence suggests that they can potentially pose significant risks to soil microbiota and crops. Nanoplastics can induce oxidative stress in plants by producing reactive oxygen species, ROS, that cause cellular damage. This stress can impair photosynthesis, reduce growth, decrease crop productivity, affecting germination, flowering, and fruiting in plant. The potential for nanoplastics to accumulate in the food chain is also a realistic concern. If nanoplastics are taken up by crops, they could be transferred to herbivores and subsequently to higher trophic levels, including humans. The long-term health implications of chronic exposure to nanoplastics through food consumption are still largely unknown, but the potential for and biomagnification warrants serious consideration. Al. 2023 Miller al. 2020 Gupta al. 2022 5.5 Knowledge gaps, research needs and concerns. The pyrolysis product of different polymers with their MZ signals and retention index after al. 2020 retention index. MZ polymer 1 1091 41 55 70 97 111 154 polyethylene 1 1393 41 55 97 125 196 1 1994 43 55 83 97 280 24 1 843 39 41 43 55 70 83 126 polypropylene 246 1 1082 41 43 55 69 83 111 125 168 2468 1 isotactic 1311 41 43 55 69 111 125 154 167 2468 1 syndiotactic 1330 41 43 55 69 111 125 154 167 3 butane 13 1761 65 91 104 115 130 193 208 polystyrene 5 135 25 14 65 91 a 117 194 207 312 styrene monomer 8.5 104 toluene 7 660 39 50 51 52 77 78 polyvinyl chloride naphthalene 11.3 128. Naphthalene 1-methyl, 12.3. 142. Methyl, 711. 39, 41, 59, 69, 99, 100. Polymethyl methacrylate, 1276. 30, 42, 55, 56, 84, 85, 113. Nylon 6, N5-hex 1943. 30, 41, 55, 69, 100, 114, 154, 168, 208. 6N5, 2660. 30, 43, 55, 114, 167, 224, 267. 799. 39, 41, 42, 55, 56, 84. Nylon 66. 1200. 39, 40, 41, 51, 52, 54, 55, 68. 1827 Dione. 23, 28. 30, 41, 55, 98, 112, 140, 198, 226. 4, 841. 39, 54, 79, 80, 93. Acrylonitrile butadiene styrene. 2-methylene 4. 1363. 39, 65, 91, 92, 157. 44. 1446. 77, 91, 103, 115, 117, 130, 142, 157. 2-methylene 4. 1873. 91, 104, 117, 144, 182, 210. 244. 2234. 91, 105, 115, 118, 156, 170, 261. 1524. 50, 76, 103, 120, 135, 163, 194. Polyethylene terephthalate. 2110. 133, 211, 241, 242, 256. Polycarbonate. 44N. 2282. 106, 120, 182, 196, 211, 212. Polyurethane. A compounds used to calculate the signal-to-noise ratios by extracting the MZ profiles of the signal. Beer attention time. The complex interactions between nanoplastics and soil constituents, including organic matter, minerals, and microbes, are not yet fully understood. Long-term studies also need to evaluate the chronic effects of nanoplastics on soil health, crop productivity, and food safety. Research on the potential for nanoplastics to interact with other environmental stressors like thermal and microbial degradation and changes in soil pH is vital. Developing sustainable agricultural practices that minimize plastic use and reduce nanoplastics' input into the terrestrial environment is crucial for mitigating their impacts. A significant limitation of the PyroGCMS is its inability to provide information on the size, count, and shape of the nanoplastics in a sample. The nanoplastic size is critical in assessing their toxicity. The higher surface-to-volume ratio of smaller particles has increased potential toxicity. The smaller nanoplastics have enhanced capability to penetrate biological membranes, con. Al. 2024, but they also translocate and accumulate in tissues away from their point of contact or entry, leading to amplified toxicological effects. The other factor that enhances the toxicity of smaller nanoplastics is their enhanced reactive surface, which binds other hydrophobic contaminants and acts as a vector for them. The limited information on the penetration capabilities of nanoplastics hinders the development of simulation models to predict their distribution and accumulation in crops and microorganisms realistically. Such models are key to understanding chronic and acute health risks associated with nanoplastic exposure. In the absence of nanoplastic inventories and size information, it is challenging to develop accurate models that can predict the potential health impacts of these particles over time. Elevated nanoplastic concentrations in soil can lead to more significant exposure for microorganisms and, in turn, can compromise crop vitality. The PyroGCMS is a potent tool for identifying polymers, but its inability to provide quantitative size and morphological information on nanoplastics complicates the exposure assessment of soil microbes and invertebrates, particularly in terms of nanoplastic effect at the molecular and cellular level. The toxicological outcomes and capability for long-term monitoring and assessment, in the absence of such size and count information, have high uncertainties. Also, the data generated is often incomparable, as it is usually reported in terms of the concentration of polymer per unit mass, rather than the number of particles per unit mass or area reported for microplastics. The experimental toxicological data on nanoplastics is often shown to be size-dependent. The surface area to volume ratio of nanoplastics is a key determinant of their reactivity and potential to be transport vectors for contaminants of concern. Smaller nanoplastics induce higher oxidative stress and inflammation in biological systems, Joe al. 2023 Increasing Toxicity, al. 2023 Li al. 2024 al. 2023 al. 2023. 5.6 Conclusion. Nanoplastics are a significant concern of the Anthropocene, posing an emerging challenge to the soil and crop systems. The nanoplastics have potentially far-reaching consequences for long-term soil health, crop vitality and productivity, and food safety issues. Nanoplastic research is still in its initial stages due to technological limitations in identifying them in environmental samples. The available evidence, primarily based on experimental data, underpins the significant soil-plant interactions, negative crop growth, and food safety concerns emanating from their presence in various plant tissues. A multidisciplinary team of environmental scientists, agronomists, toxicologists, and policymakers must address this multifaceted challenge. To develop effective management and mitigation strategies for nanoplastic risks in soil and crop systems, data on the sources, in soil, and response to microbial interactions are needed. The technical limitations of the PyroGCMS in providing size and count numbers information in environmental samples hamper our ability to assess toxicity accurately. Moreover, in the absence of size information, the surface-to-volume ratio of nanoplastics, its reactive surface and toxicity are questionable. Since risk assessments typically rely on detailed information about the particle's chemical characteristics, the lack of such details compromises the efficacy risk assessment. The other concerns emanate from the purity of the media, laboratory blanks, and lack of standard reference material. Most researchers have not reported background concentrations, hence the data cannot be corrected. To complement the information on polymer types generated by PyroGCMS and to overcome the limitations, it is prudent to explore alternative and complementary techniques like dynamic light scattering, DLS, and nanoparticle tracking analysis, NTA, that can provide information on the nanoplastic size distribution and concentration in a sample. It will be interesting to assess how these techniques can be used to obtain a more comprehensive understanding of nanoplastics in environmental samples and to evaluate their realistic toxicological implications. Furthermore, the inability to assess the size and number of nanoplastics limits the ability to establish exposure-response relationships, which are critical for determining safe levels of exposure and developing regulatory guidelines. Without this information, it is challenging to develop comprehensive risk assessments that fully account for the potential health impacts of nanoplastics. Also, the data produced is incomparable to most of the data on microplastics in published literature. It is prudent to mention that a large volume of literature on nanoplastics has inappropriately combined the information on micronanoplastics to the extent that some information is inaccurate and misleading. We have highlighted some of these in this perspective. The authors thank the Kuwait Institute for Scientific Research and the International Atomic Energy Agency for their support. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: M.Al. 2021, Biointeraction of nano and bulk lanthanum and ytterbium oxides in soil system, biochemical, genetic, and effects on. J. Hazard Mater 415 125574 PubMed. Alexander J. Al. 2016, Presence of Microplastics and Nanoplastics in Food, with particular focus on seafood. EFSA Panel on Contaminants in the Food Chain. CONTAM. EFSA J. 144501. Ali Al. 2020, Advances in Nanoparticles as Anti-Cancer Drug Delivery Vector, Need of This Century. Farm 2615-1637-1649 PubMed. OS Al. 2018, Microplastics and Nanoplastics in Aquatic Environments, Aggregation, Deposition, and Enhanced Contaminant Transport. Environ Technol 52-1704-1724 PubMed. VK Al. 2024, Effects of Microplastics on Soil Microorganisms and Microbial Functions in Nutrients and Carbon Cycling, a Review. Total Environ 924-17143-5 PubMed. AF Al. 2019, Mechanical Formation of Micro and Nanoplastic Materials for Environmental Studies in Agricultural Ecosystems. Total Environ 680-5109-71106 PubMed. T. Al. 2023, Nanoplastic Occurrence, Transformation, and Toxicity, a Review. Environ 2113-63381. V. Al. 2012, Uptake of Fluorescent Nanobeads into BY2 cells involves dependent and independent endocytosis. FEBS 586-236-263632 PubMed. Bao X. Al. 2024, Microplastics derived from plastic mulch films and their carrier function effect on the environmental risk of pesticides. Total Environ 924-171472 PubMed. A. Al. 2019, Combined Effects of Nanoplastics and Copper on the Alga. Toxicol 210-179-187 PubMed. Bosker T. Al. 2019, Microplastics accumulate on pores in seed capsule and delay germination and root growth of the terrestrial vascular plant. Chemosphere 226-774-781 PubMed. Z. Al. 2023, Biological Degradation of Plastics and Microplastics, a recent perspective on associated mechanisms and influencing factors. Microorganisms 117166-1 PubMed Central. J. Al. 2022, Enhanced Toxicity due to Polystyrene Nanoplastics and Cadmium Co-Exposure, from the perspective of physiological and profiles. J. Hazard Mater 427-12793-7 PubMed. F. Al. 2018, Evidence on the Effectiveness of Mosses for of Microplastics in Fresh Water Environment. Chemosphere 205-17 PubMed. S. Al. 2023, Analysis of Micro and Nanoplastics in Treatment Plants, Key Steps and Environmental Risk Considerations. Environ Assess 195-12-1483 PubMed Central. E. Al. 2024, Of Micronanoplastics and Heavy Metals in Soil Systems, Mechanism and Implication. In Management of Micro and Nanoplastics in Soil and Biosolids. Springer Cam 163-2-01. Y and YJ 2020, Nanoplastic ingestion induces behavioral disorders in terrestrial snails, trophic transfer effects via vascular plants. Environ Nano 739-75983. G.Al. 2022, Effects of Micro-Nanoplastics on Higher Plants and the Rhizosphere Environment. Total Environ 807 1150841 PubMed. G.Al. 2022b, Effects of Micro-Nanoplastics on Higher Plants and the Rhizosphere Environment. Total Environ 807 150841 PubMed. X.Al. 2022, C. Physiological Response and Oxidative Stress of Grass Carp under Single and Combined Toxicity of Polystyrene Microplastics and Cadmium. Environ 245 114080 PubMed. Ga.Al. 2019, Size and Shape Matter, a preliminary analysis of microplastic sampling technique in seawater studies with implications for ecological risk assessment. Total Environ 667 124 132 PubMed. M.Al. 2020, Nanoplastics on the Coast Exposed to the North Atlantic Gyre, Evidence and Traceability. Nano-Impact 2100262. Dongwei-Al. 2021, Uptake of Microplastics by Carrots in Presence of as III, Combined Toxic Effects. J. Hazard Mater 411 125055 PubMed. LC.Al. 2020, Plastic Particles Adsorb to the Roots of Vascular Plant, but do not impair growth. 5-13745. D.A.Al. 2024, Microplastics from Agricultural Mulch Films, Biodegradation and in Systems. Total Environ 912 169287 PubMed. S.Al. 2020, Long-Term Assessment of Nanoplastic Particle and Microplastic Fiber Flux through a Pilot Treatment Plant using Metal-Doped Plastics. Water Res 182 11586 0 PubMed. ZY.Al. 2022, Single and Combined Toxicity of Polystyrene Nanoplastics and Copperon. Perspectives from Growth Inhibition, Chlorophyll Content and Oxidative Stress. Total Environ 829 15457 1 PubMed. Y.Al. 2023, Toxicity of Microplastics and Nanoplastics, Invisible Killers of Female Fertility and Offspring Health. Front 14 1254886 PubMed Central. J.Al. 2016, Marine Plastic Litter, the Unanalyzed Nanofraction. Environ Nano 32346 350. J.Al. 2018, A Current Opinion, What is a Nanoplastic? Environ 235 1030 PubMed. J.Al. 2018b, Current Opinion, What is a Nanoplastic? Environ 235 1030 1034 PubMed. J.Al. 2021, Nanoplastics are neither microplastics nor engineered nanoparticles. 1655-01507 PubMed. L.Al. 2020, Exploring the Interaction between Polystyrene Nanoplastics and Allium cepa during germination, Internalization in Root Cells, Induction of Toxicity and Oxidative Stress. Plant 149 17177 PubMed. Gupta C.Al. 2022, and Toxicity of Polystyrene Nanoplastics on Marine and Terrestrial Organisms with Possible Remediation Strategies, a review. Environ Adv 8100227. LMNN 2017, Are there nanoplastics in your personal care products? Environ Technol 4728285. Hurley RR.L. 2018, Fate and Occurrence of Micro-Nanoplastics in Soils, Knowledge Gaps and Possible Risks. Environ Health 16116. K.Al. 2025, Impact of Polystyrene Nanoplastics on Physiology, Nutrient Uptake, and Root System Architecture of Grown Citrus Plants. Nano-Impact 37100-536 PubMed. L.Al. 2023, Microplastic Stress in Plants, Effects on Plant Growth and Their Remediations. Front Plant 1412264884 PubMed Central. X.Al. 2019, End of Polystyrene Microplastics on Higher Plant. Environ 258 31838 PubMed. BKKK S. Fowler SW 2023, Microplastics MPs in Marine Food Chains, Is it a food safety issue? In F. Lead, Advances in Food and Nutrition Research. Academic Press 101-140. Jones N.R. Al. 2024. Identifying Laboratory Sources of Microplastic and Nanoplastic Contamination from the Air, Water, and Consumables. J. Hazard Mater 465-133-276 PubMed. Khan A.R. Al. 2024. Micro-nanoplastics. Critical review of their impacts on plants, interactions with other contaminants, antibiotics, heavy metals, and polycyclic aromatic hydrocarbons, and management strategies. Total Environ 912-16942-0 PubMed. J.H. Al. 2017, Microplastics as a Vector of Hydrophobic Contaminants, Importance of Hydrophobic Additives. Environ Assess, 13-3494-499 PubMed. Lee W.S. Al. 2019, of polystyrene nanoplastics and their effect on the toxicity of ions in embryos. Nanoscale 11-731-733-185 PubMed. Lee J.Y. Al. 2024, a comprehensive review of urban microplastic pollution sources, environment and human health impacts and regulatory efforts. Total Environ 946-17429-7 PubMed. Lee P. Al. 2020, Analytical Methods and Environmental Processes of Nanoplastics. J. Environ, China, 948899 PubMed. Lee L. Al. 2020 B. Effective Uptake of Plastics by Crop Plants via Crack Entry Mode. Sustain 3-11-9-29-937. Lee C. Al. 2021, A Quantification of Nanoplastic Uptake in Cucumber Plants by Pyrolysis Gas Chromatography Mass Spectrometry. Environ Technol 88633-638. Lee Z. Al. 2021 B. The Distribution and Impact of Polystyrene Nanoplastics on Cucumber Plants. Environ Raise 2813-160-42-16053. Lee S. Al. 2021 C. Polystyrene microplastics disturb the redox homeostasis, carbohydrate metabolism, and regulatory network in barley. J. Hazard Mater 415-1256-14 PubMed. Lee J. Al. 2023 Single and Combined Toxicity of Polystyrene Nanoplastics and Arsenic on Submerged Plant, L. Plant, 194-513-523 PubMed. J. Al. 2020, Impact of Polystyrene Nanoplastics, PSNPs on Seed Germination and Seedling Growth of Wheat, L. J. Hazard Mater 385-12162-0 PubMed. J. Al. 2020b, Do polystyrene nanoplastics affect the toxicity of cadmium to wheat, L. Environ 263-11449-8 PubMed. L. R. A. A. 2016, Sorption of Polycyclic Aromatic Hydrocarbons to Polystyrene Nanoplastic. Environ Toxicol 35-71650-1655 PubMed. M. Al. 2018, A Microplastic and Mesoplastic Pollution in Farmland Soils in Suburbs of Shanghai, China. Environ 242-855-862 PubMed. J. Al. 2018b, Polystyrene Nanoplastics Enhanced Contaminant Transport, Role of Irreversible Adsorption in Glassy Polymeric Domain. Environ Technol 52526-7726-85 PubMed. Y. Al. 2021, A Transport and Transformation of Microplastics and Nanoplastics in the Soil Environment, A Critical Review. Soil Use 3722-24242. Q. Al. 2021 B. Microplastics and Nanoplastics, Emerging Contaminants in Food. J. Agric Food, 6936-10450-10468 PubMed. Y. Al. 2022, Uptake and Translocation of Nanomicroplastics by Rice Seedlings, Evidence from a Hydroponic Experiment. J. Hazard Mater 421-126700 PubMed. Ma. Y. Al. 2016, Effects of Nanoplastics and Microplastics on Toxicity and Environmental Fate of Phenanthrene in Fresh Water. Environ 219-166-173 PubMed. S. Prado M. 2013, Nanomaterials for Nanomedicine. ACS Med 42 147 149 PubMed. K. al. 2020, Identification Algorithm for Polymer Mixtures based on GCMS and its application for microplastic analysis in environmental samples. J. Anal pyrolysis 149 104834. M.D. 2018 Soil Pollution, A Hidden Reality. FAO Rome. T.O. Marx Fa Hansel Fa 2017 Pyrolysis Gas Chromatography, Mass Spectrometry Retention Index of Pyrolysis Products of Materials. J. Anal pyrolysis 126 332 336. Miller M.E. M. Kroon F.J. 2020, and Biomagnification of Microplastics in Marine Organisms, a review and meta-analysis of current data. Pilo S. 11510 E0240792, PubMed Central. S. al. 2024, Microplastics and Nanoplastics in Soil, Sources, Impacts, and Solutions for Soil Health and Environmental Sustainability. J. Environ 53, N. E.L. al. 2018, An Overview of Microplastic and Nanoplastic Pollution in Total Environ 627, 1377 1388 PubMed. L. Futter M. S. 2016, Are Agricultural Soils Dumps for Microplastics of Urban Origin? Environ Technol 5021, 077710779 PubMed. KCA 2024, Environmental Occurrence and Risks of Plastic Leachates in Aquatic and Terrestrial Environments. Total Environ 954 17672, 8 PubMed. R. al. 2023 Nanoplastics in the Soil Environment, Analytical Methods, Occurrence, Fate, and Ecological Implications. Environ 317 120 788 PubMed. E. al. 2023, Evaluation of Nanoplastics, Carbon Nanotubes, Fullerenes, and Graphene Family Materials. Environ 173 107650 PubMed. ACJ 2023, The Environmental Fate of Nanoplastics, What We Know and What We Need to Know About Aggregation. NanoImpact 29 100453 PubMed. SHKT 2024, Environmental Fate of Microplastics and Common Polymer Additives in Non-Biodegradable Plastic Mulch, Applied Agricultural Soils. Environ 363 125249 PubMed. CM al. 2013, A Classify Plastic Waste as Hazardous. Nature 494 169 PubMed. CM al. 2013b, Ingested plastic transfers hazardous chemicals to fish and induces hepatic stress. Rep 33263 PubMed Central. CM/BT SJ 2014, Long-term sorption of metals is similar among plastic types, implications for plastic debris in aquatic environments. Pilo S191E85433 PubMed Central. AG al. 2020, 3D printer waste, a new source of nanoplastic pollutants. Environ 267 115609 PubMed. Roy T. TK M. 2022, Microplastic Nanoplastic Toxicity in Plants, an Imminent Concern. Environ Assess 195 127 PubMed Central. Y. al. 2024, Micro and Nanoplastics in Agricultural Soils, Assessing Impacts and Navigating Mitigation. Total Environ 930 117295 1 PubMed. Shen M. al. 2019, Recent Advances in Toxicological Research of Nanoplastics in the Environment, a Review. Environ 252 5 11521 PubMed. D.Z. Bedford N. 2015 9 Materials. In D.Z. Bedford N. Nanomaterials and Devices. William Publishing, Oxford, 215-253. G. al. 2022, Microbial Community Shifts Induced by Plastic and Zinc as Substitutes of Tire Abrasion. Rep 12 118684 PubMed Central. Stevens B. al. 2013, Particle Emissions from Desktop 3D Printers. Environ 79 334 339. Sun XD al. 2020, differentially charged nanoplastics demonstrate distinct accumulation in 15755 PubMed. Sun H. al. 2021, foliar uptake and leaf-to-root translocation of nanoplastics with different coating charge in maize plants. J. Hazard Mater 416, 125854 PubMed. Sun N. al. 2023, combined toxicity of micro-nanoplastics loaded with environmental pollutants to organisms and cells, role, effects, and mechanism. Environ 171, 1077111 PubMed. Tang N. al. 2022, the adsorption of arsenic on micro and nanoplastics intensifies the toxic effect on submerged macrophytes. Environ 311, 119896 PubMed. Taylor S.E. al. 2020, polystyrene nano and microplastic accumulation at and wheat root cap cells, but no evidence for uptake into roots. Environ Nano 7719421953. S. Fowler S.W. M. 2020, an assessment of microplastic inputs into the aquatic environment from streams. Mar Bull 161 11538 PubMed. S. al. 2022, Microplastics in Kuwait Streams. Sustainability 1423 15817. A.S. S. Fowler S.W. 2023, Environmental Microplastics, a significant pollutant of the Anthropocene. In Kane C. A.M. Microplastic Sources, Fate and Solution. Springer Nature Singapore, 89105. JEC-R 2022, the stressful effects of microplastics associated with chromium VI on the microbiota of Daphnia magna. Front Environ 10875512. ICJAF AA 2014, strong sorption of PCBs to nanoplastics, microplastics, carbon nanotubes, and fullerenes. Environ Technol 489486948776 PubMed. A. al. 2021, nanoplastic occurrence in a soil amended with plastic debris. Chemosphere 262, 127784 PubMed. A. al. 2024, nanomicroplastic mobility in soil, metallic additives and isotopes as potential tracers. J. Hazard Mater 476 135 153 PubMed. Wan T. al. 2019, a spectroscopic and theoretical investigation of interaction mechanisms of tetracycline and polystyrene nanospheres under different conditions. Environ 249 3984 5 PubMed. Wan J.K. al. 2021, influence of polystyrene microplastic and nanoplastic on copper toxicity in 2. Environ Raise 28 25 33649 33668. L. al. 2020, Environmental Fate, Toxicity and Risk Management Strategies of Nanoplastics in the Environment, Current Status and Future Perspectives. J. Hazard Mater 401 123415 PubMed Central. Wu X. al. 2020, Transport of Polystyrene Nanoplastics in Natural Soils, Effect of Soil Properties, Ionic Strength and Cation Type. Total Environ 707, 136065 PubMed. Y. al. 2020, Interfacial Interaction between Micro-Nanoplastics and Typical PPCPs and Nanoplastics Removal via from an Aqueous Solution. Water Raise 184 116100 PubMed. Su J. al. 2023, A Nano and Microplastic Transport in Soil and Groundwater Environments, Sources, Behaviors, Theories, and Models. Total Environ 904 16664 1 PubMed. Su G. X. Y. 2023 B. Different Effects and Mechanisms of Polystyrene Micro and Nanoplastics on the Uptake of Heavy Metals, and Seed by Lettuce, Sativa L. Environ 316, 120656 PubMed. M. al. 2021, Adsorption of to nano-sized polystyrene plastic, Kinetics, Thermochemistry, and Toxicity. Total Environ 751 42370 PubMed. J. al. 2022, Heterogeneity Effects of Nanoplastics and Laid on Intestinal Cells Identified by Single-Cell Sequencing. Chemosphere 289 133133 PubMed. M. al. 2019, microplastics from mulching film is a distinct habitat for bacteria in farmland soil. Total Environ 680, 847478 PubMed. Joe CQ Al 2021, Response of Rice, Sativa L Roots to Nanoplastic Treatment at Seedling Stage. J. Hazard Mater 400-112-3412 PubMed. Joe Y. Al 2023, Nanoplastics induces oxidative stress and triggers lysosome-associated immune defensive cell death in the earthworm. Environ 174-107-899 PubMed. 6. Sources of microplastics in the soil and use of laser, direct infrared imaging for microplastic detection. Abstract. Agricultural soils have emerged as critical sinks for microplastics MPs, with contamination driven mainly by plastic mulch films, sewage sludge, irrigation, organic fertilizers, and atmospheric deposition. These MPs, ranging from 1 to 5, perturb the soil ecosystems by absorbing heavy metals, organic pollutants, and antibiotic resistance genes while disrupting soil structure, microbial communities, and plant health. Despite their pervasive presence, conventional detection methods, such as FTIR and Raman spectroscopy, remain intensive, making any large-scale assessments challenging. This study underscores the transformative potential of laser direct infrared (LDIR) imaging, a high-throughput technique leveraging quantum cascade lasers and rapid spectral scanning in the 975-1800-1 range to characterize MPs by polymer type, size, and morphology with minimal pretreatment. Global data highlight alarming MP accumulation in sludge-amended soils, retaining up to 3.5 mpg1 after 5 years, while mulched farmlands in China exhibit 1.08 mpg1 after 24 years. Untreated irrigation further introduces MPM3 into soils, exacerbating contamination. LDIR's efficiency, demonstrated by 80-100% recovery rates for 200-500 particles and analysis times of 3 hours per sample, addresses critical gaps in current protocols. Its integration with machine learning and expanding spectral libraries promises enhanced precision for sub-10 particles, enabling scalable monitoring. By advancing detection accuracy, an LDIR emerges as a pivotal tool for elucidating MP dynamics, guiding policy, and mitigating risks to soil health, biodiversity, and food security in the face of this escalating environmental crisis. Keywords. 6.1 Introduction. The agricultural soils are becoming a gigantic sink of microplastics, MPs, Fan Al. 2023 due to the large-scale use of plastic mulch films, Al. 2024, Al. 2024, Al. 2024, Bow Al. 2024, Organic Fertilizers, Al. 2022, Sewage Sludge Application Ding Al. 2020, GUI Al. 2021, Al. 2023 and 2024, Al. 2024 and use of for irrigation, Al. 2020 a 2022 a 2023, Al. 2021, Li Al. 2024. The compositional diversity of the polymers is another complex issue as more and more polymers are developed to meet the ever-increasing demand in terms of durability, lightweight, affordability, and water and weather resistance. The MPs possess traits that magnify their ecological threat: minuscule size between 15000, vast surface area, and hydrophobic properties, Al. 1989, Al. 2020b, 2022b, Al. 2023. These characteristics enable them to absorb toxic pollutants, including heavy metals, Al. 2018, Al. 2023 organic contaminants, Al. 2023 and antibiotic resistance genes, Al. 2023b acting as vectors for environmental contamination. Their mobility via wind and water further amplifies their reach, allowing them to infiltrate soils through agricultural practices, irrigation, flooding, or atmospheric deposition. Once embedded in terrestrial ecosystems, microplastics disrupt soil integrity by altering porosity, pH, and nutrient cycles, Al. 2022, and destabilizing microbial communities critical for soil fertility, al. 2019 of. More alarmingly, microplastics impair plant health by obstructing seed germination, stunting root and shoot growth, and infiltrating plant tissues, even translocating nanoplastics as small as 50 into cellular structures, al. 2023, Su al. 2023, a Sun al. 2023. This threatens food chains, ultimately jeopardizing human health. Compounding these risks, microplastics synergize with adsorbed pollutants, exacerbating soil degradation and creating persistent ecological hazards, al. 2019 b. Despite the growing volume of literature, with currently over 900 research articles on soil microplastics, critical gaps persist. Most studies have used methods like stereo microscopy, fluorescence microscopy, ATR Fourier transform infrared, FTIR spectroscopy, al. 2022, RAMAN spectroscopy, al. 2021, and scanning electron microscopy, al. 2021 for MP identification, often overlooking advanced detection methods such as laser direct infrared imaging or matrix-assisted laser desorption ionization, MALDITOF, that can give information on size, shape, and polymer type. Understanding the sources, distribution, and impacts of soil microplastics is a pressing environmental issue. Refining MP detection protocols and unraveling their ecological consequences can safeguard soil health, which is the foundation of food security, biodiversity, and planetary resilience against this pervasive threat. The existing techniques for isolating microplastics from complex soil matrices remain inconsistent and underdeveloped. Despite efforts made towards developing a standardized methodology for the extraction and detection of MPs, critical gaps exist and improvement is needed. A standard has been developed for soil sampling, i.e. ISO 18401-022017, Selection and Application of Sampling Techniques, ISO 2017. However, due to differences in processing techniques for MPs, a unified approach is yet to be agreed upon to assess global contamination patterns and inform mitigation strategies. Most of the popularly applied techniques are quite time-consuming and intensive, which prompts us to suggest using the laser direct infrared LDIR imaging technique, AL. 2024 as a plausible alternative, as it is both fast and reliable. Laser direct infrared imaging system employs an infrared IR microscope spectrometer linked to a high-speed scanning mechanism, utilizing a rapidly tunable quantum cascade laser, QCL, as the light source. LDIR's imaging system can analyze particle count, size, and morphology, while the spectrometer identifies polymer types, AL. 2020. The QCL is semiconductor-based and generates light through electron tunneling across engineered quantum wells. Here, photon wavelength is controlled by the thickness and arrangement of semiconductor layers rather than material composition, stock AL. 2019. This design enables rapid wavelength tuning, surpassing traditional based systems in speed and precision. The LDIR combines the QCL with a thermoelectrically cooled mercury-cadmium telluride MCT detector and dynamic optics, operating in two modes, i.e. spatial scanning, where the laser remains at a fixed wavelength while the objective scans the sample. Each pixel is analyzed in 4D, enabling rapid large-area mapping. The other mode is the spectral scanning, where the laser sweeps across wavelengths at a fixed sample position, capturing a full mid-infrared spectrum, 1800-975-1, in under 1 second. For the analysis of microplastic, both modes were utilized. Initial spatial scans, 145-1100 area, identified particles, recording their size, shape, and position. Subsequent spectral scans at each particle's location generated mid-IR spectra, cross-referenced with a custom spectral library derived from published databases, AL. 2018. More and more spectra are added to this database, further enhancing the capability and utility of the process to identify polymers. Particles under 30 triggered automated refocusing, extending per particle analysis to 8 seconds. 6.2 Sources of microplastics in soil. The soil is a sink for a gigantic amount of microplastics that emanate from different sources not limited to plastic degradation in waste dumps, sewage sludge application to soils, plastic mulch films used in agricultural farms, used for irrigation, organic fertilizers, and atmospheric deposition. 6.2.1 Sewage sludge application. Several studies have highlighted AL. 2020 a 2022 AL. 2021 AL. 2018 Lee Al. 2018 Larry's Al. 2018 Al. 2015-2017 Al. 2017 Al. 2019 and 2014 Al. 2016 The increased presence of microplastics in sludge. In our previous study, we computed that 88.999% of MPs are retained in sludge, Al. 2020, in another study, a comparable estimate was given by Sun Al. 2019, indicating 98.3% retention of MPs in sludge. In a major treatment plant, WWTP, in Vancouver, British Columbia, the primary sludge has 14.963 mpg1, and the secondary sludge has 4.428 mpg1, Al. 2018. In a study on 28 WWTPs in China, 22.712 mpg1 was reported in sludge, Lee Al. 2018, whereas in sludge from WWTP Finland, the load was 27.347 mpg1, and in WWTP, the microplastics in activated sludge were 23.42 mpg1, and in digested sludge 170.9287 mpg1, Larry's Al. 2018. Microplastics in dry sludge from WWTP Finland are 186.260 mpg1, Al. 2017, while in WWTP Germany it was 1 mpg1, whereas in WWTP Germany the concentration was 24 mpg1, Al. 2017. Al. 2019 found 59.5 mpg1 in sludge from a WWTP in northern Italy. The MPs in sludge reported from and Amsterdam West WWTPs, Netherlands, were 664.10, 510 and 760 MP1, Al. 2017, respectively. Microplastics in sludge and sewage from WWTP, Sweden, were 16.7196 mpg1, and 2014. These data provide an idea of the magnanimous quantity of MPs that exist in sludge, and their application to agricultural soils can result in accumulation. Annual microplastic input from sludge is estimated at 0.63430 million tons in Europe and 0.44300 million tons in North America, Al. 2018. In China, this figure reaches approximately 1.561014 particles per year, Li Al. 28 ton B. The recurrent sludge application results in microplastic buildup in the soil, Al. 2021. After 5 years of sludge application, microplastic densities can average 3.5 mpg1, Al. 2019, significantly higher than soils free of sludge application, Al. 2020. The sludge-applied soil acts as a sink for MPs, changing its chemical characteristics like bulk density, porosity, and permeability. It also affects the level of metals and organic pollutants in the soil. Some researchers have suggested the cleanup of microplastics from the soil by incineration, Su Al. 2023b, which is quite impractical. Another feasible alternative is hydrothermal treatment of sludge, heating it to 200-300 C. However, this is cost-intensive. More research is needed to assess the ecological implications of adding sludge. While a study revealed that crops like wheat and lettuce can absorb microplastics from sludge-amended soils, posing food safety risk, the mechanism of uptake is still not clearly elucidated. The evidence for MPs affecting soil properties is equally strong to the data that suggest minimal negative effects and considerable benefits of adding sludge that provides the nutrient input and organic content to the soil. A review emphasized the lack of global standards for microplastics in sludge, with only Germany and Switzerland setting provisional guidelines. Al. 2020, there is an eminent need for an environmental and social impact assessment of sludge addition to agricultural soils, and 2024. 622 Irrigation. The omnipresence and prevalence of MPs in are well documented. Although the WWTPs are known to trap MPs in sludge and reduce the concentration in effluent, a considerable amount of MP input takes place. Moreover, about 50% of the globally remains untreated, and a good part of it is still utilized for agriculture. The MP concentration in effluent water from Australia was 934 mpm3, Al. 2017, whereas in British Columbia, Canada, the average influent and effluent concentrations were 31,100 and 1550 mpm3, Al. 2018, respectively. The average influent and effluent concentrations of WWTPs in Denmark are 7827 and 120 mpm3, Al. 2018, respectively. The data from the WWTP in Finland have influent and effluent concentrations of 57,400 mpm3 and 700 mpm3, respectively, Larry's Al. 2018. In another study in Finland, the influent MP concentration at WWTP was 430,000 mpm3, and the influent and effluent MP concentrations from WWTP were 380,000 mpm3 and 4,100 mpm3, respectively, Al. 2015. The average influent and effluent concentrations at Seine Centre WWTP, France, were 293,000 mpm3 and 35,000 mpm3, Al. 2015, respectively, whereas much higher effluent concentrations of 15,620 mpm3 were reported from Jade Byte WWTP, Germany, and 2013. Data from the WWTP in Italy reported that the influent MP concentration was 2,000 mpm3 and effluent concentration was 300 mpm3, Al. 2019. From Westport WWTP, Netherlands, the average influent and effluent concentrations were 276,000 mpm3 and 58,380 mpm3, respectively, Al. 2017. Murphy Al. 2016 reported an influent concentration of 15,700 mpm3 and an effluent concentration of 4,120 mpm3 from Glasgow WWTP, UK. An influent MP concentration of 12,430 mpm3 and an effluent concentration of 4,120 mpm3 were reported from WWTP, Spain, Al. 2020. The MP concentration in WWTP, Sweden, in the influent was 15,100 mpm3 and in the effluent was 8.25 mpm3, and 2014. Microplastics in influent and effluent streams of the WWTP were 25,000 mpm3 and 5555 mpm3, respectively, Al. 2018. In the Detroit WWTP, USA, the average influent MP concentration was 510,600 mpm3, and the effluent concentration was 81,144 mpm3, Al. 2016. The global data indicate that effluent water has a significant MP load, and given the water shortages, the untreated and partially treated is used for irrigation, leading to MP buildup in soil, WHO 2013. 623 Mulch films. Plastic mulch films are extensively utilized in modern agriculture to enhance crop productivity, soil moisture retention, and weed suppression, Samfire Al. 2023. Global plastic production reached 425 million tons in 2018, with China contributing 30% of the total production, and 2023. Despite the agronomic benefits of mulch films usage, these films degrade quickly and are seldom recovered, and less than 60% is recycled, Al. 2020, leading to significant environmental concerns, particularly soil microplastic pollution. The most commonly used mulch films are PE, known to degrade due to physical degradation, including tillage, harvesting, and weathering from UV exposure, mechanical stress, and microbial activity, leading to the generation of secondary microplastics, al. 2016, al. 2021. Residual plastic fragments from these mulch films persist in soils for decades. Plastic mulch films improve crop yields by regulating soil temperature, conserving water, and suppressing weeds. These benefits are critical in both arid and cold regions and for high-value crops, driving widespread adoption in 2012. There is equally compelling evidence highlighting the risks of microplastics from mulch altering soil structure, including reduced soil porosity, altered microbial communities and activities, altered nutrient cycling, and potential uptake of micro and nanoplastics by crops, al. 2023, al. 2019 and 2020. Microplastics may also adsorb toxic chemicals, posing risks to soil organisms and potentially entering the food chain. Hurley in 2018, al. 2020, al. 2024. Studies have demonstrated that soils under plastic mulch exhibit significantly higher microplastic concentrations than uncovered soils. Near Hangzhou Bay, China, mulch soils contained up to 1.080347 mpg1 after 24 years of use, compared to 0.8030493 mpg1 after 5 years, al. 2020, underpinning the hypothesis that MP concentration builds up in soil over time, and soil is a sink for MPs. This was further supported by the report that the duration of use directly correlates with microplastic levels, indicating progressive fragmentation of films into 5 particles, Joe al. 2020. However, there is variation in MP concentrations within the region and globally due to differing agricultural practices and recovery rates. In Mumbai, India, MPs are reported to vary between 0.0120315 mpg1 in mulched farmlands across rural to metropolitan areas. In another review, the paucity of data on MPs in agricultural soils in India was highlighted, al. 2022 and 2025. While the MP concentration in soils in northern Germany was 0.00430012 mpg1 harms, al. 2021, and in Tunisia, 0.88 mpg1, al. 2023. Plastic mulch, widely used in agriculture for weed suppression, moisture retention, and soil temperature regulation, has been estimated to contribute 10–15% of total MPs in agricultural soils globally, with higher contributions in plastic-intensive systems, in 2018. China accounts for about 60% of global plastic mulch use. Fields in Xinjiang showed 200–400 Ha1 of residual plastic after 10–30 years of use, al. 2014. Chi al. 2020, 5,300 MP1 mainly PE, in agricultural soil that was subjected to long-term plastic mulching in China. In Europe, PE mulch fragments were detected in 90% of sampled agricultural soils, al. 2018. To address the issue of MP emanating from PE plastic mulch films, biodegradable alternatives like acid PLA have been suggested, Chi al. 2020. However, PLA also degrades into MPs, albeit faster than PE, al. 2020. Research into cost-effective, fully degradable films is quite important, though current alternatives face challenges in durability and incomplete degradation. Hence, their long-term ecological effects remain uncertain. The issue is further exacerbated, as most countries lack regulations for plastic mulch recovery, enhanced recycling infrastructure, incentives for farmers to remove post-harvest films, and the use of biodegradable alternatives. 624 Organic fertilizer. The global shift towards sustainable agriculture has increased the of organic. The organic is prepared from animal manures, plant residues, and composted waste, al. 2021, and has become a cornerstone of eco-friendly farming. While organic enrich soils with essential nutrients, reducing reliance on synthetic, an insidious threat accompanies their application, the inadvertent introduction of MPs into agricultural soils. Emerging research underscores that organic, often perceived as a green alternative, are a significant yet pathway of MP introduction into the soil, with possible negative implications for ecosystem health and food security. The MPs infiltrate into the food chain via organic usage through absorption by plant roots and entering the food chain when consumed by livestock. Al. 2024. Analyses of organic reveal alarming microplastic concentrations. Al. 2018. In Bonn, Germany, plastic fragments larger than 0.5 were detected at levels of 2.38181, while another study documented 0.0140895 particles G1 of microplastics 1 in German, and 2018. Al. 2018, despite stringent regulations in Germany that limit plastic to 0.1% and ban MP200, microplastics persist due to gaps in waste processing. Similarly, Australia's National Association for Sustainable Agriculture permits 0.5% hard plastics and 0.05% light plastics in organic, yet there are no guidelines set so far. The MPs in organic waste in Australia range between 1,500 and 16,000 MP1, with polypropylene and polyester as the main polymer types in a size range of 25-500 Al. 2025. China is probably the largest consumer of organic, with an annual MP contribution from organic input to soils estimated at 52.4 tons, Al. 2022. In another study, the average MP abundance in animal-derived organic was 10,692.63353 MP1. In organic derived from plant and animal material, it was 7,914.244443 MP1, whereas in plant-derived organic compost, the concentration was 7,539.5277799 MP1, Su Al. 2024. The MP in farm compost was highest, with a concentration of 24,344.1269972 MP1, much higher than the commercial organic, where the MP ranged between 4,266.7227745 and 18,028.62000 MP1, Su Al. 2024. Smaller particles 0.15, which evade standard filtration methods, pose heightened risks due to their mobility and potential to disrupt soil microbiota and plant health. Fan Al. 2023, Al. 2024. This trend is not isolated, as 54% of MPs are 1.0, 35.2% in the size range of 1.3, 7.8% in the size range of 3.5, and 3% 5 Su Al. 2024. The presence of MPs in organic underscores a paradox of sustainable agriculture. Practices designed to heal ecosystems may inadvertently harm them. While organic remain vital for soil health, their contamination highlights systemic flaws in waste management and regulatory oversight. Only through proactive measures can we safeguard soils from becoming a sink for MPs, ensuring that the benefits of organic farming are not eclipsed by its long-term liability and possibly compromised ecosystem services. 6.25 Atmospheric deposition. A significant amount of literature has suggested the omnipresence of MPs in aerosol, Al. 2022, and their potential for long-range transport, Al. 2019. The MPs in dust and aerosols are deposited either via wet and dry atmospheric deposition or even with snow, Al. 2015, 2016, 2017, 2018, Al. 2019, Al. 2019, Al. 2021, Al. 2018, Liao Al. 2021, Al. 2020, Al. 2021, Wright Al. 2019, 2021. MPs in the air are released from wear and tear of clothing material Napper, and 2016, Henry Al. 2019, Falco Al. 2019, by washing and drying Al. 2011, erosion of synthetic rubber tires, deterioration of house furniture, emissions from the synthetic textile industry, emissions from vinyl chloride VC and polyvinyl chloride PVC industries, and contamination from city dust Al. 2015, 2016, 2017, 2018. MP concentrations vary dramatically across regions, with 0.315 mpm3 in outdoor Paris, Al. 2017, and 0.02154103 mpl1 in snow in the Arctic, al. 2019. The MPs in China ranged between 175 and 602 particles M2 day 1, al. 2017, Zhou al. 2017. In another report, 51 mpm3 was reported in the mountains of Wenzhou, China, Liao al. 2021, 275 mpm2 day 1 in Hamburg, and 2019, whereas from Indonesia, 132.7517497 mpm3, the West Pacific Ocean 0.137 mpm3, Denmark 1.67162 mpm3, Ireland 0.12 mpm3, Brazil 0.24 mpm3, California 0.656 mpm3. In Nottingham 2.9 mpm2 day 1, and central London 712.162 mpm2 day 1 were reported, al. 2019, al. 2019 c, al. 2019, al. 2020, al. 2021, al. 2019, right, al. 2020. The dry and wet atmospheric deposition in Vietnam ranged between 71 and 917 mps M2 day 1, al. 2021. From the available information, it is clear that atmospheric deposition might contribute MPs to soils. However, the use of inconsistent methodologies in sampling, processing, and reporting, e.g. MPM2 day 1 versus MPM3, hinder any reliable assessments. The capacity for long-range transport, coupled with variable sizes and concentrations, underscores the urgent need for harmonized research to quantify risks and inform mitigation strategies for MP management. 6.3 Laser Direct Infrared LDIR Imaging. Considering the complexity of the agricultural soil matrix, which is rich in organic matter and often laden with plant and animal debris, the spatial variation of soil types makes the extraction of MPs a complex task. The LDIR has emerged as a powerful tool for characterizing microplastics in environmental samples, enabling precise identification of polymer composition, morphology, and particle dimensions. Unlike conventional approaches, LDIR eliminates the need for chemical pretreatment, allowing rapid, non-destructive analysis that maintains the structural and chemical integrity of samples. Its high sensitivity facilitates the detection of trace microplastic levels through infrared spectral evaluation, al. 2024. The automated workflow of LDIR captures mid-infrared spectra from individual particles, cross-referencing them against a polymer database for particles spanning 2500, al. 2018, al. 2020. Using the precise and sensitive LDIR technique, an efficient MP identification, concentration, and size distribution in sediment samples is reported, which to a reasonable extent is similar to soil. The advantage of the LDIR is that instead of processing large sediment samples, comparable results are obtained with smaller sample sizes of 2.5 g, al. 2024. There have been significant efforts put into developing and improving the LDIR protocol, Whiting al. 2022 optimized LDIR protocols using polycarbonate filters, 8 porosity, achieving 80-100% recovery rates for 200-500 particles across environmental matrices, water, sediment, and biota. Their method reduced the analysis time to 3 per sample, a marked improvement over traditional techniques used in al. 2018, al. 2022. In another study, the enzymatic oxidative digestion coupled with LDIR showed a near-complete recovery for 500 particles and 75% for 10 in GI tracts of fish, al. 2018, al. 2024, suggesting its applicability in high organic matrices. al. 2022, integrated microwave-assisted digestion with LDIR, identifying 20 polymers, predominantly PET and PU, in diverse samples, with 93% of particles 100. Several studies have effectively used LDIR for environmental monitoring and assessments in China. Studies revealed microplastic concentrations of MPM3, primarily 100 fan al. 2022. Studies have demonstrated that the digestion of organic matter in a sample is a crucial step for MP determination by LDIR, as incomplete digestion can lead to false positives, low degree of correlation with the spectral library of polymers. LDIR was effectively used for MPs in lake sediments in China. The identification was reported as extremely rapid at 7.2 sec per particle, al. 2022. 2 agricultural areas in China were assessed for MPs using LDIR with concentrations of 383,786 MP1 and phthalate esters 0.31581 in soils, noting higher microplastic loads in greenhouse sites, Li al. 2021. 6.4 Discussion and Conclusion. Over the past decade, significant technological and progress has been made in detecting and quantifying MPs in environmental matrices. Each technique, whether spectroscopy, chromatography, or imaging, offers distinct advantages and constraints, necessitating careful selection based on research goals. Several workers have put detailed accounts of the efficacies of the various techniques used for MPs, al. 2020, Isaac, and 2025. It is quite obvious that MP analyses are time-consuming, and it becomes quite challenging if there are a large number of possible plastic particles in an environmental matrix like sludge, sludge-applied soil, or plastic mulch-applied soils. For environmental surveillance, a high-throughput technique is required, whereas studies on polymer toxicity or pathways demand higher spectral resolution and sensitivity. To keep this balance, LDIR chemical imaging has evolved as a promising technique for MP analysis. By employing a quantum cascade laser, QCL, LDIR captures infrared spectra in as little as 1 second per particle, enabling rapid mapping of thousands of particles across large sample areas. This efficiency surpasses traditional methods like Raman spectroscopy and Fourier transform infrared (FTIR) spectroscopy, which often require minutes per measurement. Integrated visible cameras in LDIR systems further enhance detection accuracy, resolving particles down to 10, critical for identifying smaller MPs prevalent in environmental samples. The spectral range of LDIRs currently covers 975-18001 and limits its ability to identify certain polymers, which exhibit characteristic peaks outside this window. Despite this, its non-destructive nature, minimal sample preparation, and high sensitivity make LDIR indispensable for MP monitoring in soil. Automation combined with machine learning algorithms for spectral matching could streamline high-throughput screening, enabling global MP monitoring. Innovations in QCL power and detector sensitivity may further enhance spatial resolution, allowing the detection of sub-10 particles, critical for understanding ecological impacts. Open access. This chapter is licensed under the terms of the Creative Commons Attribution 4 International License (ORG) licenses by 4.0, which permits use, sharing, adaptation, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if changes were made. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: S. al. 2019, Distribution and Potential Health Impacts of Microplastics and in Air and Street Dusts from County, Iran. Environ 244, 153, 164 PubMed. SN al. 2021, Does Microplastic Really Represent a Threat? A review of the atmospheric contamination sources and potential impacts. Total Environ 777, 14602, 0 PubMed. S. al. 2019, Atmospheric Transport and Deposition of Microplastics in a Remote Mountain Catchment. 12-339-344. LF al. 2021, Presence of Airborne Microplastics in Human Lung Tissue. J. Hazard Mater 416, 126-124 PubMed. VR 2025, Microplastic Contamination in Agricultural Soils Across India, a systematic review. J. Environ Climate Change, 15-2486503. VK Al 2024, Effects of Microplastics on Soil Microorganisms and Microbial Functions in Nutrients and Carbon Cycling, a review. Total Environ 924 17143 5 PubMed. MYJ Al 2023, Utilization of Sewage Sludge to Manage Saline Alkali Soil and Increase Crop Production, Is it Safe or Not? Environ Technol 32103266. Bao X Al 2024, Microplastics derived from plastic mulch films and their carrier function effect on the environmental risk of pesticides. Total Environ 924 171472 PubMed. JSJ 2020, Microplastics in an Urban Treatment Plant, the Influence of Physicochemical Parameters and Environmental Factors. Chemosphere 230 8124593 PubMed. MW 2018, Plastics in Soil, Analytical Methods and Possible Sources. Total Environ 612 422 435 PubMed. MA Al 2011, Accumulation of Microplastic on Shorelines Worldwide, Sources and Sinks. Environ Technol 40 5219 PubMed. El Al 2017, Characteristic of Microplastics in the Atmospheric Fallout from City, China, Preliminary Research and First Evidence. Environ, Raise 24-24928. YL Al 2022, Characterization of Microplastics in Sediment Using and Laser Direct Infrared LDIR Spectroscopy. Gondwana, Raise 108-2230. F. Al 2019, Evidence of Microplastic Accumulation in Agricultural Soils from Sewage Sludge Disposal. Total Environ 671 411 420 PubMed. F. Al 2021, Microplastics Occurrence and Frequency in Soils under Different Land Uses on a Regional Scale. Total Environ 752 141917 PubMed. J. Al 2020, Transfer and Transport of Microplastics from Biosolids to Agricultural Soils and the Wider Environment. Total Environ 724 138334 PubMed. Falco F. Al. 2019, The Contribution of Washing Processes of Synthetic Clothes to Microplastic Pollution. Rep 916633 PubMed Central. Vien Al. 2020, Quality Criteria for Microplastic Effect Studies in the Context of Risk Assessment, a Critical Review. Environ Technol 5419 1169211705 PubMed Central. Ding L. Al. 2020, The Occurrence and Distribution Characteristics of Microplastics in the Agricultural Soils of Shanxi Province, in northwestern China. Total Environ 721 37525 PubMed. R. Al. 2015, Microplastic Contamination in an Urban Area, a Case Study in Greater Paris. Environ 12592. R. Al. 2016, Synthetic Fibers in Atmospheric Fallout, a Source of Microplastics in the Environment. Mar. Bull 104 122 9293 PubMed. R. Al. 2017, A First Overview of Textile Fibers, including Microplastics in Indoor and Outdoor Environments. Environ 221 453 458 PubMed. R.J.B. 2018, Sources and Fate of Microplastics in Urban Areas, a Focus on Paris Megacity. In M. Lambert S. Microplastics, Emerging Environmental Contaminants. Springer International Publishing, CAM, 6983. F.G. 2013, Suspended Microplastics and Black Carbon Particles in the Jade System, Southern North Sea. Water Air Soil 224-2-1352. Fan Y. Al. 2022, Spatiotemporal Dynamics of Microplastics in an Urban River Network Area. Water Race 212-118116 PubMed. Fan W. Al. 2023, Sources and Identification of Microplastics in Soils. Soil Environ Health 12100019. J. Al. 2023, Assessing Metal Contamination and Speciation in Sewage Sludge, Implications for Soil Application and Environmental Risk. Rev Environ 224103-71058. DA Al 2024 Microplastics from Agricultural Mulch Films, Biodegradation and in Systems. Total Environ 912-169287 PubMed. J. Al 2018 Microplastics in Air, Are We Breathing It In? Environ Health 115s. M. Al 2024 Quantification and Characterization of Microplastics in Coastal Environments, Insights from Laser Direct Infrared Imaging. Total Environ 912-168835 PubMed. EA Al 2018 Retention of Microplastics in a Major Secondary Treatment Plant in Vancouver, Canada. Mar Bull 133-553-561 PubMed. Gui J. Al 2021 Microplastics in Composting of Rural Domestic Waste, Abundance, Characteristics and Release from the Surface of. Environ 274-116553 PubMed. S. Al 2018 Microplastics in Municipal Treatment Plants in Turkey, a comparison of the influent and secondary effluent concentrations. Environ Assess 190-11-626 PubMed. N. Al 2022 Microplastics in the Atmosphere, a Review. J. Environ Expo Assess 116. Harmsike Al 2021 Amount, Distribution and Composition of Large Microplastics in Typical Agricultural Soils in Northern Germany. Total Environ 758-1436-15 PubMed. Henry B. K. IG 2019 From Apparel and Home Textiles, Prospects for Including Microplastics in Environmental Sustainability Assessment. Total Environ 652-483-494 PubMed. L. Al 2022 Spatial Distribution of Microplastics in the Tropical Indian Ocean based on Laser Direct Infrared Imaging and Microwave-Assisted Matrix Digestion. Environ 307-119547 PubMed. Y. Al 2020 Agricultural Plastic Mulching as a Source of Microplastics in the Terrestrial Environment. Environ 261-14096 PubMed. Hurley R. L. 2018 Fate and Occurrence of Micro-Nanoplastics in Soils, Knowledge Gaps and Possible Risks. Environ Health 16116. Isaac P.J. S. 2025 Laser Direct Infrared Spectroscopy, a cutting-edge approach to microplastic detection in environmental samples. 284-127284 PubMed. ISO 2017, ISO 18401, to Soil Quality Sampling Part 102, Selection and Application of Sampling Technique. In First Edition 2017-01. IS Organization, Switzerland. W. Al 2022, Automated Identification and Quantification of Invisible Microplastics in Agricultural Soils. Total Environ 844-156853 PubMed. L. Al 2023 Microplastic Stress in Plants, Effects on Plant Growth and Their Remediations. Front Plant 1412264484 PubMed. PubMed Central. BKKK S. Fowler SW 2023 Microplastics MPs in Marine Food Chains, Is It a Food Safety Issue? In F. Lead, Advances in Food and Nutrition Research. Academic Press 101-140. SM 2012 Polyethylene and Biodegradable Mulches for Agricultural Applications, a Review. Agron Sustain 32501. M. EK 2019 Microplastic Abundance in Atmospheric Deposition within the Metropolitan Area of Hamburg, Germany. Total Environ 68596 PubMed. AJ Al 2024 Strategy Towards Producing Relevant and Reliable Data for the Hazard Assessment of Micro and Nanoplastics in Agricultural Soils. AC Trends Anal 172-117567. Larry's M. Al 2018 Occurrence, Identification and Removal of Microplastic Particles and Fibers in Conventional Activated Sludge Process and Advanced MBR Technology. Water Res 133 236 246 PubMed. Lee J.Y. al. 2024, A Comprehensive Review of Urban Microplastic Pollution Sources, Environment and Human Health Impacts and Regulatory Efforts. Total Environ 946, 174297 PubMed. Ha al. 2017, Microplastics en route, Field Measurements in the Dutch River Delta and Amsterdam Canals, Treatment Plants, North Sea Sediments and Biota. Environ 101 133 142 PubMed. Lee X. al. 2018, A Microplastics in Sewage Sludge from the Treatment Plants in China. Water Res 142 7585 PubMed. Lee J. H. J. 2018 B. Microplastics in Systems, A Review on Occurrence, Environmental Effects and Methods for Microplastics Detection. Water Res 137 362 374 PubMed. Lee Q. al. 2021, Are Microplastics Correlated to Phthalates in Facility Agriculture Soil? J. Hazard Mater 412 125 164 PubMed. Liao Z. al. 2021, Airborne Microplastics in Indoor and Outdoor Environments of a Coastal City in Eastern China. J. Hazard Mater 417 12600 7 PubMed. EK HWQ CR 2014, White Revolution to White Pollution Agricultural Plastic Film Mulch in China. Environ Race 99091001. SL al. 2019, A Pollution Characteristics of Microplastics in Migratory Bird Habitats Located Within Lake Wetlands. Jing 4626392646 PubMed. K. al. 2019 B. Accurate Quantification and Transport Estimation of Suspended Atmospheric Microplastics in Megacities, Implications for Human Health. Environ 132 105127 PubMed. K. al. 2019 C. Consistent Transport of Terrestrial Microplastics to the Ocean through Atmosphere. Environ Technol 5318 106 1210 619 PubMed. N. al. 2022, Characterization of Microplastics in the Septic Tank via Laser Direct Infrared Spectroscopy. Water Res 226 119293 PubMed. A. al. 2024, A Reliable Method to Determine Airborne Microplastics Using Quantum Cascade Laser Infrared Spectrometry. Total Environ 913 16967 8 PubMed. HC al. 2025, Microplastic in Australian Processed Organics, Abundance, Characteristics and Potential Transport to Soil Ecosystem. J. Environ 375 124359. S. al. 2019, The Fate of Microplastics in an Italian Treatment Plant. Total Environ 652 6 02 610 PubMed. KF 2014, Screening of Microplastic Particles in and Downstream a Treatment Plant. In IVL Report C, P22. K. al. 2016, Swedish Sources and Pathways for Microplastics to the Marine Environment. Report C 183. Swedish Environmental Research Institute, Stockholm. PAA 2022 Plastic Mulching, Microplastics in Agricultural Soil. S. al. 2021 Micro and Nanoplastics Identification, Classic Methods and Innovative Detection Techniques. Front Toxicol 3636640 PubMed Central. Mr. al. 2016, Fate of Microplastics and Other Small Anthropogenic Litter SAL, in Treatment Plants Depends on Unit Processes Employed. Environ Waterways Technol 210641064. SM al. 2017, Identification of Microplastic in Effluents of Wastewater Treatment Plants using Focal Plane Array-Based Micro-Fourier Transform Infrared Imaging. Water Res 108 365 372 PubMed. L. al. 1989, The Air Pollutant 2 as Initiator and Promoter in a Liver Model for Chemical Carcinogenesis. Carcinogenesis 1034 354 40 PubMed. A. al. 2020, The Pollution Conveyed by Urban Runoff, A Review of Sources. Total Environ 709 136125 PubMed. Murphy F. al. 2016, Treatment Works TW as a source of microplastics in the aquatic environment. Environ Technol 5011-5800 PubMed. A. al. 2021, Microplastics in Outlets of Bandar Abbas City, Iran, a potential point source of microplastics into the Persian Gulf. Chemosphere 262, 128039 PubMed. Napper IE RC 2016, Release of synthetic microplastic plastic from domestic washing machines, effects of fabric type and washing conditions. Mar Bull 112, 13945 PubMed. El al. 2018, an overview of microplastic and nanoplastic pollution in Total Environ 627, 13771388 PubMed. Ed al. 2021, Plastic Particles in Soil, State of the Knowledge on Sources, Occurrence and Distribution, Analytical Methods and Ecological Impacts. Environ, Processes Impacts 2322-4274. S. al. 2018, Identification and Quantification of Macro and Microplastics on an Agricultural Farmland. Rep 8117950, PubMed Central. J.C. al. 2020, The Importance of Contamination Control in Airborne Fibers and Microplastic Sampling, Experiences from Indoor and Outdoor Air Sampling in Portugal. Mar Bull 159 111522, PubMed. S. al. 2018, Reference Database designed for the automated analysis of microplastic samples based on Fourier Transform Infrared FTIR spectroscopy. Anal 410-513-15141, PubMed Central. S. al. 2020, Critical Assessment of Analytical Methods for the Harmonized and Cost-Efficient Analysis of Microplastics. 74910-12104-7 PubMed. Chi al. 2020, Effects of Plastic Mulch Film Residues on Wheat Rhizosphere and Soil Properties. J. Hazard Mater 387, 121711 PubMed. SHKT 2024, Environmental Fate of Microplastics and Common Polymer Additives in Non-Biodegradable Plastic Mulch, Applied Agricultural Soils. Environ 363, 125249 PubMed. MCA 2020, Microplastic in Terrestrial Ecosystems. Science 368-649, 81430-1431 PubMed Central. MC al. 2019, Microplastic Effects on Plants. New 223-3, 10661070 PubMed. B. al. 2020, Ambient Atmospheric Deposition of Anthropogenic Microfibers and Microplastics on the Western Periphery of Europe, Ireland. Environ Technol 5418-11100-11108 PubMed. IA 2023, Plastic Contamination in Agricultural Soils, a Review. Environ 35113. Samfire M. Dr. Jones DL 2023, Biodegradable Plastic Mulch Films Increase Yield and Promote Nitrogen Use Efficiency in Organic Horticulture. Frontigron 5-114-1608. A. al. 2020, Occurrence of Microplastic Pollution at Oyster Reefs and Other Coastal Sites in the Mississippi Sound, USA, Impacts of Inflows from Flooding. Toxics 8235 PubMed Central. L. al. 2023, Microplastics in, a Review of Effects on Soil Biota and Key Soil Functions. J. Plant Soil 186-1522. M. Van N. J. 2018, Quantification of Microplastic Mass and Removal Rates at Treatment Plants Applying Focal Plane Array, FPA-based Fourier Transform Infrared FTIR Imaging. Water Rays 142-19 PubMed. N.S. Taylor MP, Wilson S.B., 2021, Quantification and Exposure Assessment of Microplastics in Australian Indoor House Dust. Environ 283-117064 PubMed. T. al. 2019, and airborne textile populations are dominated by natural, not microplastic. Total Environ 666, 377 389 PubMed. Z. al. 2016, Plastic Mulching in Agriculture. Trading short-term agronomic benefits for long-term soil degradation. Total Environ 55697, 5 PubMed. Stock F. Al. 2019, Sampling Techniques and Preparation Methods for Microplastic Analyses in the Aquatic Environment, a Review. AC Trends Anal 113, 8492. Sun J. Al. 2019, Microplastics in Treatment Plants, Detection, Occurrence, and Removal. Water Rays 152, 21, 37 PubMed. Sun N. Al. 2023, Combined Toxicity of Micro-Nanoplastics Loaded with Environmental Pollutants to Organisms and Cells, Role, Effects, and Mechanism. Environ 171, 107711 PubMed. A. Al. 2019, Microplastic Pollution in the Ambient Air of Surabaya, Indonesia. World Environ 14, 290-298. J. Al. 2015, Do treatment plants act as a potential point source of microplastics? Preliminary study in the coastal Gulf of Finland, Baltic Sea. Water Technol 72914951504 PubMed. J. Al. 2017, How well is purified from? A detailed study on the stepwise removal of in a tertiary level treatment plant. Water Rays 109 164 172 PubMed. Tien Al. 2021, Microplastic in Atmospheric Fallouts of a Developing Southeast Asian Megacity Under Tropical Climate. Chemosphere 272, 129874 PubMed. S. Fowler SW, M. 2020, An Assessment of Microplastic Inputs into the Aquatic Environment from Streams. Mar Bull 161 11538 PubMed. S. Al. 2020 B. Standardized Protocols for Microplastics Determinations in Environmental Samples from the Gulf and Marginal Seas. Mar Bull 158 111374 PubMed. S. Al. 2021, A Review of Microplastic Distribution in Sediment Profiles. Mar Bull 163 111973 PubMed. S. Al. 2022, A Microplastics in Kuwait Streams. Sustainability 1423 15817. S. Al. 2022 B. Micronanoplastic in the Aquatic Environment, Problems and Challenges. Animals 123297 PubMed Central. ASS Fowler SW 2023 A Environmental Microplastics, a Significant Pollutant of the Anthropocene. In Kane C. AM Microplastic Sources, Fate and Solution. Springer Nature Singapore 89105. S. Al. 2023 B. Aerosols as Vectors for Contaminants, a perspective based on outdoor aerosol data from Kuwait. 143470. S. Al. 2024 Sewage Sludge as Soil Amendment in Arid Soils, a Trace Metal, Nutrient and Trace Organics Perspective. Emerge 1111000420. AG Al. 2023, Thickness-Dependent Release of Microplastics and Acid Esters from Polythene and Biodegradable Residual Films in Agricultural Soils and its Related Productivity Effects. J. Hazard Mater 448130897 PubMed. A. Al. 2019, Simulating Human Exposure to Indoor Airborne Microplastics Using a Breathing Thermal Mannequin. Rep 918670 PubMed Central. F. Al. 2022, Effects of Microplastics on Soil Properties, Current Knowledge and Future Perspectives. J. Hazard Mater 424 12753 1 PubMed. C. Al. 2024, A Review of the Application and Impact of Drip Irrigation under Plastic Mulch in Agricultural Ecosystems. Agronomy 14-81752. N. Al. 2018, Organic Fertilizer as a Vehicle for the Entry of Microplastic into the Environment. Ad 448060 PubMed Central. Whiting QT Al. 2022, A High-Throughput Automated Technique for Microplastics Detection, Quantification, and Characterization in Surface Waters using Laser Direct Infrared Spectroscopy. Anal 41429 38353 8364 PubMed Central. WHO 2013 Guidelines for the Safe Use of Excreta and Use in Agriculture, 4. World Health Organization, France, 1177. Wright S.L. J.M. Kelly F.J. 2019, Raman Spectral Imaging for the Detection of Microplastics in Ambient Particulate Matter Samples. Environ Technol 53 1589478956 PubMed. Wright S.L. Al. 2020, Atmospheric Microplastic Deposition in an Urban Environment and an Evaluation of Transport. Environ 136 105411 PubMed Central. Wright S.L. Al. 2021, Development of Screening Criteria for Microplastic Particles in Air and Atmospheric Deposition, Critical Review and Applicability Towards Assessing Human Exposure. 116. YSJ 2023, Microplastics as Vectors of Organic Pollutants in Aquatic Environment, a review on mechanisms, numerical models, and influencing factors. Total Environ 887 16400 PubMed. SUGY XY 2023, a different effects and mechanisms of polystyrene micro and nanoplastics on the uptake of heavy metals, and Seed by Lettuce Sativa L. Environ 316 120656 PubMed. SUX Al 2023 B. Treatment of industrial ferric sludge through a facile acid-assisted hydrothermal reaction, focusing on dry mass reduction and performance. Total Environ 869 161879 PubMed. SUJ Al 2024, Quantification and Identification of Microplastics in Organic Fertilizers, the Implication for the Manufacture and Safe Application. Water Air Soil 235 169. El Al 2018, Pay Attention to Research on Microplastic Pollution in Soil for Prevention of Ecological and Food Chain Risks. Bolchin Acad 33103. MS 2024, Sewage Sludge Usage in Agriculture, Are We Introducing Microplastics in Food Chain? Soils, International Atomic Energy Agency 10278. KAL 2018, Microplastic Pollution in China's Inland Water Systems, a review of findings, methods, characteristics, effects, and management. Total Environ 630 164 11653 PubMed. El Al 2020, An Overlooked Entry Pathway of Microplastics into Agricultural Soils from Application of Sludge-Based Fertilizers. Environ Technol 54 74248425 PubMed. Ex Al 2021, Systematical Review of Interactions between Microplastics and Microorganisms in the Soil Environment. J. Hazard Mater 418 126288 PubMed. S. Al. 2022, Occurrence and Distribution of Microplastics in Organic Fertilizers in China. Total Environ 844 157061 PubMed. S. Al. 2024, From Organic Fertilizer to the Soils, What Happens to the Microplastics? A Critical Review. Total Environ 919 1702 17 PubMed. M. Al. 2020, The Usage and Environmental Pollution of Agricultural Plastic Film. Asian J. 42132. Jo Q. C. Luo Y. 2017, Various Forms and Deposition Fluxes of Microplastics Identified in the Coastal Urban Atmosphere. Chin Bull 62 3902 3909. Jo B. Al. 2020, Microplastics in Agricultural Soils on the Coastal Plain of Hangzhou Bay, East China, Multiple Sources Other than Plastic Mulching Film. J. Hazard Mater 388 121 814 PubMed. S. Al. 2017, Treatment Plants as a Pathway for Microplastics, Development of a New Approach to Sample-Based Microplastics. Water Res 112 9399 PubMed.